Okay, let's start on time. So welcome to the fourth day of the winter school. The first lecture is given by Professor Lin Chen. He will continue the discussion on ADI-CFT correspondence.
吴老师，你要不行，你先来，我没关。
And the schedule.
那没事，那吴老师先来吧。不是他吴老师要有事儿，可以先来，没关系的。可以换一下。你先来吧。楼上，他
昨天他安排我别的事情，把我放到另外对，
好吧，
旁边有咖啡馆，那时候看的。
楼上有那种机器，他说的磨的，没事。
我也正好有，今天呢我又安排了后面的事情。
是，你先来，没关系，我晚1小时没问题。
讲第二个 PPT 还是昨天那个接着讲？
没有讲完。
那我先来第一个吧。
我要听一下，对。
大概是到哪里？您看一下。
我第二个用中文讲的。
都可以。
这边就没有有两个。
但是不要紧。你第一个就今天就都用中文讲的吧？
没有啊，我第一个还是用英文讲
，OK，
还是用英文讲。对，就这样，对，就这样。这个怎么那么亮？你这个是不是我打了它
Okay, well, we do a little change in the schedule. So we switch the first and second lecture today. Okay, let's start. The first lecture is given by Professor Yueliang Wu. He will continue the discussion on the hyperunified theory and the gravitational quantum field theory. Let's welcome him.
Okay, good morning. So yesterday we discussed the gravitational quantum field theory. So today we'll discuss how to build the unified theory within the gravitational quantum theory. So I already yesterday we mentioned how the Dirac equation indicates that the dimension of space-time determine the independent degree of freedom. So then today we will do other way around for the unification theory. So now we already know in the standard model, we have 3 generations, leptons and quarks. So the total degrees for leptons and quarks about 256 degrees of freedom. Then we ask another question. So we have so many degrees, and we will ask what dimension of space-time that called have the motion. And eventually we found if we want to unify all leptons and quarks into a single spinor field, so then we need 19-dimensional space-time. They can move. They have motion in 19-dimensional space-time. Then we have the symmetries in 19-dimensional space-time as this generalized Lorentz symmetry or this hyper-Lorentz symmetry. And then we have spin symmetry. It's SP118 in the 19 spin related the intrinsic space-time. So then we separate these 2 symmetries, then we gauge the symmetry in the spinor representation. It's a hyperspin symmetry. Okay, and so then all the formalism for formulation or to construct the actions of unification theory is similar to I think as the for electron in the 4-dimensional space-time. Okay, so we just based on this symmetry. This we call the joint symmetry as the high Poincare symmetry in the 19-dimensional space-time, and also we have this spin symmetry in spin-related 19-dimensional space-time. So then that come to our construction for the hyperunified field theory. Actually, we want to ask more deep questions. Before, we already know the spinor field, the Dirac field, the Weyl field, and we know the Lorentz symmetry, and we know dimensional space-time, and that's one dimension, the temporal dimension, and the other spatial dimension. Then we will ask how they come out. What is more spatial, more fundamental principles to lead to this the symmetries and the space-time why time is different from the space and so on for those questions. So we just start more fundamental notion. So that the one is I call it the maximum coherence motion principle. And that means we start from motion. Okay, we do not start from space-time, do not start from the symmetries. We will derive the space-time, and also the why the spinor is a fundamental building block of nature. Okay, like electron or neutrino quarks. Okay, so what is the maximum coherence motion principle? The basic notion is that we suppose our universe is composed of fundamental building block, okay? And then we suppose all this fundamental building block has motion. They should be not static. So they have the motion, and then we require the motion to satisfy orbit a simple law. Then what is simple law? So here I suppose is called the maximum coherence motion principle, which contains 3 postulates. So one postulate is the motion should be simplest one. Okay, we know the law of nature should orbit the simple law, and then we require when we introduce the independent degree of freedom, they should be correlated. They are not independent. If that's one of degree is independent than others, so that degree is no sense. Yeah. So we require all the independent degree of freedom are correlated. So that means their motion should be correlation motion. Okay. And then we require the quadratic. Normally we know this wave motion. So we require each degree, independent degree of freedom should have the motion as the wave motion, the free wave motion. Okay. So just a 3 simple postulates, and we will derive all we know in the standard model. And then we just based another principle. This principle we already know. We call gauge and scaling invariance principle. Okay, that's we already know. So we just that this principle means so the laws of nature should be independent of the choice of the local field of configuration. Okay, and also scaling transformations. Just like the general relativity, the Einstein's the basic principle is independent of all coordinate, choice of coordinate. That means the covariance principle. So here we do not discuss the coordinate at the beginning. We discuss the independent degree of freedom. So we chose the independent degree of freedom, but the physical laws independent of your choice, and also different configuration of the field. Okay, so then we suppose the basic constituent or fundamental building block of nature is given by a column field that contains independent degrees of freedom, and then we require the simplest motion. What do you mean simplest motion? Then we require the motion is only the first only contain the first derivative. Okay, there's no quadratic derivative. There's only one linear. Okay, the derivative, and then we require that motion is correlated, so they are correlated by the matrix, and then we require the quadratic motion is independent for each degree of freedom, and you will find this gamma matrix have to satisfy the Clifford algebra, right? And then we can prove this field, I mean the single column field, had to be anti-commutation, okay? So satisfy these anti-commutation relations. So that's actually gave the Pauli exclusive principles, okay? So this comes from this naive assumptions, okay? And then we can also prove, from this one, we can prove there's only one temporal dimension. Other dimensions should be spatial, okay? I say this matrix satisfies the Clifford algebra, and you can, from the signature, we can see there's one temporal dimension, the others have to be spatial one. Okay, then we found there's maximum symmetries, okay? So without introducing the gauge principle, and the symmetry is associated symmetry. So that in a parameter, this at the beginning is a parameter. Eventually we know, because there's one temporal dimension and the other spatial dimension, so we regard these parameters as the spatial dimensions. And you will find that so the symmetry in the space-time, in coordinate space-time, and the symmetry for the spinor field, they should be associated. So this is the inhomogeneous, the hype Lorentz symmetry, this inhomogeneous hype spin symmetries, and plus two scaling symmetries. And then there's also some symmetries independent of this motion. We call it intrinsic symmetries. And eventually we found that the intrinsic symmetry, independent of the motion, is periodic. It's only from, there's spatial charges, 0, 1, 2, 3, only 4 classes. Then we can classify all this fundamental building block into 4 classes eventually, okay? And then we can prove that. So when we reproduce the symmetry in the standard model, and we need at least a 14-dimensional spacetime. And in this 14-dimensional spacetime, and we found that they contain exactly 2 generations of leptons quarks. So that means nature should exist at least 2 generations, or 2 families of leptons quarks, okay? And okay, so this is why the question why that when there's 1 more families. Maybe you can read from some history of for leptons quarks. When the mu lepton discovered in 1930s, the Rabi asked who ordered that one, because our nature considered all matter we observed, including all the materials. There's only first family of lepton quarks, electron, up quark, down quark. So why we need the mu? So we don't understand. So here we see from the unification, if we want to reproduce the standard model symmetry, we need at least 2 families of leptons quarks. Okay, so this proof. And then why 4-dimensional spacetime? Here I say we need 14 dimensions at least to reproduce the standard model symmetry, and we need 19 dimensions to include all 3 families of leptons quarks. Okay, but how? But our observed universe now is only 4-dimensional spacetime, and then we should answer why 4-dimensional spacetime. But of course, in string theory, so that 10-dimensional spacetime, that is resulted from consistency of the theory mathematically. Okay, but here we will answer because all space dimensions has physical meaning here. So why 19 dimensions is determined by quantum numbers. So 4-dimensional spacetime from spin, and then we have another 4-dimensional spacetime from isospin, left, right hand isospin, and another 6 dimensions as needed because we have leptons quarks that have color. Okay, the 3 color of quarks and the 1 color we can regard as leptons, so 1 color. So we have 6 dimensions. So this is why we need 14 dimensions. Then we have 3 families of leptons, quarks. We have additional 5 dimensions for families. Okay, and then we answer why our observed universe is 4-dimensional space-time. So the answer is very simple. We can prove that if there's only 1 family of leptons, quarks, they can only have motion. I mean, in the spin-related graph gauge space-time, they have only motion in 4-dimensional space-time. So that's why, because our observed universe, they consist only the first families of leptons, quarks, electron, and proton, neutron. Proton, neutron is considered by the 2 quarks, okay, upper and down quark. They all belong to the first family of leptons, quarks. So why our observed universe is only 4-dimensional space-time. So that means if add leptons, quarks, the second family of third family, or if they have more families, if they get mass, become heavy, and then eventually decay to the only first families of leptons, quarks. They are latest one, so that cannot decay like electron is stable. Of course, neutron can decay, but when they are in the nucleon state, they do not decay, yeah, they become stable. So then we can understand why our observed universe only 4-dimensional space-time, because they only consist of first families of leptons and quarks. Okay, that's some conclusion. Okay, so then we can write down. Okay, in 19 hyperspace-time, 19-dimensional hyperspace-time, we can write down these actions. Okay, so unify all the interactions and unify all fundamental building block of lepton quarks. Okay. Okay, then we have the jointed symmetry. Now I call that is the Pangala type symmetry in hyperspace-time, 19-dimensional hyperspace-time, and then we have this inhomogeneous hyperspin symmetries. They are now become jointed symmetry because this is local gauge symmetry. This can be globally flat. Minkowski space-time is global symmetries, and then there's 2 scaling symmetries in coordinate in the field. Okay, so that's all. Okay, so I just have no time for details. So that's 2 long papers. It's about together about 300 pages. Eventually, I actually produce it as a book. Okay, for the first part, we want to discuss the fundamental building block and the symmetry, so we can answer the problems. What is meant to be the fundamental building block of nature in the spinor field in the 19-dimensional chiral-dimensional representation of 19-dimensional space-time. And what brings about the fundamental symmetry of nature is because the independent degree of freedom and the quantum numbers, which symmetry governs gravitational interaction, is related to this hyperspin. So because all other fundamental symmetries unified to the hyperspin symmetry, and because it's hyperspin symmetry is gauge symmetry, we need to introduce the hypergraph gauge field. So that is the gravitational interaction. So what is the basic structure of space-time, and how many dimensions does space-time have? So for 3 families, at least we need 19 dimensions. And why time is different from space-time? So there's only 1 temporal dimension and other spatial dimensions. Actually, why we cannot observe the time? We can only observe the space. Okay, because the space-time is spatial dimension is for rotational one. For the temporal dimension, the symmetry is the Bose symmetry. So they change the amplitude of the field. But for the spin symmetry, they rotate among the different independent degree of freedom. Okay, so then that's from polarization you can observe this rotational symmetry, but you cannot observe the temporal dimension. But they only change the amplitude of field. That means you can you can feel the change of amplitudes to feel the time, okay, in a sense. Okay, then we already answered why we do live in a universe with only 4-dimensional one, this observed universe, and why there's leptons and quarks more than one families, and actually this we should also answer why there's maximum parity violation. They are all in chiral representations. Okay, and then second part we discussed the fundamental interaction and the evolving universe. Yeah, so actually I already discussed the symmetry govern the fundamental interactions. When we know the symmetry, and then the gauge principle, we know the interactions. And in this theory, in 19-dimensional space-time, you can only introduce one single scalar field. The others are all gauge field. The single scalar field can provide the primordial energy for the early inflation, and later on, it can provide a dark energy. Okay, and then so in this model, there's no Higgs particles. Okay, in the 19-dimensional space-time, they're all gauge field. There's no Higgs bosons. But actually, when we reduce the 4-dimensional space-time, all the gauge field in high-dimensional space-time, when you look at it in the 4-dimensional space-time, they all behave like scalars, or like bosons, not scalars, like bosons. Okay, okay. So that's why the Higgs particle, Higgs bosons in this theory, in the unified theory, at the beginning they behave as gauge bosons and factor bosons in high-dimensional space-time. But when you look at it in 4-dimensional space-time, they actually behave like scalar bosons. Okay. Anyway, so maybe I no have time to reproduce this inclusion. Actually, we already know now. So laws of nature independent of any choice of coordinates, and we can construct within the gravitational quantum theory. I showed yesterday we can construct the Lagrange or actions in the spin-related graph gauge spacetime, hypergraph gauge spacetime, hyperspacetimes. Okay. Anyway, so I already explained that this dimensional spacetime is different from the string theory, 10-dimensional, 11-dimension. They just obtained from the anomaly cancellation and consistency. But in this series, each dimension has physical meanings. Okay, when you want to bring symmetry to the low energies, you just you can break in the space-time structure of space-time because they all relate to the quantum numbers. Okay. Anyway, so for the nature of gravity and the space-time structure, we now in the Newton theory, as I emphasized yesterday, so matter, space, and time are different. They're absolute space-time. And in the spatial relativity of Einstein, so space and time, they are form the Lorentz symmetries. And in the general relativity, general theory of relativities, and the space-time is determined by distribution of matter, the energy momentum tensor. But in the gravitational quantum field theory or hyperunified field theory, the space-time itself is matter. Because the coordinate space-time, so we can always choose globally flat mean cosmic space-time. That is really, in a sense, like a vacuum. So they just describe the motion and without interactions. So actually, that space-time can be infinitely large, but we cannot observe because if there's interactions. And then actually we have another spin-related intrinsic space-time. So yesterday I said by-from space-time. So that space-time describes interactions with all the spinor field and the gauge field. Okay, so that space-time is observable through the interactions, gravitational interactions, for example. Okay. Okay, maybe I direct go to now. That's already finished for this unification within the gravitational quantum field theory. So maybe I could take a little time to go to the TIGIC program to test, or eventually we want to understand the nature of space-time and the gravity, and then we can use the space-based gravitational wave. Okay, when we come to the another one, yeah. So the TIGIC program is actually is quite similar to the LISA. Maybe it's better if maybe I prepared in English. Maybe I don't know if you better understand Chinese, but we still have some foreigner. If you don't care, I speak Chinese. Maybe they could understand it. But here you can already from my English. So anyway, the LIGO announced the direct discovery of gravitational wave in 2016. So which provided the more fundamental test on the general theory of relatives, and then it asked us to have deep study to understand the nature of space-time and gravity. So this is why I come to this long papers. I should thank this COVID-19. I got all the time stay home to just to think and write. Okay, so the TIGIC is a Chinese space-borne gravitational wave detection, and leading by the Chinese Academy of Science. And I think okay, I turn to the Chinese now. 这个太极计划是这个中科院的这个发起的一个空间引力波探测的计划。那么它也是由3颗卫星组成，跟这个 LISA 计划是类似的。OK， 这个3颗卫星，那么是绕着太阳转。OK， 在地球前面或在地球后面，大概18度到20度左右。OK， 那么这个计划的话呢，我简单介绍一下。最早从2008年，我们有吴文来院士。这个组织国内有中科院，但是叫基础局组织讨论这个空间引力波探测。那么10年就开始技术和这个研究关键技术。那么11年的话呢，已经完成了基本的一些设计等等。那个时候的话呢，这个原来呢再早呢我们知道这个 LISA 计划是欧空局和 ESA 跟 NASA。他们是在上个世纪90年代开始讨论，提出这样的计划。那么到2011年的时候呢，这个 NASA 退出去，由于经济原因、各种原因，就 LISA 自己来做。LISA 自己来做呢，他把原来的3颗卫星变成一个小3星，那他邀请中国来参加。所以当时的话呢，在2012年的话呢，我们实际上就是，OK， 所以邀请我们参加的话呢，那么我们。有机会呢，参加了他们第一次的这个ELISA 的 consortium 的 meeting， 在2012年在巴黎。那么当时我们就报告了中国的空间引力波探测计划。当时我们是有3步走的计划，但是呢有这个2条腿3步走。什么叫2条腿3步走呢？一条腿就是跟欧空局合作，按照国际惯例贡献20%，那么参与他们的合作。一种呢就是我们独立的做，是吧？如果是我们独立做呢，我们就要分3步走，这个就是当时提出来的。那么在那个会上，我们第一次提出来，这个3颗卫星组成一个正三角形，并且每颗卫星之间的距离300万公里。这个是不管是从科学目标还是工程实现，我们认为300万公里是在优化的一个构型。看，那么这个关于科学目标刚才讲的这个为什么是吧？并且比 LISA 要好，是吧？这个构型，它们灵敏度也比它要好。OK， 那么同时呢，当时把它的灵敏度呢调到0.01这个赫兹这个范围。那么这个时候呢，在这个中等质量黑洞这个探测比较敏感。因为最终呢，我们希望要理解这个大黑洞、超大质量黑洞怎么形成的。小黑洞我们知道是这个塌碎以后，是吧？恒星塌碎以后形成的。在于超大质量黑洞，我们并不清楚。那么一种想法就是可能是从中等质量黑洞它们成长演化过来的。 那么所以我们把这个灵敏度调节到0.01赫兹，然后呢300万公里，那么是最优化的一个方案。那么接下来的话呢，我刚才讲，所以我们就提出了这个我们自己的一个计划。当时，那么到了2015年，刚才讲的2015年，实际上4月份的时候，当时卡夫里研究所我们举办了全世界的关于引力波的一个会议。当时这个莱国的这个发言人做了2个报告。那么最后一个报告的时候，还专门问他，我说这个莱国什么时候能够观测到这个引力波？他说可能按照他们的估计，起码1年以后，因为他这个估算这个世界力啊，他说最小可能这个1年也许能碰上一个啊，这个当然是也不排除大的可能性。这是4月份的时候，他们的发言人在理论物理所那个卡夫里研究所做报告时说的。到9月份的时候，我收到一个他们的内部的信件啊，组织者当时告诉我他们看到了这个引力波，当时要求我保密啊，不能说出去。那我还是遵守诺言，没有说。那么大家知道，后来2016年2月份是宣布他们直接观测到引力波 ，OK。所以呢，他们应该说是很幸运，是吧？那么这完了以后的话呢，我们就决定中国的引力波我们自己做。我原来说的是2条腿，一条腿我是合作，一条腿自己。所以当时我们就决定自己做了。所以我们这个时候对外宣布中国空间引力波探测叫太极计划 ，OK。这是当时原则上这个全国最早2008年开始我们就一个计划。那么后面我们知道也有天津计划，是吧？天津计划绕着地球轨道，那么我们绕着太阳轨道。那么当时太阳轨道，我们刚才讲的2012年我们就提出这个壁上300万公里的这个三角形正三角形绕着太阳转，是吧？那么我们看看这个 LISA 计划呢，最早刚才讲的ESA 跟 NASA 在一起的时候，他们是500万公里，就5年左右。那么后来刚才说这个NASA 退出去以后，2011年，包括他们邀请我们也加入的是，他们100万公里，并且这个3星的话只有2路激光干涉。那6颗星的时候，原来最早是6路激光干涉，因为经费的原因啊等等。那么后来我说我们到2015年，我们后来一直在2012年，我们就一直，假如我们自己做的话，我们是300万公里是最好。OK， 当时我们提出来。那么后来到17年的时候，16年我宣布太极计划自己做。17年的时候，这个 NASA 这个在中国科学院大学就在这样，我们召开的一次国际引力波会议。NASA 说他们要回到ESA，这个一起参加这个空间引力波探测。所以当时呢，又恢复到原来的这个 LISA 的整个3个卫星6路激光干涉。那么他提出来是250万公里，那这个就跟我们300万公里很接近了。所以这两个卫星，我想这2组的卫星的探测 ，LISA 和太极现在是比较接近的。看，这个我刚才讲的就在我们这开的一个会议啊，这个会议差不多是 LISA Pass Fund 的首席科学家，还有ESA、NASA 的他们参与的这个所有的这个单位的代表都参加了，是吧？这是一个比较大的。在这个会议上 ，NASA 就宣布决定他们要跟ESA 在一起合作，在 LISA 恢复到原来的 LISA 计划，把臂长变成250万公里。OK， 那么太极计划的话呢，我刚才讲我们就分3步走，这个最终这个太极计划要求达到的这个指标，比如激光干涉，我们要求是8个皮米，是吧？那么这个无拖曳控制要求在加速度的噪声，我们要达到10^-15次方每秒米。看那个精度都是现在这个极限的一个精度。好，那么中国2012年宣布太极计划，那么接下来呢，我们就很快就得到这个科学院的这个先导的支持。我们在2018年8月30号立项，正式立项。2019年这个8月31号这个发射，这个发射的时候正好是早上7点41分发射成功。那正好那一年的国科大开学典礼在这，白群礼院长在开学典礼上就宣布，这个我们中国的第一颗空间引力波探测的实验卫星啊发射成功。那么因为中国科学院大学是科学应用系统单位，所以这颗卫星是应该是给科学院大学做的啊。 好，这个过程中大家看到啊，这花了1年的时间，就这个从立项到这个建设，在科院的卫星史上大概从来没有过。它要求这个技术难度大，那么从来没有做过。那么空间引力波探测跟其他的卫星都是不一样的。这个卫星不光是个平台，卫星本身要将来作为一个载荷的一部分，要保证这个无拖曳控制，是吧？还有激光干涉，这样的精度，然后时间短，看这任务重等等。就当时参加的平均年龄大概只有不到35岁，都是年轻的，所以很多他们这个30晚上都没过，这个全年参与。那么这颗卫星这个发射成功以后，这个卫星大概180公里，这个离开地球地面大概600公里的高度。那么这个卫星呢主要是验证一个可行性，这个方案的可行性，还有一些关键技术这个测试，刚才讲的激光干涉啦，这个无拖曳控制啦等等这些。看，那么我简单介绍几个数据啊，这一个就是我们测量的这个激光干涉的精度，那么大概是100个皮米，那么最好的在高频段我们达到25个皮米。100个皮米的概念大家知道，就是这个氢原子大小 ，OK。那么25皮米比氢原子大小还要小，这个测量的一个精度。那么加速度噪声，我们达到了10^-10次方每秒米，就直接观测的这个噪声啊。那么这是一个什么概念呢？这个加速度噪声就是说，这颗卫星180公斤，假如一颗蚂蚁推一下这颗卫星，产生这个力啊，推一下这个卫星产生加速，你要把它测出来，有这么高的精度。那么还有就是我们刚才讲的这个推力，刚才说的你要这个测量这个加速度噪声，你还要测量这个推力，你要保证无拖曳控制，要把控制的相当于做这个所有的力要抵消掉，最后让相当于在做惯性运动，所以你要把这个推力控制得很好。那推力达到了0.115左右的这个微扭，这个概念什么概念呢？就是这个重量就相当于你把一颗芝麻把它分成10万份，每一份的重量就相当于这个微扭量级，是吧？0.1微扭量级。那么在无拖曳控制整个这个卫星的话呢，达到了加速度的剩余加速度达到是这个负8次方。那么这个原则上是直接测量在这个空间轨道上能达到的一个精度。当然你可以把它标定，把它延伸，是吧？这个。那么这个工作呢，我们发表在Communication Physics 上面。这个另外呢，我们还有一个更长的一个工作，就是有一本这个捐介，在国际International Modern Physics 上面。那么这个直接到我们大概有20几篇文章，我们参与的单位，这个参与的人员大概超过这个200来个，参与的单位大概是有30来个研究所。是，这个就是基本的太极1的型号。那么太极2的话呢，那么这颗卫星的话呢，空间2019年发射以后，我们实际寿命是1年，实际上运行了差不多3年。看，好，这之后的话呢，我们就准备太极2号了，就是2022年那个卫星太月了。实际上我们已经进入这个，我在说太极1号发射以后，我们就进入太极2号了。那么太极2号包括太极3号的这个关键技术攻关和一些指标在地面上的一些攻关。那么太极2号呢，原则上我们是准备是2颗卫星，2颗卫星的话呢，要测量这个激光干涉。这原来你在一颗卫星内部的话，这干涉距离还太短，那么是要2颗卫星来测量这个激光干涉，还有测量它这个无拖曳控制。你看。大家看到就是太极2号、太极3号的话呢，原来这个太极2号原来有2个计划，是吧？你可以在地球轨道来验证，但是最好是要达到我们的指标是要太阳轨道上面。那么 这个具体的我想不去讲了，就是在地面上验证的所有的这个有效载荷的这部分，这个大家看了，这是在杭州高等研究院的，是吧？我们这个有理论物理研究所和我们这个 ICTP-AP 共同承办的一个基础物理跟数学科学学院，那里边有个太极实验室，这个太极引力波宇宙太极实验室。那么这当然我们是在北京，在中国科学大学，但是我们在杭州有一个，也是一个这个分中心，相当于一个。有这个太极实验室在那里，这好多这个阶层等等都在那里做。其他我们参与的单位，主要的单位包括力学所，是吧？包括这个上海机物物理所、长青光机所、上海光机所等等，这个跟载荷有效载荷有关的，前面有讲的，总共有30个那个单位。那么当然卫星的话，还有空间中心等等，上海小卫星，是吧？是。那么总的来说的话呢，就是说。太极2号我们需要在地面达到的指标，我们现在基本上都达到了，就是地面公宽这些指标。我还有多少时间
？10到15分钟。
OK， 对，我倒留点时间大家可以讨论。对，那么实际上的话呢，简单来讲这里边我刚才讲的这个激光干涉将来要8个皮米，8个皮米的概念，我刚才讲的100皮米是原子大小，8个皮米比原子大小还要小。那最终我们的这个太极计划太极3号10的负15次方每秒米的正余加速度经度，这个概念是什么概念呢？就是我们在座哪位同学，你去推一下那个喜马拉雅山，假如喜马拉雅山能动的话，你推一下，你这个力推一下，它产生的加速 ，OK， 你要把它测出来。这个，所以呢，在地面上很多，刚才我讲的，包括这个无推控制，特别是卫星的地面上，我们是真的是个模拟了，是吧？这个有时候是半物理方程，我们不可能达到空间环境的那些。尤其地面上这个重力加速的噪声，差不多地面上的极限是能达到10的负8次方左右就很不错了，通常也是10的负6次方，因为地球上面的一个噪声，这个震动啊等等这个影响，哪怕你潮汐，所以这个就非常之敏感。上次我们在航高院他们测的话，哪里发生地震以后，它就可以检测到这个地震波的这个信号，都能测出来的。所以呢，我们希望在锦屏地下实验室暗物质探测的那里边，将来可能会做一些这个方面的测试。当然，这边力学所这边他们有一个小的10米的三角形，他们也在做一些模拟的测量等等。这里边我想总的来讲，就是所有的技术和工程都是达到现在我们的极限。那么现在的话，太极2号的话，你按照成熟度，他们评估的话呢，按照小卫星给我们评估的话呢，应该达到了5级的成熟度。那就意味着原则上可以进行工程立项，是吧？我想这个就是具体的一些技术，大家看一下哈。这个还有这个卫星，我刚才讲的卫星啊，通常我们现在好多卫星在天上都是个平台，其他在卫星里边做实验。在这个卫星将来的3颗卫星啊，它要求里边的这个测试质量做无拖曳控，做这个相当惯性运动，所以它要创造一个条件，使得它是这个我们叫做这个无拖曳控制的条件。那么卫星，假如它要偏离这个卫星，受到某种干扰以后偏离卫星，那我们要调整这个卫星，使得这个测试质量在卫星里边要做这个惯性运动，相当于。同时还要求卫星上面，因为这个我刚才讲的这个很灵敏，所有的磁和电，剩余的磁和电的效应都要消除掉，还要求所有它的温度要保证在很低，这个温度的灵敏度调节要很低，要达到这个100个 μK 或者就是0.1个毫 K。这些我想都是在卫星也是。然后刚才讲这个卫星在空当中的话呢，它自身要做一个有效载荷来调节变成无拖曳这个运动状态。还有这个 300万公里，到天上去的300万公里，这个激光干涉是个弱光的一个激光干涉，这里边有所向、所频，还有这个将来就是根苗，就是到了天上以后，你要保证3颗卫星之间是关联的，激光干涉，你怎么让这个卫星要看到另外2颗卫星，要对准的，等等，这里边都是很多的挑战。这个我想已经做了很多的这个，将来还有技术，刚才讲的，这个是计算的难度，将来真正要探测引力波的时候，还有很多难度。除了刚才讲的，我们在做黑洞的等等，这理论很简单啊，黑洞我知道是并合以后产生引力波。那么你如在地面上的话呢，这个引力波的信号比较少，它的困难是如何增加引力波信号。然后在天上的话呢，你发现空间引力波探测时信号多得不得了 ，OK， 然后你的关键的问题要区分开来这些信号，是白矮星是吧产生的，还是中子星产生的，还是这个黑洞产生的？黑洞有大质量黑洞、小质量黑洞等等，那个信号位是很多。那么你怎么样提取我们所需要的，针对我们要研究的那个黑洞并合的那个信号？那么这里边是要从大量的噪声当中把信号都取出来，然后还区分不同引力波信号。那么这里边就是要求我们的这个 simulation 这个模拟是吧？放针，还有模板波源这个模板的匹配等等，就一大堆的研究，包括数据处理。所以这部分的话呢，这个我想前面科技部启动了这个重点研发计划，科院启动了这个先导项目，这个我们都得到一些支持，在所有的方面呢，都展开了这个攻关，是吧？这个是刚才讲的这个数据处理方面的啊。那么骨科呢承担的是这个科学应用系统，将来在这个数据分析等等啊，还有这个处理这个噪声里边有一个叫做 TDI 的这个时间延迟这个方法等等。OK， 到目前为止，刚才讲的我们太极2号基本上结束了。当然，在香山会议上，我们讨论我们的太极2号的时候，这个是 Lisa Pazfan 的首席，这个将 Lisa 的这个首席，他是这个意大利的多伦多的，这个是马普所的13研究所的这个单子嘛，这个费塔里他们当时建议，他说你们是不是不要做2颗星的，直接就发展3颗星的？从他们的经验来说，他说他们原来这个太极Lisa Pazfan 的。在技术上遇到一个小问题，他们延迟了5年，是吧？然后呢，他说他们可以提供给我们一些经验，是吧？那我们是不是直接这个发射这个3颗卫星去探测引力波？那后来确实是科院我们的领导最后提出来，我们是不是不走这个2颗星的路，我们直接就是3颗星，即使是这个小的，是吧？小3星的3颗星，能够直接探测到引力波，这是后来是我们这个太极计划的一个目标，是吧？这个，我想这个从科学界来说也是这样，希望我们能够早日看到引力波，是吧？然后相互之间合作，是吧？这个，当然现在我们知道 ，NASA 参加以后，我们空间科学我们不可能是官方来合作了，是吧？所以我们是科学家之间，我说作为基础研究，我们总是可以讨论啊，这个合作交流啊，这些总是可以的。那么太极3号刚才讲的将来的目标，我们这几大目标，一个就是关于超大质量黑洞的并合，是吧？那么还有这个一个大质量、超大质量、一个小质量黑洞的是绕卷过程，那么对应的科学目标是吧？不同的这个波源对应不同的科学目标，还有呢，在我们银河系里边的一些几枚星系之间的并合产生的引力波。那么当然大家可能今天讨论很多的关于这个背景引力波的包括宇宙旋的等等的，是早期宇宙的，是吧？跟我们的粒子物理其他有关系的这个波源。那么当然还有一些波源可能我们不知道的，是吧？一些需要研究的一些波源。那么包括将来还要跟暗物质、暗能量可以连起来的，空间引力波探测连起来的，这些是相关的一些科学目标。那么计划刚才讲的，我们是3步走啊，那是太极1号成功发射，太极2号刚才讲的，我们已经关键技术攻关都完成。 那么我们等着这个列项，那么再后就是太极这个3号。OK， 我们希望当然一个是我想空间引力波探测刚刚开始啊，我们希望当然越多越好。那么假如是 Lisa 有，我们太极有是吧？跟后面我是不是要提到啊？刚才讲的。好，联网，这个联网的好处，刚才我讲的LIGO 跟 Vigo 等等，他们联网，将来还有这个Kagra 等等，联网的好处是可以很快知道波源 ，OK， 因为你在不同的位置的话，那么信息在同一个波源以后，在不同的位置测到以后，我们可以来定位这个波源。那么空间引力波探测原则上它本身也有一个好处，自己可以定位，因为它不是固定的，它本身在动，它自己可以定位。它假如两组卫星都在天上的话呢，在一起再联网的话呢，那可以更快、更精确的来定位，是吧？可以提个好几个量级。这个，他们这个郭忠官他们也领导的小组他们做了，可以提个好几个量级，是吧？这个，这个是刚才我讲的关键技术里边有的啊，这个是关于联网的。那么假如我们将来还有天琴，那么他们也讨论过啊，不管天津还是太极研究组，它在地球轨道，我们太阳轨道，两个联网也可以联网，联网以后也可以这个来做一些更加有趣丰富的这个物理啊，这个另外当然就是刚才联网以后测量以后，在波源定位好了以后，在我们将来研究宇宙这个膨胀、这个哈勃常数等等，这些都有好处啊，这里边也专门有研究过。可以把哈勃常数的精度提高得更好，甚至不确定小于0.5啊等等，这些我想都是将来的这个空间引力波探测。我们希望即使 Lisa 有、太极有、天津有，还不够多，我想将来还有的话，当然还更好。有的可能涉及再下一代的空间引力波探测，甚至可能不在地球轨道，其他这个轨道都是可以的。好，这个我想刚才前面已经讲过了。这个我们留点时间，是不是还有问题？也许时间也差不多到了。
我们感谢吴老师给我们的。关于吴老师理论的这个工作和引力波探测，我也同学还有什么问题？
吴老师你好，就是目前那个广相不是预言引力波，它有2种极化模式嘛？然后一些其他理论可能有4种甚至6种。然后我想知道目前我们的这个引力波探测是否能区分出来这种不同的极化方式，极化模型，以及这个太极计划未来它探测的时候能否区分这种不同的这种极化模式呢？
对你这个好问题，我刚才讲的我的引力量场论里边，我们现在是有5种极化模式。2种就是张量的，是吧？在爱因斯坦广义相对论里边的，还有2种是矢量的，还有1种是标量的。更一般的里边，他们讨论过，就是在广义相对论里边，他们讨论一般的啊，它可以有6种，因为我们在广义相对论里边有个坐标不变性，所以你10个多利变量里边，你 fix 开去以后，这个广义坐标不变性4个去掉以后，通常情况之下你有6个。但在爱因斯坦广义相对论里边，它还有一个 diffeomorphism 不变性 ，OK， 这个不变性又去掉4个，所以在爱因斯坦广义相对论里边呢，它只有2个。那么在引力量场论里边呢，我们发现呢，它这个广义坐标不变性还是有，你去掉4个，剩下6个。6个里边呢，发现还有一个，但是它没有 diffeomorphism 不变性，但它有一个某种意义上有一种 scaling 的另外一种单个这个不变性。这个变性去掉一个自由度，所以它剩下5个。5个的话，2个就是张量的，有2个是矢量的，一个标量的。那么，但是呢，一般的广义相对论里边有一般的讨论是6个。这个6个的话呢，它这个极化的模式也都有。但是呢，这个呢就是超出了广义相对论或者甚至你更高级的这个修正等等啊。但是在我们的里边，这个模式是比较确定的。2种模式是张量性质的。2种模式是矢量型的，这个矢量型的2种模式是跟自旋有关系的 ，OK。 然后呢，还有一个是标量的，跟自旋有关系的。像假如你要探测是空间的变化，完全是坐标空间的这种变化的话，在我们那里边是等于0的，是没有的。你如果你发现，就是你虽然可以把极化模式广义的把它写下来啊，这个6种模式，但是在我们的理论里边，那2种模式跟自旋有关的2种模式，在太极的测量或者是 LISA 的测量里边是测不出来的，因为我们用的是测试质量，都是用质量测试质量的宏观的还是测试质量来描述它变化，但是标量模式是可以测出来的。矢量形式一定是跟内禀的、跟自旋有关的过程才能测出来，也就是将来可能是在我们的冷原子啊，还有我们这个引力波产生的时候，它本身跟自旋有关系，它不光是绕卷，还有一种进动，是吧？其他的跟反映自旋信息的那个东西，那是可以测的。所以这个跟普通的你是广义相对论的其他的修整的模型是不一样的地方。回答你的问题了吗？
还有其他问题吗？
就是一个拿 if 的问题。太极的话，您刚才讲到是在那个太阳轨道上面，对吧？天琴的话是在地球轨道上面。我想知道这2个探测，它的这个不同的轨道到底对它探测有什么样的影响
？OK， 我想地球轨道、太阳轨道呢，是早在 LISA 他们以前都是都研究过的。那么它也各有好处啊，各有这个优缺点。这最终，比如包括 LISA 选择太阳轨道，最重要的一个原因是这个有一个就是一个是要避开地球、月亮的这个影响，还有一个最重要的因素是这个热效应。我刚才讲的这个要求，这个引力波探测要求是在温控要达到100万分之一。OK， 那地球轨道它有白天和黑夜，这2个温差就很大，甚至它可能会影响你的仪器。因为温度变化了以后，在你的仪器的精度会造成影响，所以然后呢，你一定是有一段时间段是不能测量的，只有有限的时间来测量。在太阳轨道的话呢，他们算了，在这个黄道面60度的时候，这个你可以让这个探测仪永远面向这个太阳，所以它的温度是相对来说是稳定的，是啊，这个是一个很重要的。当然，太阳轨道离我们远，是吧？你要通讯啦等等，是吧？发射了要花个时间。那么地球轨道比较近一点，这地球轨道也必须高轨啊，不是低轨道啊，一样，大概是这样子。
好的，谢谢老师。
好，谢谢。那个老师想请问一下，当时太极就是决定把这个臂长设置为300万公里的原因是什么？因为看太极的这个不仅臂长更长，而且一些噪声的指标也更大。就是说，当时选定这么个参数是出于什么考虑？
不，原来是LISA原来是500万公里 ，OK。当然我们知道距离越长越好，因为你最后测量的灵敏度是 delta R 比上 L， 所以你 L 越长，那么 delta R 固定的时候，你这个灵敏度越高。那假如说你测量的精度这个 delta R 改变，你能测量的包括激光干涉皮米亮线，你只能到比如多少个皮米 ，delta R 固定了。那么你这个 L 越长，那么灵敏度越高。当然还有一个就是你长度固定了以后，那就要求你假如长度做短了，就要你这个 delta R 变小 ，delta R 变小就对你的技术要求很高。你比如说你要短了以后，你可能要求1个皮米，我们现在太极是8个皮米左右就可以的，满足300万公里。那你要说只有这个100万公里或者10万公里，你接着要把这个 delta R 要这个灵敏度提高。那你要变成1个皮米，比如说你这个假如这个臂上相差1个亮节，你delta激光干涉精度要提高1个亮节，那技术就很难。所以当时我们跟着科学目标，我们满足科学目标和满足我们技术的话呢，我们选300万公里。所以这样子我们8个皮米，我们现在的实验室这个激光干涉方面，像那时候他们已经达到皮米2节，所以应该是满足的。看，所以你刚才当时说中国起步晚。那个技术，那个我们为什么赶300万公里，是吧？当然 LISA 再找500万公里，它要求的精度更高，10个皮米或者以上就可以了。那么但是的话呢，我刚才讲的就是太长了以后，还有一个激光干涉弱光，在功率损耗以后，你那边接收不到了，还有一个问题，你望远镜要做的大等等。所以最终我们优化了以后，发现300万公里 要求我们的灵敏度范围之内，这是比较优化的一个距离。
好的，谢谢老师。
还有别的问题吗？可能时间关系，我们再问最后一个问题。
陈老师有个问题好像
啊，那你
没关系，多一个他好。
我就想问一下你们那个，因为你们那个探测嘛，它跟那个波源有关系，所以你们需要有一些理论的模板。就说你们的，比如像 Emory 啊或者这些，你们现在谁在负责这些模板的那个
？OK， 好，
这方面的讨论。
我们现在这个科技部是重点专项里边有一个重点专项是关于理论研究的，是理论所在牵头，还有关于一个模板的，是这个国科大杭高院在牵头，这个跟北师大那个叫潮州界啊，还有韩文标啊、Emory 等等，他们在牵头，所以这个他们还是比较强的，应该说国内是最强的一个他们的一个小组在做。
行，那由于时间关系，那我们再次感谢吴老师给我们2堂精彩的报告。大家有问题可以在私下里再找吴老师讨论。好，那我们稍微休息几分钟，我们准备下一个陈老师的课。
好，我这个就没有了，对，好了，正好。
好，感谢吴老师。
好，
那个话筒。好，谢谢。 The second lecture this morning is given by Professor Bing Chen, and he's going to continue the discussion of ADS-CFD correspondence. Let's welcome him.
So good morning, everyone. So let me continue yesterday's talk. So yesterday I stopped at the margin limit of Young-Mills, and so we say that even in 1970s, Ter Hooft proposed that the margin limit of Young-Mills is actually a string theory, and so you say it's at that time. What Ter Hooft considered is just a pure Young-Mills, so no supersymmetry and no conformal symmetry. So we know that Young-Mills theory classically it's conformal scale invariant, but quantum mechanically, so we know that the coupling constant is rounding, and so quantum mechanically, pure Young-Mills is not scale invariant, but so. Okay, let me skip this slide. And if we but if we consider supersymmetry and we consider enough supersymmetry, for example, the most famous case when n equals 4, that means you have 4 copies of supersymmetry. Then the super Young-Mills in this case is conformal invariant. And this has been proved perturbatively and also non-perturbatively by using some topological twist trick. And so now, if we assume that the theory we considered is scale invariant, and it has some, as I mentioned yesterday, its gravitational dual could be in a higher dimension. So, for example, you have an extra dimension Z. And so the question is that what kind of geometry it should be. And so since the field theory is scale invariant, so that has some scaling transformation like x mu to lambda x mu. And if you consider the extra dimension has the same scaling behavior, that means it's isometric scaling. Then and require that the matrix is invariant under this kind of scaling transformation, then you will say that this function Wz should be L over Z. L is a constant, a kind of parameter. Then this metric, this 9 element, can be written in this way. And what's this? It's actually the metric of the 5-dimensional anti-de Sitter space-time in a spatial coordinate, the so-called Poincare coordinate. So it's ADS. So you say that if you have a scaling symmetry and the holographic dual should live in an anti-de Sitter space-time in 5 dimensions. So this is a very simple argument. And furthermore, if you are not only scaling symmetry, you have some other, you have some spatial conformal symmetry. So we know that there are some general conclusion. For example, the conformal field theory in n dimension, it could be conformal invariant quantum mechanically, and okay, I'm sorry, and okay, and its scaling invariant in many cases implies that the theory also conformal invariant if you require the field theory has non-symmetry and unitarity. And this has been proved in 2 dimensions by Poczynski, and also in 4 dimensions by Zohar's group, and also so you have some. If you have extra conformal invariance, then you will say that if your field theory in n dimensions is conformal invariant, it has a conformal symmetry group. It's SO2n, and SO2n is exactly the symmetry group of ADS n+1. So this is some kind of consistent check that if you have a field theory, it's conformal invariant, its holographic dual should be a gravity in ADS. And then there's some extra dimension. As I mentioned yesterday, you have some compact manifold, then the field content of this conformal field theory is closely related to the compact manifold. So for instance, if it's S5, then it's just a pure N=4 super-Young-Mills. But you have some other conformal field theory with N=2, then the compact manifold could be different. And so that's all. And you have some other ingredient. So that's just what I have mentioned is a general conclusion. But we know that we expect that the no-energy effective action of a superstring theory is Einstein gravity, Einstein supergravity. And that means no-energy effective action means that the ADS radius should be it's very much greater than the Planck scale. And then you have some more. You can consider some more interesting question that you have you can put in a large black hole in the back, and that require you have a large number of field. And that means you should take in the field theory side to have a large number of field, you have to take this margin limit. So that is from another point of view to say why we should take this margin limit. And also you have strong coupling. And this is because that the graviton, it behaves like a bound state rather than simply a pair of gauge boson. And this suggests that we should have a strong duality. So on the field theory side, it's just a gauge boson, a pair gauge boson. But on the gravity side, you have a bound state of a graviton. So that is in a strong coupling. So this is some intuitive understanding. And also, we in this ADS5 super-Young-Mills 4 case, one has supersymmetry. This is for stability. So that means on the so with supersymmetry we have various good properties. Next, you have better UV behavior, and also on the gravity side, in most cases, the configuration could be stable. So that is some technical requirement. Okay. So let me turn to another very good, a very wonderful idea in string theory. That's called the open closed string duality. So this is this duality, from my point of view, it's still not very well understood. It's a quite intriguing relation. So this is, I think, a few days ago, you have Professor Lu should have introduced this diagram to you, and in the study of the deep brain. So if you consider two deep brain the same dimension, it's a BPS case, and then you can consider the interaction between two DP brains. Then you have two different perspectives to look at the interaction between two deep brains. One is the open string point of view. So you say that the open string ending at the DP brain. And so this diagram is a cylinder. But from open string point of view, you say it's a one loop. So it's a one loop effect from open string point of view. But you can also take the deep brain as a non-productive object in string theory. In that case, it's some coherent state, and the two deep brain they exchange the closed string mode. So you have that closed string and at the train level of propagating between two DP brain. So you have two different point of view to look at this system, and this is a kind of open closed string relation, and these two kind of perspectives suggest that the open string can form a closed string, and the closed string can leave the deep brain into the extra dimension. Okay, so that's the some intuitive picture. Okay, so so we say you have NDP brain wrapped on each other, and we say that the deep brain, this is deep brain, and you have the open string ending on the DP brain. But the open string, the endpoint can tie together to form a closed string. Then the closed string can leave the DP brain into the back. And so that's the basic picture of why have this ADS safety correspondence. Since this DP brain is a quite heavy object, so and it can backreact to your background and the curved background, so to make it into an ADS space-time. And so that's why closed string lived in an ADS space-time. But DP brain itself, it can be described by the super young layers. So okay, so I think I should introduce in this slide, and so that's I think Professor Lu should introduce to you. And DP brain is an extended object, and with a p+1 dimensional world volume. So it's a one-time direction, and p is the spatial direction. And from open string point of view, it can be described by the open string with Newman boundary condition along the world volume direction, and deleted boundary condition in transverse directions. So that's the open string point of view. Then you can quantize the open string with such kind of boundary condition. And if you consider the no energy effect and the massless excitation, you will see that you have some gauge field along the world volume, and also some massless scalar in the transverse direction. For example, for a D3 brain case in type 2B superstring, you have the massless bosonic excitation A mu and phi I. So A mu is along the world volume, so from 0 to 3, and phi I is the transverse scalar excitation, so from 1 to 6, and and then the no energy effective action of this D3 brain is described by anchor 4 and UN super young layers. And this theory is maximally supersymmetric and also conformal invariant. And usually people discuss SUN, not UN. The reason is that this among this UN you can factorize to SUN cross U1. And the U1 is the position of this D3 brain. It can be anywhere in your space-time. So that U1 is not important. And so one can factorize that U1 sector. Okay, and then we look at this system from closed string point of view. And in closed string, this DP brain could be taken as some coherent state of closed string. So you have various closed string excitation, and the D brain is a non-productive object, so it's a coherent state. And in the no energy limit, then it appeared as a non-productive Soliton solution, and in supergravity. So with some Raman charge. Okay, it's some quite technical stuff, but it's quite important. And this is the metric and also the flux for this D3 brain in type 2B supergravity. And F is a harmonic function, and star is a Hodge dual. So you see that the 5-form field strength flux is self-dual. So it's 1 plus Hodge dual itself. So it's self-dual itself. And one can say that this DP brain, D3 brain, it carries Raman charge. It's N, so here it's N. So N is the charge of the Raman charge. Also, that indicates the how many D3 brain you are considered. So you have N D3 brain. That means you have Raman charge N. And this solution is not a singular solution. So it has it's not like the black hole. You have a singularity as the origin. So this Soliton solution is not singular. And the horizon, compared to the, so it's somehow it's a misnomer. Since the horizon now is at r equal to 0, and then one can consider the near horizon limit. Change R tends to 0, and somehow you just zoom in the near horizon geometry and what to see what you get. And so if you do that, take this limit, took this near horizon limit, you will see a different geometry. Now the geometry behaves like this way. So now it's we introduced another coordinate, so to compare with the ADS5 geometry in point-guide coordinate. So we change this the coordinate R into Z equal to L square over R. So L is the radius of ADS and also the ADS of S5 sphere. And now if you take this near horizon limit, you get this kind of metric. So this part is ADS5, and exactly the same as the one from the discussing before. And this part is the S5. It's a 5-dimensional sphere. And both pieces, we know that ADS5 and S5, both of them are maximally symmetric space. And both of them have radius L. And now, okay, also a very subtle issue is so-called the decoupling limit. One has to consider the decoupling limit. That means you have a dp brane originally. You have a dp brane in a flat space-time. But now we zoom in the near horizon, you will get this kind of geometry. So after you take this so-called decoupling limit, that means the near horizon region gets decoupled from the asymptotically flat region. And this near horizon region, to study the physics around near horizon region, have two different descriptions. One is the gravity in ADS5 cos S5. So another description is by some NCO4 massless NCO4 super young mirrors, and including the various massless open string excitation on the brane. So, and you will see that the asymptotical flat region decoupled completely. So you only what leaves just the gravity as ADS5 cos S5, and also another descriptions NCO4 super young mirrors. So this leads, I think this led Juan Madacena to suggest some kind of equivalence between the supergravity on ADS5 cos S5 and NCO4 super young mirrors. So so now I'll give you the really precise version of ADS5 super young mirrors for correspondence. So the precisely this correspondence tells us on the supergravity side, on the quantum gravity side, we have this type 2b superstring on ADS5 cos S5, and with radius L and string coupling GS and n units of the 5-form Raman flux. So this is the string side, and on the field field side, we have this NCO4 super young mirrors in 4 dimensions, and with gauge group UN or SU1, and coupling G young mirrors at large n. And so we see that there's some parameter in string side and also in the field side. And these parameters are related to each other, and by studying the decoupling limit. And one will say that the Young-Mills coupling related to the string coupling. So it's G Young-Mills square equal to 4 pi string coupling GS. And the ADS radius and related to the, so it's proportional to the number of the deep brane. So you have more deep brane, that means you curve the space-time more strongly. So that it's more precisely you have this kind of relation. So you have this the radius L4, and the right-hand side is 4 pi GS, and this is string scale. You have a string scale here will appear in the story, and we know that there's a Teuft coupling. Teuft coupling is G Young-Mills square times n. So here it's GMS square times n equal, so you get this 't Hooft coupling lambda, and times the string scale, the force of string scale. So you have this this relation, and then you study this correspondence. This is somehow it's a quite precise description, and but I have to say this correspondence, strictly speaking, is still a conjecture, since we don't know how to quantize the string theory in this spacetime due to the presence of this self-dual Raman-Raman flux. And so ADS5 cos-5 is a coset model. So somehow you have some world shear theory, and with target space as coset model, that's been well understood. But if you furthermore have this self-dual Raman-Raman flux, that make your study much more difficult. So we have no well-established framework to quantize the string in this case. So what we can do is to consider the no energy limit and or some special limit, and to simplify the story. And also there's some strong version of this correspondence, also a weak version. The strongest version is that this correspondence could be true for arbitrary string coupling, and that means also the arbitrary n. So even n equal 2, yeah, it's still true. It could be still true. But in that case, it's very difficult to study, since at the string side, that means you have a strongly interacting string theory. So the string theory in that case is a non-perturbative. You have the perturbative string is not enough. You have to consider the string field theory, etc. Okay, so what we can do, I think in most cases, the people study the classical limit, take this also the 't Hooft limit. So in that case, n should be very large. That means your string interaction is quite small. So in that case, you can reduce your theory. At the string side, it's a classical, free classical string. So on the other side, on the Yang-Mills side, this corresponds to the, since it's large n limit, that corresponds to the planar limit of super Yang-Mills. So even in this case, there are some study, for example, in the from integral or integrability to study this correspondence, one can study this classical limit, but we can even do more. And we, under this, not only classical limit, we take a further low energy limit. This leads to a weakest version of ADS correspondence. So in that case, in the low energy limit, that means we only consider the massless excitation of string theory. Then in the string side, that means it's not string. It's reduced to the supergravity. It's reduced to the type 2b supergravity, ADS5 coset 5. So on the field side, the same limit give you the n-4 super Yang-Mills, but now you have a strong coupling, so it's at a large lambda. So you see that it's a strong weak duality. So on the field side, you have a large. So since you take large n limit, the effective coupling now it's the 't Hooft coupling. So the 't Hooft coupling is the strong coupling. On the gravity side, you simply have a supergravity that is weakly coupled, and this so that's why we call this ADS-CFT correspondence. Usually, in most cases, it's called the gravity gauge correspondence. So the gravity is just a pure gravity, Einstein gravity with something else. And on the field side, it's just a Yang-Mills, a special kind of Yang-Mills. So a gauge theory. So it's called the gravity gauge correspondence in this sense. Okay. And one can do some very simple check and consistent check based on the symmetry. And so I have mentioned that this SO42, this is a conformal symmetry group in n-4. So it's the conformal group of n-4, and it corresponds to the asymmetry group of ADS5. And now you have another piece is S5. S5 asymmetry group is SO6. And for NCO4 super Young mirrors, it has some R symmetry. So the R symmetry means that you can rotate you have 4 pieces of supersymmetry. So you can rotate the 4 copies of supersymmetry. That is a group, give you a group of SU4. So SU4 is isomorphic to SO6. So this group also yet have very nice correspondence in on both sides. And you have some other symmetry, like the supersymmetry. Supersymmetry in the string side, you will see that this ADS5 cos S5 actually it's a maximally supersymmetric reduction. It's called fluid Rubin compactification in type 2b supergravity. It has a 32 supercharge. On the super Young mirror side, from supersymmetry, if you simply counting, it's 16 supercharge. But now you have the conformal symmetry. So this 16 supercharge get enhanced, also get enhanced to 32 supercharge. And so that is a simple check based on symmetry. So the final check is on the actually it's on the not the global symmetry. This is some on the dynamic. So we know that superstring type 2b superstring for D3 brane is self-dual. So you have a coupling constant tau. So this is a complexified coupling constant. So with string coupling and also another field axiom, and in string theory. And so this is a kind of related to the denotator, and this is related to the axiom. And this complexified coupling constant, it can be transformed by SO to the transformation. You will see that the theory is invariant under this kind of transformation. Then on the super Young mirror side, you will see that we also have a complexified Young mirrors coupling with Young mirrors coupling here, and also we have a theta vacuum. So we have a theta parameter here. Also formed a complexified Young mirrors coupling, and the theory is self-dual under the transformation of SO to the transformation on this Young mirrors coupling. Also is self-dual. So that is another consistent check. Okay, and furthermore, there are many more checks, and so here I just mentioned some of them. And for example, at the beginning of ADS-FT, that in the beginning error, and the people checked that the spectrum between two sides. On the super Young mirror side, one consider this chiral operator. It's BPS and its spectrum, and you can construct various kind of the operator, and it corresponds to the supergravity compactified, Kaluza-Klein compactified on S5, and you have a Kaluza-Klein spectrum, also a series of the states, and one can check that the scaling dimension of this chiral operator corresponds to the like the mass of the KK spectrum. Okay, so that is a first step check, and then one studies various kind of amplitude protected by the supersymmetry. So with supersymmetry, you can study the on the field theory side, it's strong coupling, but with supersymmetry, it's protected. So you can still do some predictive computation. So on the gravity side, it's weak coupling. So one can study this kind of amplitude protected by the supersymmetry. And furthermore, in general, one can study a partition function. So the partition function it's important. So on the back side, on the supergravity side, here the phi could be any kind of the field, and you study with this field with a boundary. So z equal to 0, it's asymptotic boundary. So now it's in Poincare coordinate. So at the boundary, it has a boundary value, phi 0. And then you consider the the partition function with this kind of field in ADS phi. On the field theory side, this phi 0 behaves like a source. So you have some kind of correspondence between the operator and here and the field on the back. So this phi 0 is a source term like J in I think in quantum field theory, and the O is some kind of perturbation. So with a source term, and on the safety side, one can expand to compute this kind of coordination function, and then to check in the back side what you get. For example, the most important one is when you consider the graviton in the back side, so it's G mu nu. And on the boundary side, you have this corresponding operator, it's the stress tensor. So, and actually, when you study some like QGP, like you study the nature of QGP. So on the field theory side, you want to use this linear response theory to compute the stress tensor, to read the, for example, eta over S, viscosity over the entropy density that encodes into the stress tensor, the 1-point function of the stress tensor. So in that case, on the gravity side, actually, what you compute is a perturbation of graviton perturbation perturbed a black hole in the center of the ADS phi. Then we will find that at the no energy limit, the cross section of the black hole will correspond to the eta over S. So that's why you get a very simple answer. Okay. And there's some other check next to consider a special limit, like the PP wave geometry. That means you have some null orbifold, you zoom in the null orbifold, then your space-time. In that case, not ADS5 cross F5, but a PP wave geometry. And in this case, the string theory is solvable. And one even can use this net cone quantum field theory, string field theory to study the string acting, string interacting. And on the Yang-Mills side, one can consider beyond the planar limit. So that's a very strong support of this ADS safety correspondence. So it's not only the planar limit. So what I mentioned before is simply supergravity and the super Yang-Mills. But in this case, since one can do quantization of string theory in PP wave geometry, one can even consider the string interaction in this case. So, so this is work by Madasena and Bernstein and Nastase in 2002. And furthermore, starting from the 2002, there's lots of work to study this correspondence based on the integral structure and the semi-classical string. And also there's other kind of check. So I think for ADS5 super Yang-Mills 4, we found no counterexample to this correspondence. So there are many evidence to support this correspondence, but we cannot say it has been proved. So as I emphasized before, we don't know how to quantize the string theory in ADS5 cross S5 with Raman on self-due Raman charge. And so perturbability we don't know, and non-perturbability it's even harder. Okay. Okay, let me see. Okay, so the ADS safety correspondence. So I think what I have told you, it's the message is that this ADS safety correspondence, at least for ADS5 super Yang-Mills 4, it's well established, and I think almost everyone believes that's true. And with this correspondence, so actually you can attack various kinds of questions in quantum gravity and also in quantum field theory. And so first, let me introduce its implication to quantum gravity. So it provides a new way to define string theory. So, and usually string theory, we define a string theory in a target space-time, then we have to try to quantize the string theory. But now in this case, even though we don't know how to quantize string theory, but we know it has a safety due. So in a sense, we use this conformal field theory at ADS boundary. We can't define a string theory in the back, even though we don't know how to deal with the string theory directly. And then one may study string theory by using super young years. And there's some various kind of study, like the tensionless string, and the higher spin gravity, and the string interaction in the PP wave case. And this has been checked. And also one may use this ADS-FT correspondence to investigate some long-standing problem in quantum gravity, like the information loss in black hole evaporation. I think you saw this diagram yesterday in Zoya's talk. And so we say that this is you form a black hole, this is the horizon, and this is the singularity. And we know Hawking radiation. It radiates a pair of particles, and one particle escaped to the infinity, now infinity, and another particle fall into the singularity. And this pair of the particle, they are entangled with each other. So when you compute, so there's various aspects of this information loss. One aspect is that the entanglement in the radiation. So you have some kind of the page curve. If you simply compute the entanglement in the radiation, you will see that in the net time of the radiation, the entanglement in the radiation is larger than the black hole entropy. So that means unitarity got lost. And that's one aspect. And this kind of information loss issue has been solved in the past few years by studying carefully what's the entanglement in the radiation. So using this quantum extremal surface and also the Island formula. So that's the development in the past few years. And so even there's some other aspect in information loss problem. And but ADS-FT correspondence simply tells you in principle, you don't need to worry about that. You don't need to worry about the information loss. Since from this correspondence, we know that a black hole in the back, it corresponds to a special state in the boundary safety. It corresponds to a thermal state in a boundary safety. So we know that in the super young years or more general, in a safety, its evolution is unitary. Anyway, the information it's still there, and so that means what happened in the back, you don't need to worry. The information should be somewhere. Maybe it's not easy to read them, but you don't need to worry about the information loss from this ADS-FT correspondence. So unitarity must be preserved due to the if you believe ADS-FT correspondence, and so there's some other issues. So how to use this correspondence to probe the physics behind the horizon, and the physics near the singularity. So that's what what people have been trying to do. That's an important question. And so classically, we know that when the matter falls into the horizon, it will fall into the singularity. But near the singularity, we know that at that scale, the quantum effect should be very important. That means if you have a quantum gravity theory, your singularity should be resolved in some way. And the people wish to use this ADS-FT correspondence to study the physics near the black hole singularity, also the physics near the cosmological singularity, if you have a well-defined correspondence. Okay, so that's the implication of ADS-FT correspondence to quantum gravity. So
another remarkable lesson from ADS-FT correspondence is that is so-called imagined space-time. That means the space-time itself could be not fundamental. So from the correspondence, we know that we have a boundary safety. Then we can from the boundary safety, we can emerge a space-time. And the space-time in this case is not a fundamental one. It could be oh, very good question. Yeah. Yeah, that's so what we can do now is emergent of a space direction. The people also think about that, but it's a very difficult question. If the time also can be an emergent notion. Yeah, we don't know. Yeah. That's yeah. And for space, it's related to this radial direction. It's related to the arc scale in the field theory side, and okay, that's fine. But for the time direction, it's we have no good idea in that case. Yeah. Okay, so then let me ask the question: what's the nature of gravity? So the gravity. So we have studied gravity for several centuries, but so from ADS-FT correspondence, it seems that what we know about gravity could just maybe it's an illusion. It's not a true fundamental subject in nature. Yeah. Okay, and on the other hand, since we have this strong weak duality in ADS safety correspondence, then it allows us to study various strong coupling issues in various field theory systems, ranging from the low energy QCD and superconductor, superfluid, non-fermion liquid to quantum phase transition. And this area has been developed very fast in the past 15 years and or even maybe 20 years. Originally, I think start from the KSS bound is somehow around 2005, and so that leads to a lot of work. So this now we even have some textbook on this so-called applied ADS-FT. And this is the study of the various problems in QCD, the low energy QCD, and this is for some quantum matter, and this by Sachdev and his collaborator. And this one is by Liu Yan, Sun Yawen, and postdoc supervisor Zanon and Xiao. And there's another textbook using this holographic duality to study the various problems in condensed matter physics. So if you are interested, you can look at that. Okay, and so finally, what I say before, it's we use this ADS-FT to study the condensed matter problem. In the past few years, there are very interesting development. It's to the people working on condensed matter physics, they propose a duality. They propose ADS2 duality. So this is so-called the SYK model. So this is Sachdev, Ye Jingwu. He's not here, but he will give talk tomorrow. And Kitaev. So I think it's in 2015. Kitaev in a talk, he proposed that this kind of model, this SYK model, could be due to a homographically due to a gravity in 2 dimensions. This is jetty gravity. So this is spent a few minutes to explain. This is SYK model. So SYK model itself, it's a quantum mechanics model. That's the only time, and one could consider a Majorana fermion in this case. And the Hamiltonian is quite simple. It's with a random coupling. So this J is a random coupling. You have a 4 fermion interaction. And this model is exactly solvable if you consider some special limit. And this is random coupling. That means it's itself. If you take the expectation value of yourself, it's simply 0. But it's J square. The expectation value of J square is not 0. It's just J square over n cubic. And n is the index of this I, so the number of the Majorana fermions. And then similar to the 't Hooft coupling, one have to consider this large n limit, and then you get some strong coupling system. But you see that in the large n limit and keep this this effective coupling to be fixed, one can solve this SYK model exactly. And the interesting part is that, and if you consider the IR effective action of this SYK model, you will find that this SYK model actually it's no energy. It's IR effective action. Actually, it's a kind of Liouville action. So this is the bracket F and T. It's the variable. It's Liouville bracket is defined in this way, and so this model, this correspondence ADS2 SYK has been first proposed by Kitaev in 2015, and in 2016, Matsuda and Stanford try to elaborate this Kitaev study, and that wrote a very nice note on this ADS2 SYK, and so this is on the SYK model itself. You will see that it's simply defined by this kind of action. So on the gravity side. On the gravity side, we know that if you have a pure 2-dimensional gravity, simply it's trivial. So we know that the 2-dimensional gravity is simply trivial. But once you, so one has to make it dynamical. You have to put something. So you have to put a dilaton, or simply put a scalar into the game. The scalar will induce the dynamics. And so that leads you so-called the jetty gravity. So the jetty gravity, it's a scalar non-minimally coupled with ADS2 gravity. So you get this jetty gravity. And you will see that this jetty gravity also, the information of this jetty gravity actually its dynamics is encoded by the behavior of the matrix near this ADS boundary, and then you will see that the dynamics of jetty gravity also since so you know it's 1 + 1 in ADS2, but its dynamics is reduced to the behavior at the ADS boundary. So also it's simplified to a 1-dimensional action, the same kind of action here, and the same effective action. So then one get a new correspondence between the jetty gravity and SYK model at the boundary. And then one may use the SYK model to study the physics of the black hole, the various kind of physics, quantum chaos, etc. Okay, so this is a very interesting development starting from 2015. So you see that it's out of our expectation. This correspondence first proposed not by string theory, not by an expert in gravity. It's proposed by an expert working on this quantum phase transition, on this stuff. And so that is somehow it's some kind of feedback from the expert in other area. Okay. So finally, let me give some general remarks on ADS safety correspondence. So as I emphasized before, even for this most well-known, most well-studied ADS5 super-Yang 4 correspondence, it's still a conjecture. The reason is that we don't know how to quantize the string theory in this space-time with this safety Raman background. The people propose various kind of the formulation. So we know that in string theory, we have this NSR formulation. Also, we have this screenshot formulation. And there's some other framework, the people in I think around the end of last century, people in a period wish to study this string theory in a new framework, so-called the pure spinner. It's somehow it's half screenshot, half NSR formulation. But finally, we say that it's not so successful. So perceptively, we don't know how to quantize the string theory in this background. And moreover, non-perceptively, then it's even harder. We don't perceptively we don't know. So non-perceptively, it's even harder. And we say that the ADS super-Yang 4, and originally its establishment heavily relies on string theory. The various kind of ring system, they have to take the decoupling limit carefully, and so it's and other string technology, and even in ADS safety, the gravity in ADS in anti-de theta. In this case, there are still many important questions remain unanswered. So holographic principle seems to be a quite general principle in quantum gravity. So that means the holography should be true not only in ADS, but also worked in other space-time, asymptotic flat space-time, asymptotic de theta space-time. And but even in ADS safety, many important questions remain unanswered. So like when this correspondence work and how it works. And for example, so what kind of the gravity ADS can have a holographic view? Or vice versa. So what kind of safety could have an ADS view? This kind of question, we have no good answers.
Things which are really not conformal, like the mass gap in QCD. So do people have hoped that it could help?
Pardon?
The mass gap question. Do people have hope that ADS CFT could help?
I don't think so. The people try to, for example, you have a mass gap, the people try to study the real QCD problem, for example, like the hydron, meson, and then the people try to introduce a kind of cutoff or some software in the ADS. Yeah, that's what people have been doing. Yeah, and to holographically to study the hydron and meson in that way. For the mass gap itself, yeah, I have no answer. Yeah, since you know this correspondence, it's set up, it's just for conformal field theory. Yeah. If you this theory like the pure Yang-Mills, what is holographic view? Like what Polyakov and then Polyakov try to understand. Yeah, still an open question. Yeah. So what's a holographic view for a pure Yang-Mills? Yeah.
So maybe or probably, I don't know how to say, it's not universal. And then the question is there something, for example, the Kitaev model, it has to do with experiment. I mean, is it related to experiment?
Huh?
The Kitaev thing that you were mentioning.
Yeah.
For example, you get ways to compute experimental things in both space.
On the JT gravity side, I don't know what's the experiment, but on the SYK model that has been applied to study this quantum phase transition, this stuff. It can be mapped, theoretically, I mean, okay, okay. Okay, so this I have mentioned before. So how to understand the holography beyond the ADS, like in flat space-time, in the theta space. This has been, I think, still under active research in the past 10 years. This kind of problem, and one clue is that we have to for a flat space-time or the theta space-time is very difficult to establish the correspondence from string theory. From string theory, since you will say that you have very severe restriction to use the string technology. So I think in most cases, one only can establish the ADS-FT correspondence. But for the asymptotic flight or the theta, as far as I know, there's no establishment from string theory, and so that requires us to understand this general holographic principle from other point of view. Like we use a different approach, different angle to investigate the holography. So yesterday I mentioned that this bottom-up approach to study the asymptotic symmetry group of gravity is one way. There's some other way, and for example, so this is using the quantum entanglement to study these kind of questions. So I think starting from the 2006, and Yu and Takagi they have a very wonderful discovery that they propose a very nice relation between the entanglement in the field theory side and some kind of minimal surface, area of minimal surface in the bulk. So that's the so-called the holographic entanglement entropy. And starting from the discovery, the people have been doing various kind of investigation. Since this formula shows that, okay, let me I should explain more carefully. And so what they have done is that they study the entanglement in a conformal field series, in a conformal field theory. If this conformal theory has a holographic view, they propose that the entanglement between A and B, the entanglement entropy, could be computed by the area of a minimal surface, gamma A. This gamma A is ending at the boundary, at the same boundary A, as the asymptotic boundary. So it's very similar to a black hole. The first page in my talk, it's very similar to the Perkinstein-Hawking entropy, and it has been shown by Madasena and Lukowitz that this kind of holographic entanglement entropy is actually a kind of the gravitational entropy. So that's why we need a lot of development in that side. And so more generally, the people expect that the quantum entanglement could play a fundamental role in the emergence of your space-time. So under this so-called RT formula, it's one example. So we study the entanglement on the field theory side, and minimal surface emerged from the study. So the people wish that by studying the quantum entanglement at the boundary, the dynamics, not only the geometry and minimal surface, even the dynamics of the Einstein gravity could also emerge from this picture. So there's a lot of studies along this line since 2006. And okay, so I think that's all. Oh,
just one more.
Yeah, it should be one more picture. I don't know.
Yeah, just go forward.
go forward?
Yeah.
Okay. Thank you.
Okay, we thank Professor Chen for the very pedagogical overview. Just because time limited, just one very short question. Maybe. Sorry, can you, because you're from local, you can ask Professor later.
Thanks for the next lecture. I have a question. Is there any research that studied the string field theory and the ADS safety correspondence? I hear something from Professor Sen Hu. He said that the string field theory can automatically imply the open-close string duality in string theory. So I'm wondering, is there any relation between the ADS safety correspondence and the string field theory?
Oh, okay. So it's a very good question. And so I mentioned in my talk, so when you study this PP wave geometry, is so let me see how to say. So PP wave geometry appeared in the study of ADS safety correspondence. So if one consider a kind of special orbit in ADS5, and when you zoom in that orbit, you will get this PP wave geometry. And string theory in PP wave geometry, one can quantize it adaptively. And even using this net quantization, one can study the string field theory in this context. So what I want to say is that one can apply the string field theory in this case, even though it's in the PP wave geometry. PP wave geometry is also it's a part of the ADS safety correspondence. And on the Yang-Mills theory side, you have the some operator, some non-chain operator, a very huge global charge. And then there's some correspondence between the string theory in PP wave geometry, its excitation, the string excitation, and the operator in the Yang-Mills side. And when you consider the interaction of string interaction using the net constraint field theory side in PP wave geometry, on the Yang-Mills side, you can study the non-planar diagram. So the planar is free string, but the string interaction with a non-zero string action, then that means you have to study the non-planar limit of super Yang-Mills. So that almost 20 years ago, that's in active research. Yeah. Okay. So it gives a very non-trivial support of this correspondence.
Okay, thank you.
Okay. Again, because time limit, for more questions, please ask Professor Chen in private. Let's thank Professor Chen for the 2 great lectures again.
Okay, thank you.
Okay, let's take another few-minute break. We prepare for the next lecture. Okay. 多谢陈老师。
我可能一会儿就走了，因为我下午还有一个要赶回中国学院，好吧？好。
So， 因为陈老师马上就下午要离开，如果有问题赶紧问。
哦，对，好吧，我想问一下，就是现在这种 ADS-CFT， 它不是认为都是那种 decoupling 这种 limit 但就是您认为有可能就是比如说我们在 ADS 上加一些量子的这种修正，然后把一些本来可能有的量子效应加回去，然后这个可能calculate还是成立的。它这里面它已经可以考虑各种各样量子修正，原则上是。你尽管你看我们现在讨论你看我就说它有好几个层数，你最简单的大家都其实大家能够做，因为大家对 supergravity 那就考虑简单的gravity。但是 gravity 这边呢，你可以看到它也有一些考虑一些，因为你看你 pure gravity 它肯定就不只是这个，你看它有一些，比如像刚刚提到的。
Hi Leo, can you hear me?
半径的学用可计系统来考虑。
Leo, can you hear me? So, okay. So we just finished the last lecture. So we are taking a little break. Okay. We take a little break and then we can continue. We can start your lecture in a few minutes.
All right.
这方面不是很清楚，我简单一点，就是我看着大家都在提那个应用这一块的 CS，就是我比较困惑，因为我之前觉得那个QC 它真的它那个正义到底是不是对应到真实世界物理？打响。
他这个问题很好的问题，其实他有的时候呢，你看他们讨论的是，如果你想真正的来，因为他你看感觉怎么做，就是一个什么样的。有的问题呢，他说他们的一个argument，因为两个会讨论这个是不是ACD 啊，然后跟我们真实的 QCD 差不多，对的。那这样的话，你为什么可能有些东西看起来还比较这样这些问题，他们的 argument 就是说，他可能是一个universal class。就是每次都是一个普通的角色，它是同一个普世的，因为同一个普世内容呢，在当前但是呢，如果你想做的更精细，比如说要去做一些强行介入，那个基本上它尽管有一些，他们有很多构造，还构造接近于真实KGD，它也是没有很强的重视，这次他甚至说他把这些就算到但这个呢，我觉得呢，其实要小心，因为我觉得你看，这样做跟那个很像。然后学麦子，非常麦子要小心，更有知识，对吧？那你这边也会发现，那个是吗？难为情，对，因为这里面，那你看，实际上1800万，跨个有没有成长？1800万还有，你真的会有一项，
那次是它的一个不是那种意义上的那些，
它有些对有的粗糙的成绩，对那个他们超五啊，他们游戏啊，游戏在某个阶段，好，有问题是，就是
可以就是实现一个，比如说他们在云态上表面有一个物质表面上可以实现一个特定的一个 CLT， 然后那这个时候是不是意味着它中间的这个爆炸就是某一个
不一定。所以刚才我最后提到温暗号的问题，你有一个是，你看我们知道很多是什么 ICTP， 对吧？什么 3或者什么很多 minimum 模型，那这些 minimum 模型，你看前面我刚才也提到了，一个 ABS 是需要一个 mass 的或者取一个伸缩价值大，但是呢，你看一个 ICTP 模型一个伸缩价值。是很小，对吧？然后你说他的一个队友，如果可能，他的肯定就是一个参与，但你知道，这是一个问题，但他到底是
我的意思就是我能找到一个这个已知的这些比较确定的这种队友，能够在它的这个表面实现。
那比如你看，你现在大家能够做的也是一些波音，比方 SYP 嘛，那大家体上就是它可以在某些系统能够捕捉到这样的情况。
Hi Leo, can you please share your slides?
Sure.
We're gonna start soon.
Just 1 second.
Yes, we can see it. Shall we start? Are you ready?
Yes.
Okay. Okay, let's get started. So the next lecture of this morning session is again given by Professor Panozayas. He's going to continue the discussion on black hole thermodynamics and quantum entropy corrections. Let's welcome him.
All right, thanks. So yeah, this is the second part. So let me remind you what we did last time. So last time we discussed black hole thermodynamics and Hawking radiation. Again, this was a little bit more on the pedagogical side. So I expect that this is something you might have seen already in some advanced GR class. And the new sort of on the research level discussion was about logarithmic correction. So I discuss why they are important. I show you a computation that explains that they are very robust. You don't need to know the full UV complete theory of quantum gravity to reliably determine this correction. So they are, in that sense, they are a little bit like a, like a bag of gold. So if you have it, then you have something very powerful. And towards the end, I started explaining that there seems to be an issue, a puzzle, on how to apply the quantum entropy formula of a shock send. So I did two computations. They don't agree among themselves. Only one of them agrees with the field theory side. So that's where I think I left. So what I want to do today, of course, is to continue, finish this part, the part in blue here, to try to argue to the best of my ability where I think is the issue with this quantum entropy formula, and then start lecture 2 proper, where I promised yesterday to show you agreement with CFT. So I'll do the computation. I will sketch, of course. I cannot do many things due to time constraint, but I'll show you the ingredients. Then you can go to papers where these have been done in full detail and track it if you're interested. After that, I want to switch a little bit gears and talk about the same problem, the problem of logarithmic corrections, but in a context that perhaps is more familiar to you, the context of the prototypical example of ADS-CFT, where you have ADS-5 black holes on one side and the N=4 supersymmetric Young-Mills on the other. Then if I have time, this is again, if I have time, I will talk a little bit about some logarithmic corrections in temperature that are becoming quite prominent, and that I think would be nice. All right, so that's the overall outline. Here's a little bit more concrete. As I said, first, I'm going to talk about how to resolve this puzzle. Then I'll go to the topologically twisted index of ABJM theories. I remind you yesterday. I will remind you what these are, define them, etc. And after that, I want to switch to the superconformal index. So this is the partition function essentially that counts black hole states on the field theory side, and then how we can reproduce logarithmic corrections using Kerr-CFT. After that, again, as I said, if I have time, I will tell you a little bit more about this sort of new direction where it's again quantum corrections, but they are not logarithmic in entropy. They are logarithmic in temperature, where Hawking temperature here. All right, so this was sort of my last slide last time. I have shown you the computation when the computation where we have ADS4, the Reiner-Nostrom ADS4 black hole times S7. And here we're going to the near horizon. So the near horizon is this space here, this ADS2 times some 9-dimensional manifold, which is an S2 bundle over S7. And the bundle topological numbers are given by the magnetic charges of the black hole. All right, so again, I just remind you, I already gave you some sort of taste of what kind of, what goes into this computation. So you need to find out zero modes because you are in 11 dimensions. And there are many zero modes now in the near horizon geometry. There's a one-form zero mode in ADS2 that was like a vector. There's a graviton, a zero mode. There are gravitino zero modes. And then there are three forms. This three form is because you have a one form in ADS2 and a two form on the M9 manifold here, right? So if you put it all together, you get this number. I explained that this number does not agree with the field theory, which I will show you, and was obtained simultaneously by myself with some of my collaborators, by another group. I think INTAC is in China. I don't know if he's at the conference. But this creates this kind of puzzle. So what's going on? Why is this not agreeing? And of course, you can say, well, this is the answer, but it would be nice because the quantum entropy formula, sense prescription, always worked, but it was mostly tested in for black holes in flat space. So this is the first time where it was confronted for black holes in asymptotically ADS time. So to do that, one approach that one can follow is to do the bottom up computation. So take ADS4 and try to understand if something is failing or what is the behavior of these corrections at that level, which is what I did in this paper with my former student Marina David and Victor Godet and Jihan Liu. So let me roughly tell you. So the coefficient of the log correction, I would denote it here C. Before I was denoting it by lowercase a, but now let's see C, which is a slightly more standard notation. So it has two contributions. One is local, and I will talk a little bit about this one. That one was not present in 11 dimensions. It's only present in even dimensional space-time, like ADS4, right? And there's another piece that is global. This global piece contains 0 modes, and it can contain contributions that come from ensemble changing. So if I am in microcanonical and then I want to go to canonical, there might be a contribution that I will also call global, right? Now, the local one is the one that is given by the Sealy, the width coefficient. Yesterday, also my notation, I would call this, I call this D/2. So this would have been in my yesterday's notation A2, but it's more a standard notation to call it A4, which is D, the dimension of the space in this case. Anyway, so I mentioned, and I tried to give you some argument as to these coefficients are essentially expansion in curvatures, in derivative of curvature. So A4 is a fourth derivative term, and you can see there's a term that comes from the Euler characteristic. This is the wild tensor square. This is, a Ricci scalar square, and this is Ricci times F squared. So this is a fourth derivative contribution, and then we are parameterizing it in a particular way with these coefficients, AC, B1, B2, right? So essentially, if you give me a theory, all I need to do is to find what are these coefficients for different fields. And in fact, in this paper, we have this table, and we can compute it for a free scalar. So these are the numbers. Maybe some of these numbers are familiar to you from anomaly, and that's why this is actually not that far away conceptually. Okay, the computation is very similar. So we have the full table. I will not go over it, but important thing is that we put some of the fields separate, right? Free, gravitino, etc. But we also considered the whole multiplet of theory. So this is the statement that I was saying, that if I know the low energy spectrum, I can compute this coefficient. I can compute A4, right, by knowing what is my low energy spectrum of the theory. And that number that I compute completely in low energy must agree with whatever UV complete description I have. And in this paper, I highlighted that if you consider the n equal 2 gauge supergravity multiplet, it gives you contributions that are different from the Euler part. So they are not topological. In many cases before, it was always topological. But anyway, the key thing is that I know these numbers for the fields that are interesting to me. And I can take, for example, the Reiner-Nordstrom black hole. And for this black hole, I can evaluate all the curvature invariants, right? So we can put this in some software and evaluate it. And we have an expression depending, again, on the coefficients A, Euler, C, B1, B2. These coefficients will be given, will take values depending on the context, the matter content, and then I can find a local. Now, what is interesting about this computation, the reason I'm trying to show you, remember, we are puzzled by the fact that we have two sort of computation. One computation was in ADS4 in the full space versus the computation which is in the near horizon, which is essentially ADS2. This is S7, and this was M9. All right. So this is what we're trying to understand. To do that, again, I don't tackle the problem in 11 dimensions because I miss a lot of information. I go to just the 4-dimensional case. But one thing that now I have the precise answer. So in the precise answer, I can take the limit, right? I can now evaluate my answer for the two sort of space times. So here again, I'm going to write for simplicity ADS2. That would be my near, and then of course, maybe like this S7. All right. So when I evaluate that, this is the interesting thing that I find. So in this paper, we computed the logarithmic correction to the entropy of asymptotically ADS4 black holes in minimal n equal 2 gauge supergravity. So we find that the logarithmic correction can be non-topological. This was new for the majority, or I would say for all asymptotically flat spacetimes, it was topological. The only contribution came from the Euler part, which when you integrate it, you get a number, right? So we find that that's not the case in ADS. But the most important fact that we established is written here in blue. So if I compute the local contribution, the one that comes from the fourth Seeley-DeWitt coefficient, it really doesn't matter whether I do it in the full geometry or in the near horizon. See, as long as I take the limit appropriately, right? So the difference, therefore, in logarithmic correction between the full geometry and the near horizon geometry comes exclusively from global part, in particular for zero modes. So, and that is the reason, that is really the reason why the entropy formula was not working, because when you go to the near horizon, you're changing the number of zero modes that you might have, and that changes the answer. And that's really the issue. And I can now see it explicitly because I did the computation and I look at all the contributions, the class, the global and the local, and I can see that the local is fine. It matches. It doesn't really care whether you compute it in the full space or in the near horizon, but the global is of course not. And this, so if I have time, I will go because these have implications to a discussion that is going on right now about logarithmic temperature corrections in theories that are motivated by Jackie Teitelbaum. So I leave this as an appetizer. Let's see if I can get there. All right, so that was what I wanted to also do yesterday, but I couldn't. So now what I want to do is to show you how to compute on the field theory side. All right, it's completely changing story, right? So now no longer we are talking about gravity. We are now put our field theory hats, and that's what we want to do, a computation in field theory. So first, let me define the theory that I'm interested. This is again this ABJM theory. It's essentially a three-dimensional Chern-Simons matter theory. So Chern-Simons matter theory are sort of vanilla gauge theories that condensed matter people know and love. And again, this is nothing exotic. The only maybe not non-standard thing is that it has this gauge group, UN level K times UN level minus K. And there's this here is a depiction of the quiver diagram. So there's a standard way to characterize, to depict the theory. So the circles are the gauge groups. So there are two gauge groups. They have level plus K and minus K. And then there are a bunch of fields, in particular, all these four fields that are bifundamental. So they are anti-fundamental. So the arrow tells you essentially how they transform. The theory has a lot of supersymmetry, n equals 6 or n equals 8. These are sort of a maximum amount of supersymmetries. And then it has a bunch of global symmetry. Again, if you're familiar, fine. If you're not familiar, I'm just telling you what the field theory is, the content, and you can go into more detail if you're interested. All right, so now what we want to do is to compute essentially some partition function, right? Because that's how we do counting in thermodynamics. Of course, the partition functions that we want to compute, normally in StatMech, you think it trace e to the minus beta h, right? But they are decorated. The ones that are relevant for this problem, they are supersymmetric. So we will count with signs. So this is fermion number. It would be plus for a fermion, so plus for a boson, minus for a fermion. The Hamiltonian come from the anti-commutator of the supercharge because supersymmetric theory. And then I still have some fluxes or generator of flavor symmetries that I can use to decorate my partition function. So this is some grand canonical partition function that we can compute. We know what the object is. Now, for us, the convenient thing is the fact that the index that we're computing here, this formula, I can define it using my Hamiltonian language, but it is easier to compute using the Lagrangian language, in which case I want to compute some path integral with appropriate boundary conditions. And so in this case, it's the topologically twisted index, right? And this was explained by Benini and Zaffaroni in 2015, and we can just do it. All right. So again, you need to know a little bit about supersymmetric localization, but that can be done. So I will not bother you with the details of supersymmetric localization. It's a very interesting source of non-perturbative results. So I absolutely, if you're a student or postdoc, I absolutely encourage you to become familiar, because it's a magnificent tool. And essentially what you need to do is to put your theory in your background. So you see that this characterizes a circle, this is S2, and then I have a background gauge field, which is R charge. So again, there's some magic that happens, but at the end, the partition function that I'm seeking is given by this integral, a sum over charges, magnetic charges in some lattice, and some integral, right? And this function is some meromorphic function that is some meromorphic function. Now, the beauty of supersymmetric localization is that you can then you compute your answer by using essentially like Lego pieces, right? So you have many ingredients. You can have, for example, the answer is always going to be a classical contribution and a one-loop contribution and nothing else. There are no other contributions. There might be some instanton contributions in some cases. In our case, they're non-perturbative or non-perturbative contributions that come from magnetic fluxes. These are called magnetic flux, but they are all under control. What you need to do at the end of the day is put these different Lego pieces together, and here's the answer for the theory that we're interested in. So the topologically twisted index for ABJM is given by this formula here. Of course, this is a complicated formula. If you have never seen it, you will not understand it right now. But the point is, in this formula, compared to what was given here, I have done this integral, right? So this is an integral of a meromorphic function. So essentially, I need to find the poles and integrate those poles. And because I changed variables from x, which were my variables, to this e to the ib, I have some Jacobian that I need to introduce. That's it. Okay, so again, these equations, they look, if you have some condensed matter background, they look like the Bethe-Ansatz equation. And in fact, this is called the Bethe-Ansatz approach to the topologically twisted index. But let me summarize everything that I said. Complicated formula, I use the magic of supersymmetric localization. Here's my summary, right? One slide summary. So what we need to do to compute the topologically twisted index is, given some chemical potentials, or if you want fugacities, right? Just find the solutions of this Bethe-Ansatz equation, xi or ui. So here's the equation. This is a system of 2n by 2n algebraic equations. You can solve this in a computer, right? So you solve this Bethe-Ansatz equation. It gives you the holonomies of the two-gauge group. So remember, this was un cross un. So the holonomies characterize the Cartan of each of these un. So u and u tilde. And once you have the solution, plug them back into your expression, and then you have z. That's it. Now, the beauty of this is that this is an exact expression in n. I am not taking any limit. I am not saying that n has to be large. This is true for any n. And that allows me to not only get the large n part, which will be connected to the entropy of the black hole, but it allows me to access subleading in n corrections among them the logarithmic in entropy correction, right? So that's essentially what is going on in this computation. So, of course, I told you you have these equations. You have this equation. You have to solve them. So here's the solution. You find that there's some scaling with the parameter n. This plot is given by n equals 60, and you can see that they very nicely line the solid lines are some analytic estimate for the large n. So you see that this works very nicely. Of course, this is not the way that you should do it. If you know a little bit about matrix theory, the right way is to think about a continuous distribution of eigenvalues with some eigenvalue density distribution. In this case, because you have two gauge groups and essentially they are complex, you have two functions that describe the eigenvalue density, but this is sufficient for you to evaluate the partition function. And once you have the partition function, of course, you can get the entropy. But for me, the most interesting part is that I can also, not only I can get the leading piece, which is this n to the 3/2, I can very precisely compute subleading corrections. In particular, I get this -half log n. And this should, of course, start resembling what, or this is precisely the result that we had on the gravity side that I showed you yesterday. So again, the leading term was obtained in beautiful paper by Benini, Christosa, Ferroni, and my contribution with my collaborators is to find this log correction. And in fact, I showed you yesterday that if you study fluctuations around the black hole and you want to compute subleading corrections to the entropy, it actually turned out to be precisely this number. All right, so that part, it's again, kind of, I set it up yesterday, but now I show you what the computation is. The computation that I show you about finding, solving the Bethe-Ansatz equation, then plugging back, can be extended to many other models. In particular, I talk about this class where the 7 sphere is substituted by some 7-dimensional Sasaki-Einstein manifold, and the field theories are known. In particular, here are some of the quivers. Again, remember, circle means a UN gauge group, box is a flavor group, and you can have very complicated quivers, but for all of them, you always get the same answer. And this answer agrees precisely with what you have on the gravity side. So that's a bit of a success. So one last thing that I can fix is that I did this computation for S2 cross S1. And in fact, I told you yesterday that in gauge supergravity, the horizon can have any topology. It can be S2, but it can be any Riemann surface. So there's also a nice and relatively easy way to generalize, given the free energy or the partition function on S2 cross S1, to go to S2 cross sigma G, the Riemann surface. And this is the formula, and that formula precisely agrees with the formula that I showed you yesterday in general. So now we have shown that the field theory computation of the log correction of the entropy precisely agrees with the gravity computation. All right. So okay, so that is that part about. This was about ADS4 black holes. So now I want to tell you a little bit about. I promised also at the beginning that I wanted to talk a little bit more about these rotating black holes, and in particular this ADS5 black hole. So at the end of 2018, 3 different groups, more or less simultaneously, found a microscopic explanation for the entropy of ADS5 black holes. These are supersymmetric black holes, of course. And very quickly, this was extended to basically all rotating black holes in ADS4, ADS5, well, ADS6 and ADS7. And I contributed with different people, but in particular with Jun Liang, who's organizing the conference. So we worked out how to compute the partition function that explains the entropy for ADS4 black holes. All right, but so once you have so much data, right? So you have now for all ADS4, 5, 6, and 7. You might wonder, okay, so given that at least the Bekenstein-Hawking entropy area divided by 4G is such a universal quantity, you wonder, do I really need all topologically twisted index, superconformal index, all this very detailed knowledge of the UV theory? Or is there some simpler way based on maybe just symmetries that I can get at the entropy of black holes, and maybe even to subleading correction? That's a natural question that arises once you have this abundance of examples. And in a sense, conceptually, this is similar to the developments during the Strominger-Vafa era, if you wish. So there at the very beginning, if you remember, or if you know, the computation was based, was kind of a complicated computation. You have to look at the modular space of some instanton in a string theory, the 1D5 system. So it was a complicated computation. But after a while, people realized that you can reproduce the entropy of all these black holes using ADS3, essentially, and the Brown-Henault asymptotic symmetries that are in the near horizon. So this is sort of what we are looking for here, okay? An analog of that sort of conceptual simplification of the issue. Of course, it's nice, and I think it's very impressive if you are a string theorist to see that a string theory and ADS-CFT can provide explanation for the entropy of all these black holes, right? So this is certainly not a fluke. This is a very powerful result in string theory, but we also should understand whether there's a simpler way to tackle it, to interpret it. So for that, let's go to the, now by this time I have shown you many partition functions. So this is the partition function, the superconformal index. This is of course I'm writing this for n equals 4 supersymmetric Young-Mills. This is the prototypical example of ADS-CFT. This n equals 4 super Young-Mills dual to type 2B string theory on ADS5 process 5. So this index counts 116 BPS states in n equals 4 super Young-Mills. If you have some other theory that has n equals 1 supersymmetry, then it counts a quarter BPS. So only one supercharge is needed. Again, here you have your what you remember from your even undergrad standard class, e to the minus beta h. But again, it's supersymmetric, so it's decorated. It's actually some sort of with an index, has -1 to the f. And then there are two angular momenta, J1, J2, that I can use to refine my partition function. And then again, global charges. These global charges are in the Cartan of SO6, if you wish. So it's all understood. All right, so this partition function, again, can be computed using localization or other techniques. And what I did with some of my collaborators, so my former student, Alfredo Gonzalez and Jung-Ho Hong, who was a PhD student here in Michigan, and my colleague Jim Liu, is we studied this partition function and we expanded for large N, right? Because we wanted to see, to reproduce, of course, reproduce the entropy, but as you see, by now you probably see me as the logarithmic police. So wherever there's a logarithm that might be lost, I go there and I find it. So we went into this partition function and we found that there's also a log correction, and this is the value. So it has coefficient 1, and so we did it in two different ways just to be sure that we are getting to the right answer. But then there were a number of papers, in particular one with Antonia Mariti. Alessia is in the audience, I believe, who showed that this is really true for other gauge groups in other situations. And after that, there was a paper by Kazani and Komagorsky, and also another paper by Murthy and Ardehali that tackled this problem, and again reproduced this log. So this log is there in field theory. I computed it with my collaborators, but many other groups have confirmed that this is there. So it would be wonderful to have some understanding of this log correction from the gravity side. Unfortunately, now the problem would be in type 2B supergravity, which is an even dimensional theory. So I have tackled this problem. It's quite tough. But I started by telling you about some lower dimensional approaches, right? So here I would like to have some sort of lower dimensional approach. So I will tackle this log correction in a slightly different way, which I will tell you right now. So as you see in this diagram, right? So this is what I told you yesterday and I'm part of today for ADS4 black holes, right? So I told you how to compute correction in the boundary theory, how to compute corrections on the gravity side. In this situation, it's a little bit more complicated. So what I'm going to do first is to go to the near horizon geometry, right? And another great thing is that I know in ADS5, there are no zero modes. So I know that I'm unsafe. If I go to the near horizon, I'm not losing a lot of any information for that matter about the log. So that's really crucial. I cannot do this for ADS4 because I will be missing global information. But for ADS5, it's okay. So in this case, if you go to the near horizon, then you can apply Kerr-CFT and get an explanation for the entropy that is also microscopic, right? So you have some CFT2. In that CFT2, you do a counting using maybe Cardi formula, some kind of counting formula in CFT will give you precisely an explanation for the entropy. That's sort of the path that we want to follow. So the right approach, because these black holes are rotating, these are not spherically symmetric, so it's not so simple to get to the near horizon, is to apply Kerr-CFT. So Kerr-CFT was introduced in this paper by Strominger and collaborators. And for the case of ADS black hole, Hong Liu was a big contributor, so he has 2 papers. I think he lectured in this school as well. But anyway, so that was done in 2008. More recently, again in collaboration with Junyan and also my student, my ex-student Marina David, we revisited this problem for these black holes in complicated gauge theories, and we found that for all the black holes, all the black holes, rotating black holes, ADS 4, 5, 6, and 7, we can run this argument, go to the near horizon, and apply Kerr-CFT, and we do get a microscopic explanation of the entropy. So that was encouraging. So after having this success, we decided to tackle also the logarithmic correction. All right. So again, just a picture is always clarifying. So a lot of the computations were done at the boundary. So we have a boundary CFT, and that was clarifying and computing for us the entropy of the black hole. But now we're going to be working in this area, very, very close to the near horizon. We apply Kerr-CFT to find a statistical interpretation of the entropy. And again, this is in my paper with Marina and Jun, and that paper described this term, right? The big chunk, the Bekenstein-Hawking entropy, for all the black holes that I discussed at the beginning. Now, at the level of a technical level, so Kerr-CFT provides some CFT2, and in this case, it has n global U1 symmetries, right? So they're conserved charges. It's not just a CFT2, the simplest CFT2. So in fact, these are the conserved quantities. But if I know the partition function, right, I can do a Laplace transform and get the density of a state. That's the microscopic derivation of the entropy. So for the saddle point, if I just do these integrals using saddle point approximation, I get the main Bekenstein-Hawking entropy. So that's what I did with Junyan and Marina at the, first. And then after that success, we went after the logarithmic terms. And in this picture, all we need to do is really do this integral a little better, right? Not just stop at the saddle point, but do maybe a Gaussian approximation. If you do a Gaussian approximation, you get that the contribution to the entropy is -2 log n. At this point, you might say, hey, -2 versus +1, what's going on? So what's going on is that there's another contribution that I'm not writing, but that comes from changing ensemble, right? So this is microcanonical. The partition function was in grand canonical, so I need to change ensemble, and that gives me this 3 log n. So at the end, there's perfect agreement, again, using Kerr-CFT. All right, this is for ADS5 black hole, also works for ADS5 rotating black string. So it's quite generic, this approach. All right, so let me summarize a little bit most of what I have done up till now, because it's quite a bit. There's a lot of moving parts. So yesterday and between yesterday and today, I convinced you that the log correction to the entropy of magnetically charged ADS4 black holes that are ADS-CFT dual pairs, including very complicated quivers. S7 is the quintessential example where I have ABJM and ADS4 cross S7, but I can also do it for all these 7-dimensional Sasaki-Einstein, and it always agrees. Okay, I show you the computation yesterday on the gravity side, today a little bit on the field theory side. Good. So I also, this one I did not show you in detail, but I mentioned that I can compute the log corrections of ADS4 black holes that do not come from N2 brains. So they come from RAP N5 brains, RAP on hyperbolic 3 manifolds. So there the computation on the gravity side is what I showed you yesterday. And on the field theory side, it's much harder because it uses some other technique, the 3D correspondence, which it will take me a long time to explain. But believe me, the field theory there, it's anyway. So that is part of what I have done, and I have 1 or 2 slides yesterday trying to convince you of that. I have not shown you the field theory, but believe me, or you can look at any of my papers that address that issue. All right. So then I discussed this sort of bottom-up approach to corrections, where I try to understand more specifically where is the correction coming from, the near horizon or the full space. It turns out that in even dimensional ADS, for ADS4, I bet for ADS2, it does matter. It does matter a lot because the issue with the zero modes and global contribution. But in ADS5 is fine. But at least now we have an explicit explanation, explicit computation of the contribution. And then the last piece that I explained was how to get subleading corrections for rotating ADS5 black holes using the superconformal index, or from rotating ADS5 black strings using the topologically twisted index. So I'm not, okay, here I'm calling things their rightful name, but roughly speaking, we have to identify the right partition function that does the counting for the black hole configuration we're interested. And we showed that if I go to the near horizon and use the Gaussian approximation to the Cardi formula, I can also reproduce the log correction. So that's what I have been telling you up to now. So I did not check exactly how much when I started. So how much time do I have? Okay.
You still have about 15 minutes.
15 minutes. Okay. All right. So let me start. Okay, I'll tell you an a brief version of this log temperature correction because I think this is quite interesting. I will not go into details, although I have some slides with technical details, but I will stay. Okay, yeah, let's go. So up to now, I told you about logarithmic in entropy. So the entropy of a black hole has area divided by 4G. Then I mentioned there are high curvature corrections that we are not talking at all now. But then there's some corrections that come log of area divided by G. And then there's other kind of correction, let me call them B, that are log of temperature divided by some quantum temperature, right? So these are the ones that I want to talk about right now, these log temperature corrections. All right, and let me tell you a little bit about the history. It's a quite interesting history of how this actually started out. So if you take any black hole, and I will show you some example if I have time, but if you take any black hole that is close to extremality and you expand its entropy, the entropy goes linear with temperature, while the mass goes quadratic with temperature. So if you're at very, very, very low temperatures, so there's a scale here that I did not write, but let's assume that this is T over TQ, right? So this because it must be dimensionless. So when T over TQ is a lot smaller than 1, right? Then this is a lot smaller. This contribution would be a lot smaller than the entropy. And that's a problem. This problem was identified by these people back in 1999, so almost 30 years ago, more than 30 years ago. So the problem is that if you want to emit the Hawking quanta, the quanta has energy proportional to the temperature. So one quanta with energy proportional to temperature will completely obliterate the black hole, which has a lot smaller mass, right? So there's not enough energy in the black hole to be taken away. So it creates this kind of breakdown of thermodynamics. That's how they explain that. So and essentially, yeah, it indicates that something is fundamentally wrong with this limit. So in this limit, clearly a black hole is not even able to, the approximation, the semi-classical approximation that we think of our Hawking radiation is completely wrong. All right. So now this puzzle was resolved, and it's amazing that it did not require a full quantum theory of gravity. It was resolved by understanding that that there are some zero modes in this problem. If you have a black hole that is near extremal, there's usually an ADS2 region, and then there's some zero modes, and that those zero modes, if you treat them carefully and correctly, you get a correction to these formulas, right? A correction that becomes more important in the region where you expect trouble. Okay, so that's roughly the situation there. Now there's a lot of work that came before that. So these are these papers here. In fact, I think that the speaker before me was talking precisely about SYK, JT. So this resolution was possible because it was already understood in the context of JT gravity that the temperature actually effectively works as a coupling constant. And very high temperature is like the system behaves classically, but at low temperature, quantum fluctuations are very important and you cannot neglect them. And in fact, if you take them into consideration, then you get a resolution of this puzzle, precisely because at that level, there would be a logarithmic in temperature corrections to the entropy. And then this whole formula is invalidated. All right, so that's what I wanted to. So this fits very nicely with the story I was telling you before. Before I was telling you a little bit about this story. So instead of talking about the high level ADS CFT problem, I focus on the near horizon problem, right? Which I can understand better in terms of symmetries that asymptotic symmetries, that kind of thing. So similarly, right? So we can also take some near horizon limit of many of these ADS black holes and try to put them in this context where you have SYK on one side or SYK-like theories and JT gravity. All right. So good. So, but we don't want to do just JT. JT is a toy, sort of a toy type of problem. We want to understand our actual black hole in higher dimension. How is JT going to be relevant for this black hole? And now, so if I show you that there's a JT sector or subsector that dominates the path integral, that's really quite important, and that's what's shown in this series of papers by Iliesu, Turiachi, Heidemann. Now, if my black hole is spherically symmetric, everything is very easy, right? So if I have ADS4, a black hole in 4 dimensions, in the near horizon will become ADS2 cross S2 or something like that. So clearly, I expect the JT to arise here. But for black holes that are rotating, it's not so easy. There were a number of attempts at understanding how JT, certain classical aspects of JT are relevant, but that was in this series of papers, but this was only classical. So what we would like to see is the physics of JT, not necessarily just the physics, the intuition that we gain from JT, apply that directly to rotating black hole in higher dimensions. So that was actually done in these 2 kind of twin papers by Strominger and collaborators, and here Rakic, Rangamani, and Turiachi. So they computed this log temperature correction for the Kerr spacetime. This is asymptotically flat for dimensional Kerr black hole. All right. So what they did was to realize that the near horizon solution admits, in fact, a family of normalizable zero modes. Right. So once you have these zero modes, you need to learn how to deal with them. So, for example, the path integral over these zero modes leads to an infrared divergence. So this is the partition function essentially becomes infinite. And this matches very nicely with what we were doing yesterday. Yesterday, we were looking at how to compute the determinant of this operator. But if you have a zero mode, it will go to the denominator. And if it is zero, the whole thing blows up. So that's the infrared divergences we're talking about here, right? Now, you have to regulate it. The natural way to regulate it is to turn on some temperature, small but non-zero temperature, and then see how much of that remains. So the resulting finite temperature geometry actually breaks the symmetry. So the zero modes are no longer zero modes. And now the path integral is infrared finite. And when you compute it, you will get that there is a contribution to the partition function that goes like, t to a 3/2, or for the free energy would be 3/2 log of t. So this 3/2 log of t is a lot larger than t if t is small enough, it's smaller in some scale. That's how the problem gets resolved. Now, what I did in this paper with my collaborators, Sabiasachi Maulek, Ogniva Reid, and Jin Chao Zhang, was precisely to understand how this works for black holes, basically in asymptotically ADS, because I want to always connect to ADS CFT. So we did this computation for Kerr ADS4 black hole. We also did it for Kerr Newman ADS4 black hole, and also for some rotating black holes in n equals 4 gauge supergravity. So U1 to the 4 supergravity. This is the supergravity where the black hole that is dual to ABJM leaves. And in all these cases, we get universally this 3½ log of n from the tensor modes, right? And so we also discussed asymptotically flat Myers-Berry in 5 dimensions, KRADS5, and of course some elements of the gauge supergravity that would be related to the ADS5 black hole. So we universally found in all cases this contribution, and it came after we do the computation a few times. We realized that the ingredients that were required were essentially that you always have SL2R acting. This is, of course, the group of isometers of ADS2. There's always an ADS2 factor. And then there's a set of cancellations in the Lishnerovich operator. This is a little bit less trivial, but after you establish that, then you get that this is always the contribution that ends up, this is the final contribution. All right. So let's see what else. All right, so I don't know if I want to show you too much of the computation. Let me do it quickly, just so that you see that there's no, nothing is. So here's the supergravity action or the gravity action. I'm going to discuss curved ADS4. It's simple, negative cosmological constant. Here's the metric. The metric, I hope that you're familiar with the curved black hole in ADS. Here's what I was telling you about expanding for a small temperature. The mass has some M0, right? And then it goes quadratic in temperature, while the entropy has S0, this term, and then goes linear. That is the conflict. That is what we want to solve. And here's the angular momentum of the black hole. So we can take the near horizon limit, some sort of Bardeen-Horowitz limit. The key thing is that the near horizon limit gives me, so you can recognize this as an ADS2 part of the background. Of course, it's fiber over zone U1. This is so the black hole is symmetric. And then I'm also allowing this linear in temperature correction to the metric, so as to lift the 0 mode. So if this term is not there, if this is not there, then I do get 0 modes, and my path integral is divergent. But once I integrate this, it regulates. It regulates the whole partition function. Now, here's a little bit more detail again, because in ADS4, I need to do things more carefully. So I'm expanding, right? I'm expanding around the black hole like I did yesterday. Now I'm doing it in more detail. So this always gets you to a Lishnerovich operator. I also need to include the fact that to integrate over metrics, I need to do my gauge fixing. So here's my Lishnerovich operator. You can see in this case, because I have cosmological constant, it's a little bit more complicated. So I can show that if T is 0, right? If I have the metric with no linear in temperature part, there are 0 modes. The 0 modes are obtained in an interesting way. They are obtained by diffeomorphism. So this is quite typical in ADS. And I can compute, right? I can compute the 0 mode. This is the 0 mode, this part of the metric. If you put it in the Lishnerovich operator, you will get 0. And now what I want to do is to include, so I can study what is generating this 0 mode. What are the diffeos that generate that isometry? And more interested, I want to see what the diffeos are at infinity. And at infinity, for eta is the radial direction. At infinity, this is the form that the diffeos take. They don't die. So these are what they are called this large gauge transformation, right? So again, the diffeos, they generate a vector field at the boundary that you can write like this, or in a more convenient language, you can see how it changes the coordinates. So this part, we know that this is exactly how the Schwarzian mode acts on JT gravity. But of course, we have a more complicated situation. We have the action is more general, but it does contain the physics that we know. This is the wiggly ADS2 that you might have seen in some papers. So, but this was the fact that this gets extended is now very explicit. So after that, I can compute these were 0 modes, so the eigenvalue was 0, and now I look at the correction that comes from turning on temperature. It's linear in temperature, and here I can now find the product of all these modes, or the sum of the log if I want. This is the determinant, right? We discussed this yesterday, And when I evaluate this, I get precisely this expression. This expression passes a few interesting sanity checks. So if I take L large, I reproduce the result of Strominger and Friend and on the other twin paper. But good. And we can we also confirm that this is independent of the ensemble that you're using. So this term, as I said, this term, log of T Hawking divided by T quantum, dominates the one loop partition function of very small temperature. So small with respect to TQ. And that is, again, the way out of the puzzle. And it's important that we can do it now for rotating black hole in many, many examples. So I just show you the computation for Kerr-ADS4, but in the paper we did it for Kerr-Newman ADS4, Kerr-Newman ADS4 in N=4 gauge supergravity, the theory dual to ABJN. We did Myers-Perry, which is asymptotically flat in 5 dimensions. We did Kerr-ADS5, and we did, not completely, but some of the parts, some aspects of the 5-dimensional U1 cube gauge theory, which is the dual to N=4. So in all these cases, we find the same contribution from the tensor, and we know that it comes because there's some isometries in the ADS2 throat, and then there's some specific cancellations in the Lishnerovich operator, independent of the matter feed that you turn on. All right, so now you might be puzzled, like, oh, why didn't you tell me about log corrections yesterday when we were? But yesterday I was talking about supersymmetric black holes. So I want to show you a counting that convinces you that this does not apply or is not relevant for supersymmetric black hole. Because in supersymmetric black hole, we will have a contribution from the graviton, which I am saying is completely universal, this 3½ log T. But then the gravitino, in N=2 theories, I have 4 gravitinos, and each is a fermion that contributes -½ And then I have a vector that contributes +½ So the overall contribution is 0. So supersymmetric black holes do not suffer from this log correction. These are for black holes in that are non-supersymmetric. So that's why we are okay from what we did last time. So I think this is more or less what I wanted to tell you. So I want to finish with some open problems. So some of them I'm working on them right now. So I want to actually highlight the hard work that some of my collaborators are doing. So there was this paper already recently in October in collaboration with Xiaolong. Xiaolong is a student at the University of Chinese Academy of Science, and my collaborator Junyan. And we are about to finish, it's about to appear another paper with Songyuan Yue, who's also a student at the University of Chinese Academy of Science. So these papers deal with trying to understand these fluctuations, these quantum fluctuations for near-extremal black hole in the ADS context. So because we have ADS-CFT, we can see if they change the phenomenology of ADS condensed matter, or we change or how they affect issues in the fluid gravity correspondence, which is a very important result in ADS-CFT. So I'm also working on how these corrections affect Hawking radiation. And so yesterday there was a question, and I think that was referring to a paper by Iliesu, Pennington, Brown, and Usak, who did this for spherically symmetric black holes. So it is really interesting to do it for rotating black holes, Kerr-Newman black hole, because black holes in the skies don't have charge, but they do have a lot of angular momentum. And just to finish, I want to emphasize that there are many black holes I will leave you with proof that there are many near-extremal black holes in the sky, astrophysical black hole. And I think that we have learned a number of lessons studying supersymmetry and studying black holes in ADS, but some of these lessons we might try to take to this actual astrophysical black hole. And in particular, given my collaborators in China, I am excited about exploring whether there's any imprint in gravitational waves that come from this near-extremal black hole. I want to leave you with this table. It's hard to see. I know it's hard to see, but let me leave you with this table. This is a table from a PhD thesis at the astronomy department here in Michigan. That essentially these are all examples of kind of solar mass type black holes, and this is the spin. This is the parameter that is angular momentum divided by the mass. A1, right, represent a stream of black hole. And you can see that the majority of the black holes are really here, very close to extremality. So I think this is exciting, and I leave you with that. You're young and powerful, so I wish that you get excited about this and write some excellent papers that will bring some of these ideas into connection with black holes in the sky. So thank you very much.
Okay, we thank Professor Pandor-Zayas for teaching us some modern applications of VDS-AFT correspondence, in particular to black hole physics. Any questions? Oh.
Hello, Leo. May I ask you a question?
Yes, please. Hi, Sanjuan.
Hi. How are you?
Good.
I have a question about the generalization to the Kerr black hole case, because in the Kerr black hole, maybe it seems that the zero mode is quite different from the original one. The original one maybe kind of only have the time reparameterization mode and do not have the rotational mode. But it seems that in the so do you think there is enough technique to generalize to the Kerr black hole case for each of the
So I think it is exactly. I mean, if you look at JT gravity, this is the reparametrization mode. It acts on the boundary, right, on eta. It also acts on time by shifting time. It just happens that this particular zero mode, it also acts on the angle, but I think it's the natural extension. So the beauty about this computation, and I think this is really, at least for me, what is exciting about this kind of computation is that it is not that I start with, let's say, 4D gravity and I do dimensional reduction to 2D and then I see, this 2D has JT. No, this is not what we're doing. What we're doing is we are tackling a problem always in 4 dimensions and realize, right? So here, for example, if I'm looking for a zero mode of this Lishnierovich operator, this is a 4D operator. It just happens that there's a zero mode that nicely connects with the zero mode that is there for JT gravity for 2D. But my problem is always I never reduce, I never throw away a lot of information. So that's what I think is, for me, is interesting, because we're seeing the physics of JT, but in really higher dimension without the need to truncating. Once you see, if you want to look for a quantum aspect and you truncate, then you're being counterproductive. You have to, when you have fluctuation, everything fluctuates. So to say this fluctuates, but this other thing is a big approximation. But this is a 4D problem, and in this 4D problem has a solution that comes from the physics of 2D. That's the right conceptual way, I think, to tackle this.
Yeah, thank you. I agree. So you think in this 4-dimensional construction from the 4-dimensional symmetry of the zero modes can also do the path integral among all the zero modes, just like the dimensional reduction case is the same?
Yes. So there, okay, good. That's a very subtle question. So I don't know, right? So probably not. But this is the beauty of zero modes. So zero modes are special characters. So my talk yesterday was about this particular two-form zero mode in 11-dimensional supergravity that accounts for all the log entropy, right? So this is, I think, this is a very exciting question. I think it's not completely settled. So this idea that this zero mode near the horizon completely determines the answer, and that needs to be checked. In fact, some groups are trying to check that, because we know that, for example, for some of the theories that is not true. But I see this as progress. Again, it's not completely settled, but I think it's moving in the right direction. But I'm happy to talk more to you more about this with you, especially in a few weeks I will visit China, so I'm excited about having more discussions.
Okay. Thank you.
More questions? Any other questions? Okay, you want to, okay.
Does this log entropy survives in the ds gravity?
Oh, that's another very
Especially
good
DS2?
question. Yeah, no, that I don't know. I have some friends who are doing this computation, and they come up with some friends tell me yes, some friends tell me no. So I don't know, but I know it's a very active, very exciting question. But I unfortunately am not working on that. I don't know at the moment. Nice question. Yes, but it's very interesting. I know at least 2 groups, if not 3, that are discussing this. Yeah, log corrections in de Sitter. Yes.
Any other questions? Okay. If not, let's thank Professor Panazas for these 2 great lectures. Okay. Thank you much. Thank you, Leo.
Thank you. Thank you.
Okay. Thank you. So that's it for this morning. We're going to continue at 2 p.m. Hi, Professor Chen. Shall we start your second lecture on time? Hello.
Yes.
Okay.
Can you hear me?
Okay. Yes, we can hear you.
Great.
You can share your slides again.
All right. Can you see it? Well,
not yet. Not yet.
All right. Let me.
We saw it
before, right?
before.
Yes. Let me do it properly. How about now?
Yes, we can see your slides and we can hear you.
All right. Very good.
And it's the time.
All right. So let's
Okay.
get started.
Yeah, let's start this afternoon session. The first lecture is again given by Professor Chen. He's going to continue the discussion on neutrinos. Let's welcome her.
All right, so I hope everybody had a nice lunch and a lot of good discussions. And just a reminder, yesterday we went through the neutrino oscillation formulation. Also very quickly, we introduced various type of experiments that measure, using atmospheric neutrinos as a source, using solar neutrinos as source, using reactor neutrinos as a source. So of course there are a lot of both past, ongoing, and upcoming experiments. And within the last let me see, 15 years or so, we have learned a lot in terms of neutrino properties, particularly their masses and mixing angles. So what you see here, this sort of a very nice pictorial summary of what we learned, what we know so far. So what's plotted here are the ordering of the three neutrino mass eigenstates in terms of their masses. On the left, this is called the normal ordering, or sometimes it's called normal hierarchy, where nu3 mass eigenstates is the heaviest mass eigenstate, where nu2 and nu1 are the lighter mass eigenstates. And the way that nu1, nu2, and nu3 are defined, as you see here with the colors, they are defined using the compositions of nu-e, nu-mu, and nu-tau. All right. So of course, the particular compositions is indicated proportionally on these diagrams. And this proportionality are determined, of course, through the measurement of the mixing angles. All right. So as you can see here, for the normal hierarchy, this big delta m square between nu3 and nu2 or nu1, this is what's driving the atmospheric neutrino oscillation. And through the measurement, we know this delta m square is on the order of 2 times 10 to the minus 3 electron volt square. Where the smaller mass square difference between M2 and M1, this is what drives the solar neutrino oscillation. And from the experiment, we know this delta m square is around 7 times 10 to the minus 5 electron volt square. All right. On the right, again, this so-called inverted mass ordering or inverted mass hierarchy is also compatible with our current data. And for the inverted ordering, we have nu2 and nu1 being the heavier mass eigenstates, and nu3 being the lightest mass eigenstates. All right. And again, the delta m square between nu2 and m2 and m3, this is the delta, right? This is what drives the atmospheric neutrino oscillation. And again, the m2 squared minus m1 squared, this is what drives the solar oscillation. Okay. All right. In terms of the mixing angles, again, the three mixing angles are describing the mismatch between the mass eigenstates, nu1, nu2, nu3, and the flavor eigenstates nu e, nu mu, and nu tau. And currently, the measurement roughly give the following values. For the 2-3 mixing angles, or the atmospheric mixing angles, this is large, close to maximum, but it's not maximum, right? So it's about 42 degrees. Where the 1-2 mixing angle, is sometimes also called the solar mixing angle, is about 33 degrees. Where the 1-3 mixing angle, this is about 9 degrees. All right, so this is sort of our current knowledge of the oscillation parameters. So you combine all the available data and perform a chi-square fit. There's a really big industry. There are actually 2 main groups in the world doing so-called global fit, and this basically the best values that can fit all the experiments and give the lowest chi-square. All right, so that's sort of the whole idea. So I'm not going through. I am not going through the details of this table. You can look up the reference and study more closely. But just to draw your attention, where for the atmospheric mixing angle, again, like I said before, it is large, but it is not maximal. All right. But another very interesting aspect that I would like to draw to your attention is the fact that even though so far we don't have a direct measurement of the Dirac, so-called Dirac CP phase in neutrino oscillations, from the global fit itself, meaning the consistency, right, across all the experiments, we are able to draw some information about the value of delta CP, right? So from the global fit, we know the best fit value right now is about 232 degrees for normal ordering, where for the inverted ordering, the best value is about 276 degrees. And of course, the allowed range is still large, but on the other hand, certain region of the delta CP values are ruled out, at 3 sigma level using the global fit. All right. All right, very good. And in terms of the preference between normal ordering and inverted ordering, again, I think it's still like way too early to tell. Statistically, there's not really a strong preference of one versus another. And there's a very recent meaning, earlier this year, where different experiments, they are combined their analysis, and in particular, this involving T2K and NOVA, and also later with Dial Bay. And depends on how one combine the data. In some cases, inverted ordering was slightly preferred, but once adding the Dial Bay data, then the normal ordering is preferred. So bottom line here is, I think for the mass ordering, we still need to wait and see. All right, so even though we have learned a lot in terms of the mixing parameters, but there are still many open questions in regard to neutrino properties that we still don't know. And there's a list of questions that you see here. This include the Majorana versus Dirac nature of the neutrinos, right? Meaning where the neutrinos are their own antiparticles. Whether there is CP violation in the lepton sector, right? Whether delta CP is 0 or 180 degrees, or or is it like really CP violating? Meaning if it has a value that is deviating from 0 or pi, right? What is the absolute mass scale of the neutrinos, right? Because neutrino oscillation only give us the information about delta m squared, but it doesn't really tell us what is the absolute mass scale of the neutrinos, right? So this is still an unknown. Again, mass ordering, meaning whether it's inverted or normal ordering that we saw from the last slide. In other words, what is the sign of the delta m 1 3 squared? Okay? whether there are only 3 neutrinos or are there, more neutrino species, namely, are there stereo neutrinos? Again, this is still an open question. And the last one, last but not the least, is the precision. Meaning, we see theta 23, which is very close to maximum, meaning 45 degrees. But it is, so far, the basic value is deviating from maximum, right? And of course, this question about precision is very relevant when we are trying to build models to explain, right, the observed mixing angle. In other words, if theta 23 turns out to be exactly maximal, meaning 45 degrees, that would strongly indicate that there is underlying mutal symmetry, right? But if the theta 23 deviates from 45 degrees, what that is telling us is that this underlying mutal symmetry must be broken. And right, how big the deviation is would correspond to how big, right, how badly the symmetry breaking is, right? So these are sort of the open questions, still outstanding questions in regard to neutrino properties. And of course, there is a suite of current and upcoming experiments that are aiming at address these puzzles. All right. And of course, in order to understand these properties from a fundamental at the fundamental level, this will require beyond the standard model physics. All right, so now I'm going to move to the theory side. I just show you those more like final neutrino property related questions. And of course, fundamentally, so far this observation of small neutrino masses and their large mixing also pose certain challenges theoretically, right? The first challenge has to do with the smallness of the neutrino masses, right? I just show you the 2 delta m square, both are in the sub-eV electron volt regime. But if I put the possible neutrino mass pattern on this mass spectrum that I showed yesterday, what you see is there is a huge gap, right, between the neutrino masses and the charged fermion masses. Right, so the question is why the neutrino masses are so much smaller compared to the charged fermion masses. Right, so that's sort of one question. And another layer of the question is why do all the masses older the way it is, right? So this is the so-called fermion mass hierarchy problem. And of course, if you compare the observed lepton mixing angles, they are really large. Right, so what I show here on the bottom part, these are the corresponding range of values for each PMNS matrix elements, right? And if you compare this with the range of values in the CKM matrix elements, you see a very, very big difference. So in other words, the smallest elements in the leptonic mixing matrix, meaning the 1,3 mixing angle, this is smallest in the leptonic mixing matrix, but this corresponds to the largest mixing, right, in the quark sector. So the question is, why do leptonic mixing angles are so large while the quark mixing angles are so small? And of course, a related question is, what is a precise value of the Dirac CP phase in the lepton sector? All right, so I just mentioned that. And of course, these different structures correspond to the mismatch between the weak interaction eigenstates and the mass eigenstates. So what that's telling us is, quarks do not really mix that much, but for leptons, it is totally the opposite. All right, so of course, all these patterns that we just saw, are not really explained in the standard model. In the standard model, these patterns are accommodated by a very large number of free parameters in the Yukawa sector. So my first question of the day for you is, how many parameters do we need in the Yukawa sector of the standard model, assuming neutrinos are Majorana fermions? Is it clear what the question? Any volunteer? How many?
Just give us a bold answer.
Just give you an answer. Oh, all right.
No, you already give answer. Okay.
So
do you still want some student try?
Yeah. What should be the answer?
Okay. In the quark sector, we have 6 quark mass and 3 mixed angle and 1 CP violation. So there will be 10 parameter in. There will be 10 free parameter in quark sector, and in the lepton sector, there will be 6. There will be 6 lepton mass parameter, and also 3 mixing angle and 1 or 3 CP violation phase. So there are total 10 or 12 free parameter in the lepton sector. So the total free parameter may be maybe 20 or 22.
Right? If neutrinos are Majorana fermions.
Yeah, if neutrino are Majorana fermions, then there will be 22 free parameter.
Right, excellent. So 22.
Okay.
Right, so there are many, right? 22. And this is 22 out of the 28 parameters in the standard model. So again, what this means is, a really large part, the structure of a very large part of the standard model parameters that we don't understand, okay? All right, so in the rest of the lecture, what I will be focusing on is really the origin of the fermion mass hierarchy, flavor mixing, and CP violation, right? So the question is whether there is a simpler organization principle rather than just having, 22 undetermined free parameters, all right? And so this is like a little bit like periodic table, right? The ordering of the periodic table is determined by the atomic mass and atomic the number, right? And with these 2 numbers fixed, we know how the periodic table is organized. And likewise, we want to have such a more fundamental understanding about why the fermion masses are ordered in a particular pattern and why their mixing angles are of a particular pattern, right? And of course, a related question is, where do neutrinos get their masses? Since we know in the standard models, their masses are predicted to be 0. So the question is whether it's the Higgs or something else that give rise to neutrino masses. Right? Okay, so a related question, which I don't think we will have time to touch upon, but this is very closely relevant, is what is the origin of matter-antimatter symmetry of the universe? Meaning, why do we exist? And later go through some literature where you find this neutrinos may play a very important role through the mechanism called the leptogenesis, which is again closely connected to the mass generation of it's closely related to the neutrino mass generation mechanism. All right, so neutrino masses beyond the standard model. Yesterday, we already talked about, right? Standard model predicted 0 neutrino mass because, standard model doesn't have right-handed neutrinos, and it also doesn't have, Higgs SU2 triplets. So the simplest options to generate neutrino masses is to add right-handed neutrinos, right? So once I add the right-handed neutrino, which is a gauge singlet under the standard model, we can then write down the so-called Dirac mass, just like what we do for all the charged fermions, right? Even though this is okay, but there are certain issues, right? Even though I can write down this operator, but there are certain issues. And the first issue is why the Yukawa couplings are so small, right? Because the Higgs wave is 126 100 GeV-ish, and in order to get a neutrino mass on the sub-eV level, I need the Yukawa coupling constants on the order of 1 part in 10 to the 12, right? So that's like very unnatural. And the second issue with this approach is the question why there are no large Majorana mass terms for the right-handed neutrinos, right? Because the standard model symmetry allows the right-handed neutrino mass term. And therefore, any operators allowed by the symmetry should exist in the Lagrangian. So if I were just like to give a Dirac mass term only to the neutrinos, then there's this question, like what forbid the Majorana mass term for the right-handed neutrinos, right? The second option is to add a Higgs SU2 triplet. And this, of course, give rise to Majorana mass for the left-handed neutrino. And again, this is an exercise for you. This is following up to the question that was asked yesterday, right? Why is this term allowed? And this is really just SU2 gauge, SU2 group theory. So it's a nice exercise for you to do at home, right? To convince yourself that products rule give you a pure singlet, right? All right. So even though we can add a SU2 Higgs triplet and write down such a Majorana mass term, but the question then is, why is the vacuum expectation value of this Higgs triplet much smaller compared to the Higgs wave, right? So these are the issue if I'm just going to do things so simply. So generally, in these models, new fields are introduced only to generate neutrino mass. And secondly, there's no understanding of why neutrinos are so light, right? This is a bit ad hoc. All right. So if we take the approach and assume that, the standard model is an effective low energy theory with some, and what that means is there's new physics above certain cutoff scale. And in my effective low energy theory, those new physics effects would appear through the so-called non-renormalizable operators. And these effects are suppressed by powers of the small parameters, namely the electroweak scale, which is a characteristic scale of the standard model effective low energy theory, divided by the cutoff scale lambda. Neutrino masses can be generated by the so-called Weinberg operator, which is a dimension 5 operator of the form of HHLL, right? And given that it's a dimension 5 operator, it is, it has to be suppressed by 1 power of this cutoff scale, big lambda, where small lambda, ij, these are the dimensionless coupling constants. So if lambda is, large enough, then we can generate a light enough neutrino mass with order 1 coupling constant lambda ij. Right. Any questions about this? All right. Okay. So here is our Weinberg operator. And I want you to stare at it for 10 seconds. And the question for you is, what symmetry or symmetries does the Weinberg operator break? Any volunteer?
I think it's the lepton number is violating.
Excellent. So lepton number is violating, and more precisely, it's both the total lepton number and the individual family lepton numbers, right? These are broken, okay? And therefore, lepton mixing and CP violation are expected, right? Very good. All right. So now, of course, we can UV complete this Weinberg operator, meaning, so above the cutoff scale, we can write down the renormalizable Lagrangian, and it will have the following form, right? So what I have here is, I just consider one generation of standard model fields with an additional singlet, which is the right-handed neutrino, okay? So once I do this, I can write down the usual Dirac-Yukawa coupling, which is the second term in the Lagrangian. And the first term is the Majorana mass term for the right-handed neutrinos. Okay. So if Mn, meaning the mass term for the right-handed neutrino, is much heavier compared to the Higgs FEV, then you can diagonalize this 2x2 mass matrix and get the 2 mass eigenvalue. What you will find is the lighter mass eigenvalue is highly suppressed. Okay, so with this Lagrangian, in the new LNR basis, the neutrino mass matrix is given in that form. Okay, where in the off-diagonal elements, those are the Dirac masses, and the 2-2 elements, that's the Majorana mass term for the right-handed neutrino. All right. All right, so once you do that, once you diagonalize it, again, what you find is there's a heavy mass eigenvalue, which is roughly Mn, and a lighter mass eigenvalue, which is M Dirac times the ratio of M Dirac divided by Mn, right? So again, if the new physics scale Mn is large enough, then we naturally get a very suppressed effective neutrino mass. Right, so this is the so-called seesaw mechanism. And of course, what I discuss here is just one generation, but it's one can just generalize this to 3 generations very straightforwardly. And the complication there is, instead of dealing with one number, you have to deal with the whole matrix. And the seesaw can be realized, for example, in a sort of more unified gauge group, such as Lebesgue symmetric gauge group or Patti-Salam gauge group, or a simple gap model, such as SO10 or SU5, right? But SU5, of course, you have to adding the right-handed neutrinos into the model. All right, so here's another pop quiz. What is needed in order to populate that 1-1 entry with a non-zero contribution? Right, so previously I told you I just add the right-handed neutrino, I show you the 2 mass terms, and that give me this 2x2 matrix, right? So the question is, what would be needed in order to populate, make that 0 being non-zero? how do I get a contribution for the 1-1 entry? Any volunteer?
Yeah, yes.
Yes.
Okay, maybe just a diagonalize make this matrix diagonal and define some new engine vector.
No, I want to work in the spaces, right? So my question is, if I go back to the Lagrangian here, yes, I have these two terms that will lead to the 2x2 matrix.
Yeah.
All right, so far so good. All right,
yeah.
And my question is, what else do I need to add if I want to generate a contribution at the position where the 0 is? And remember, this is writing in the new L and R basis.
Which term you need to add into the Lagrangian?
Right. What additional ingredients do I need? Or what terms do I need so that I can generate a non-zero value in that 1-1 entry? Will be able to do it just with one right-handed neutrino and the lepton doublets and the Higgs, or do I need something else?
Just to make this non-zero, you need to add one more term.
Okay.
Which term?
I think maybe just add left hand add a Marana mass for left hand neutrino.
Very good. And how do you do that? Yeah, on the right track. How do you make that happen? How do you make a gauge invariant mass term, direct mass term for the left-handed neutrino? What do you couple the left-handed neutrinos to? Or the lepton doublets? We've seen that before.
A Weinberger operator for left-hand neutrino.
It has to be renormalizable.
Maybe just add a triplet Higgs or a scalar with the vacuum.
Absolutely wonderful, right? So it's a triplet Higgs. Once I have the triplet Higgs, that would give me a Majorana mass term for the left-handed neutrinos, right? And that, of course, corresponds to the 1-1 entry, right? So the 1-1 entry will be proportional to the vacuum expectation value of the SU2 triplet Higgs. Excellent. Does that make sense? All right, good. All right, so here again, this is a summary, right? If I have a standard model as effective low energy theory, then all the new physics effects are categorized by these higher dimensional operators. And it turns out that there is only one dimension 5 operator, which is the Weinberg and it is the Weinberg operator. So in a sense, neutrinos actually is the most sensitive place, right? It is the most sensitive operator to the high scale physics because this is the lowest higher dimension operator, right? So if I put in the measure delta m squared and take the square root that's give me 0.1 electron volt. So that's roughly the scale that we expect for the effective absolute scale of the neutrino mass of the neutrinos. If I put in 100 GeV for the Higgs fifth, and if I assume order 1 dimensionless coupling constant lambda, it turns out the scale for new physics has to be on the order of 10 to the 14 GeV-ish. All right. And of course, this scale is very close to the scale of grand unification. And again, given that Weinberg operator violates lepton number by 2 units, neutrinos are Majorana fermions. All right. So of course, there are many ways to UV complete the Weinberg operators, and various ways just get its own name, right? So the so-called type 1 Cecil mechanism, this is a Cecil mechanism, sort of the standard version of the Cecil mechanism, where the portal particle that UV complete the Weinberg operator is a right-handed neutrino. Okay, so I show that right there. Where the type 2 Cecil mechanism is the middle diagram here, where the SU2 triple Higgs is a particle that UV complete the Weinberg operator. The so-called type 3 Cecil mechanism, the portal particle is the SU3 triplet fermion. All right, and you can see how the diagram looks. All right, so all these three three type of portal particles and contributions, they are sort of work equally well in terms of their ability to UV complete the Weinberg operator. All right, I say that. And of course, for the type 1 Cecil mechanism, where right-handed neutrino is needed to UV complete the Weinberg operator, this can be embedded in the grand unification, grand unified theory very nicely. And in particular, this right-handed neutrino is predicted in grand unification, grand unified theory based on SO10. All right, so again, I think probably most of you already seen what grand unification is. Basically, the 3-gauge coupling constants of the standard model runs, right? And if there is supersymmetry, the 3-gauge coupling constants meet at one point. And that scale where the 3-gauge coupling constant meets is around 10 to the 16 GeV. And of course, in this framework, the quarks and fermions, they are unified into single multiplates, right? That's based on SO10. So in other words, in SO10, quarks and leptons within one generation are unified into a spinor representation, which is 16-dimensional. And so here, just give you the decomposition. There's 15 of them are the standard model, one generation of fermions, and the extra degrees of freedom turns out to be a gauge singlet under the standard model gauge group. And therefore, right-handed neutrinos is actually predicted if we go to SO10. All right. So now I'm going to just move on. I just address, right, where do neutrinos get their masses, the mass generation. But the remaining 10 minutes or so, I'm going to move on to address the flavor structure, okay? And I think I can, maybe let's skip this. All right, and the whole idea here is really, right, if I have, enhanced symmetry in my model, the symmetries would give rise to relationship, between the particles and between the coupling constants. And therefore, this would allow us to reduce the number of free parameters. In other words, there could exist relationships, among the observables that enabled us to test, such models experimentally. All right. So a popular scenario for addressing flavor hierarchy utilizing symmetry is so-called, it falls under the name of Fergat-Nielsen scenario. Okay. So this is a very sort of, should I say it? Simple is not the right word, but okay. So let's take U1 symmetry, right? The simplest symmetry that we have. And suppose the 3 generations of fermions, or leptons, to be more specific, carry different charges under this U1 symmetry. So depending on the charges, the U1 charges of the standard model leptons, and different generation of standard model leptons, each term I can make each term to be invariant under the U1 symmetry by inserting some power of the so-called flavon fields, which carry the U1 charge of -1. So this is a normalization. All right, so as you can see here, the NF here, this is the difference of the charges of the right-handed charge lepton and the lepton doublets, all right? Such that, once I include this S tilde field to certain power, this whole operator is invariant under U1, right? And of course, given that this is a higher dimensional operator, I need to suppress it by some power of lambda. And if lambda is if somehow this the vacuum expectation value of S tilde is slightly smaller than capital lambda, meaning there's a sort of a Mayer hierarchy, then this provides us a way to build a hierarchical mass matrix. Okay. All right, so he just give you one example. The hierarchical Yukawa couplings and non-trivial mixing angles make it generated by having different U1 charges of the standard model fermions across the 3 generations. And of course, if I gauge the U1 symmetry, then I do get additional very stringent constraints on the model. And that, because of the time, I'm just going to tell you the answer. Of course, those constraints are the anomaly cancellation constraints, right? So models are actually very, very tightly constrained. All right. So of course, more recently, due to the observed large neutrino mixing, there have been a lot of activities, trying to use discrete family symmetries to understand the observed large neutrino mixing. And again, this discrete family symmetry acts across 3 generations. Some of the symmetries that have been looked at are listed right here, like A4, T prime, S3, etc. And their geometrical interpretation. I put it in the parentheses. All right, so let me see. All right, so all these activities were actually motivated by something called the tribimaximal neutrino mixing. And if you remember, again, your classical mechanics, I think we all worked on this problem before, where I have a double coupled, I have a doubly coupled pendulum, right? So again, if they are uncoupled, x1, x2, x3, each of them can do the simple harmonic motion independently. But once I connect the pairs with a spring, then x1, x2, x3 are no longer, normal modes, right? But rather, the normal modes are linear combination of those 3 individual displacements. Right, so if you remember this problem that you worked on before, what I show here are the normal mode solution, right? So one is, doing this, right? and the other is all the 3 pendula just move together, and the third one has a 1, -2, and 1 phase. And somehow the solution turns out to coincide with the structure of the tribimaximal mixing matrix. So this is actually kind of neat if you make the connection. Okay, so this tribimaximal mixing matrix, this can be realized with the finite group family symmetry based on A4. So A4 is even permutations of 4 objects. And if you do some counting during your break, what you find is there are 12 such permutations. And therefore, it is a group of order 12. And geometrically, it is an invariant group of a tetrahedron. Okay. So again, the group is generated by 2 generators, T and S. T is a reordering of 1, 2, 3, 4 into 2, 3, 1, 4. And the second generator, S, is a reordering of 1, 2, 3, 4 to 4, 3, 2, 1. Okay. And the generator specified this set of algebra. So S squared is 1, ST cubed is 1, and T cubed is 1. And again, geometrically, this rotation or the discrete rotations about this axis that goes through one apex and one center over the face of a face of the tetrahedron. Of this 120 degrees rotation will lead the tetrahedron invariant, right? So all these rotations correspond to the group elements. And likewise, we have the other rotation that I show on the right-hand side. All right, so with the A4 symmetry, actually the model is rather predicted. Did I miss some slides here? All right, no. All right, so the outcome of the symmetry is the following. It gives rise to a mass matrix, neutrino mass matrix on the as shown right here, right? And what you notice is that in the mass matrix, the relevant strength of the mass matrix elements are described by only 2 free parameters, Cauchy0 and U. And all the rest of the numbers, the 2, the +1, and the -1, these are the Clebsch-Gordan coefficients of the group A4. Okay. And what's interesting about this is that regardless of what values of Cauchy0 and U assume, this mass matrix is always diagonalized by the tribimaximal mixing matrix, as you see right there. All right. So in a sense, the predictions for the mixing angles in this particular case are entirely group theoretical, right? Meaning it doesn't depend on any arbitrary parameters, but it's fixed by the group theory. And that's why, you know, this approach has generated a lot of attention, right? And of course, even though the mixing angles depends only on the group theory, the mass eigenvalues do depend on the free parameters Cauchy0 and U. But given that there are 2 free parameters, what that means is there is one relation. All right. So again, in this framework, it is possible to generate neutrino mixing angles entirely from group theory. All right. So the way it works is here's a model. To get that mass matrix that I show you, the 3 generations of the lepton doublets must transform as a triplet under A4. And the right-hand charge leptons transform as one double prime or 1 prime. So these are the irreducible representations of A4. The standard model Higgs, it is a pure singlet under A4, and the operator for neutrino masses are given right there, right? So I have the Weinberg operator, but I also make use of the Fergal-Nielsen mechanism, or Fergal-Nielsen-like mechanism applied to A4 symmetry. From the group theory, I know the 3 cross 3 give rise to the product rules of 3 plus 3 plus 1 plus 1 prime plus 1 double prime. And therefore, by picking up the triplets and the singlets from the HHLL, and then I can couple the whole thing to a triplet of flavon fields and the pure singlet flavon fields. And that's where the two free parameters come in, okay? So this is a model, which I know I go through like way too quickly, but just trust me, with this, you get the mass matrix that is shown right here, okay? And of course, you do the same for the charged lepton sector, which turns out to be diagonal, okay? All right, so, if you compare the prediction for the TB and mixing matrix, it mostly rather consistent with the data, except for the prediction for 0 theta 1 3. Okay, so again, this is just to illustrate, right, the robustness of the symmetry, right? With the symmetry, it allows us to, significantly reduce the number of parameters. And many of the interesting relations is just dictated by the symmetry itself, right? The properties of the group. All right, so I know my time is up. So just very quickly, just a few words. Very recently, a very hot topic is so-called modular flavor symmetries. But I don't have time to go through, so encourage to just look into it if you are interested. And again, this is a scenario which is rather robust. So just come to like sort of the concluding remark. So far, the fundamental origin of fermion masses and mixing patterns are still unknown. And I think, you are all young people, right? Students in the audience. So I think it is important to be patient, right? Because it took decades in order to understand just the gauge sector of the standard model that has only 3 parameters. And here in the flavor sector, we have actually a way bigger number of parameters. And therefore, it takes time to make progress. But on the other hand, it is important, right, to strive to have breakthrough in this regard, right? To really look for new solutions to address the flavor puzzles. Uniqueness of the neutrino masses offer very exciting opportunities to explore beyond the standard model physics. There are many new physics frameworks which allows both to address the neutrino mass generation and also other puzzles. And there may be also connection to early universe cosmology. And in recent years, we have learned a lot of new tools, new insights, and it may also enable us to find some phenomenological relevance of more formal theories. So I just mentioned this modular flavor symmetry, which actually have very, very strong top-down UV connection. All right, so I think I'll stop here, and if there are any questions.
Okay, we thank Professor Chen for the very pedagogical lecture. Any questions? It's super clear. Oh, there is a question.
Thanks for the very inspiring lecture. And may I ask, what if I add some new interactions, like flavor-philic interactions to the model, and how would that affect the oscillation of the neutrinos? For example, if I add a gauge boson only couples to muons or mu minus tau, and there exists a background potential for this gauge boson, then how would that affect the oscillation of neutrinos?
Right, so depends on, so you say this is flavor dependent So what type of couplings? I did not get that part.
For example, a new gauge boson, U1 mu minus tau,
very
or
good.
E minus mu, anything.
Right. So there,
Yeah,
because of the non-universal coupling, right? One has to let me see. Right. So because of the non-universal coupling, that of course would affect the mixing, and that's very model dependent. So I cannot tell you directly, right, how that would impact. But yes, if it's a the flavor non-universal couplings, then yes, that would impact also. So that's actually also one way to get contributions to the flavor mixing.
I see. Thank you.
More questions? Okay. Oh, there's another question.
So I have a question about the experimental search for the mass ordering. Why we can determine the new 2 heavier than new 1, but we can't determine whether new 3 is heavier than new 1?
Yeah,
it's because that previous. Is that because previous experiments are have some technological difficulties or something else?
Yeah, so the fact that's an excellent question. And that's a part that I did not have time to go through. The fact that we know nu 2 is greater than nu 1, that's because of the matter effect in solar neutrino oscillation. And because of the matter effects, we can determine, that nu 2 must be heavier than nu 1. But there's no such effects from the atmospheric part.
So in the future, like Juno and Dune also aim to measure the mass ordering.
Precisely.
But I have noticed that the Dune actually is a medium baseline experiment, and Dune is actually a very long baseline. So why these 2 experiments have different baseline, and they can also aim to the same ordering measurement?
Right. So let me see whether I have a slide. Let me see whether this is a good place. Just trying to find the slides that I have. Oops. I think, okay, so I think the best way to see is, remember yesterday we wrote down this 3x3 transition probability, right? Which is involving, the products of the PMNS matrix elements. So one can actually expand it, right, and write it in terms of the mixing angles and the delta M square, and so depending on, when one design the experiment, right, we always want to maximize the efficiency, right? So there's the energy of the neutrino beam that would be important, and whether we sit at the first maximum or second maximum of the oscillation. Again, that's also a factor in determining the baseline, right? And of course, there's also the yeah, there's a lot of echo. That's why I'm stopping every 5 seconds. All right, so once one include the matter effects, one has to also modify the oscillation, the formulation, right? Because the formulation that we wrote yesterday, that's in vacuum. So, so I think your question is, why do, this different experiment have different baselines and their capabilities are, they can measure similar properties? Was that the question?
Yes.
Right, so I think this is like a rather complicated. You really have to go in and put different pieces together to see it.
Okay.
Okay, if no more questions, let's thank Professor Chen for the 2 great lectures. Okay.
All right.
Thank you much.
Thank you.
Thank you much,
Yeah.
Professor Chen.
Yeah, and if there are any
you.
questions, you know how to find me. Just send me an email, and
thank
I
you.
will be happy to continue discussion. All right.
Okay. See you. Hope
See you.
to see you next year. Bye.
Yes. Bye.
Okay, let's take a few minute break. OK，谢谢。
您用那个，
好，
这个可以帮我，这个是满面的。
好。So I guess we still take a few minute break. It's too intense.
换了100C 的 PDF，然后我重新考了一次。
好。I guess so. Yeah.
Wow. So I went to this conference. They're having a Danish innovation conference. They have a Danish and coffees, and I stole some. Yeah. Yeah, I see. So we can go and I can go and have you can pretend to be Danish. I'm Danish. You're Danish. I want to be Danish. Let's say we are participating in activity. Yes. And I think it's oh, really? This is I recommend. We can try this. Oh, the tart? You want to be the French tart? It's impossible to get these things nowadays. Yeah. I didn't know you have. So you'll be here. So I just. I'll be here tomorrow, I'll be here till the end, and on Saturday I go near the hotel of near the place where the Chinese Academy of Science in Beijing.
Because I just
Do you know that?
yeah, but I just saw
What about you?
who's that guy? The Anthony is here.
Oh,
he's not in this building, but
he's there
in BIMSA, and he's staying in fancy.
But BIMSA, is it the National Academy of Science?
No, it's just next to this building, this campus, like 4 kilometers away. 4 kilometers north.
You mean not in this place?
No.
Another place. I have a new place.
Right, so I just took, and he gave a talk this morning, and he's staying in Kapinski Hotel, which is a really fancy hotel around here.
Yeah, but he's in Dubai.
Dubai?
Dubai, yeah.
He didn't tell me.
I'm not so sure.
He said he's in Nodida.
No. Oh. But you will stay here for a while, or in China?
I started my job here. I got retired. So I'm here for 5 years.
You have a job here?
5 years.
They give jobs like that. But you have to be in this area or in Beijing?
From north.
At north?
Just 4 kilometers away. But I have to go to Beijing teaching next semester twice per week.
Yeah. Anyway, this retirement is absurd. This thing of retirement is absurd.
What over time?
The fact that at 65, 60 people have to retire.
No,
makes no sense.
Well, but if you go to state, and it's all professors say, oh, then the young guys don't have jobs, and that's absurd again.
They wouldn't have more jobs, or less or more. It's just it's a prejudice by age. It makes no sense. It really makes no sense because, first of all, you have young people who are idiots. I mean, it's not the exclusivity of old people. Okay, so anyways, and the family is around?
Yeah. My wife is here.
Does she like it?
We are adjusting. We are adjusting. But we are very grateful that we have this opportunity.
Oh, you already have the microphone. Okay. Is your one? Okay. So let's continue the winter school. So the second lecture of this afternoon session is again given by Professor Kim Yong Lee, who will continue the discussion on solid tones. Let's welcome him.
Okay, so I don't think we are not allowed, but there's other conference on innovation with the Danish and coffees over there, but you can speak in, I guess. So I was talking to a guy, one of the guy, and he said, oh, he's in Tianjin Juilliard Music School, where he came here, attended a meeting, and then he was inviting me to come to Tianjin to hear the classic music. So I said, thank you, but no thank you. Going to Tianjin? No. But anyway, so yesterday I talked about few solitons. So today I'll talk about little more about anyons, because anyons are so fundamental in many ways, condensed matter physics and theoretical physics and mathematics. So those theories arise from very simple observation in 3D, where one can have not only Maxwell term for kinetic energy for gauge field, one can have Chern-Simons terms. And when you have Chern-Simons terms, Gauss's law changes completely. Gauss's law is a sort of constraint you have to enforce on the physical system, which comes from variation of A0, which is not dynamical variable. It's like Lagrangian multiplies. And so it generates constraint. And Gauss's law says if I have charge, I have flux. That's the Gauss law. So you are making charged particle to be composite of charge and magnetic flux. And with that, because of you have charge, and if you have magnetic flux, then you have current, so you can define the angular momentum. And also with specific potential, you can have a bound on the energy given in terms of magnetic flux. Then one can have some vortex or cuboids in depending on whether you are in the symmetric phase of potential or broken phase of potential. In this case, you have 5 to the 6 potential, so you have two degenerate vacuum, symmetric phase and broken phase. All right. So symmetric phase, you have a charge given in terms of some phase. It's not vorticity and flux, and they are related by Gauss' law. And broken phase, we have a magnetic flux vortex, which is related to vorticity of scalar field, and flux is quantized by 2 pi n, and the 2 pi is like a minimum Dirac flux, which you cannot observe using the charge one object because around form phase is trivial. And then you have charges also quantized. Now, if you calculate the angular momentum, then interestingly, sign changes depending on symmetric phase and broken phase. So especially when k equal to 1 and q equal to 1, so that's minimum charge and the minimum Chern-Simons level, then angular momentum in symmetric phase is 1/2. And broken phase, k equal to 1 and the flux is, say, 2 pi, which is k equal to 1, then again you get angular momentum, but minus 1/2. So half angular momentum minus 1/2 angular momentum are fermions. So broken phase fermions are possible, but not anyons. But symmetric phase, you can have anyons or fractional spin. If k is bigger than 1, then spin becomes 1/2k, which is smaller than 1/2. Now, interesting thing is, we just calculate angular momentum using the specific potential, but we don't need to. We can angular momentum is nothing to do with shape of potential, so we can think about k equal 1 Chern-Simons theory with lambda pi 4 interaction, forget the 5 to 6 interactions. In which case, in 3D, lambda has a dimensional mass because pi has dimension of mass to 1/2. So pi to 6 is dimensionless, but dimension 3, but pi to the 4th is mass square, so lambda has to be mass dimension. And then effective coupling, if you do Wilsonian running coupling constant, then in IR, this effective coupling goes to infinite, such a way that there's and the lambda pi 4 with plus 4 plus lambda is a repulsive force between particles, and this contact interaction between particles, which is 4-point interaction, goes to infinite. Turns out this theory, because k equal to 1, as I said, in symmetric phase, we have spin 1/2, and broken phase, we have spin minus 1/2. So it's sort of 3D Dirac fermions. And the Dirac fermions, you cannot be in the same state because of Pauli exclusion principle, and that comes from the IR that lambda runs to infinite. So contact force is infinite, which means the two particles cannot be on top of each other, so which is Pauli exclusion principle. So very simple calculation tells us that k equal to 1 Chern-Simons theory with this IR Wilson Fisher fixed point of this theory is identical to 3D massless Dirac fermions, especially if you go from, say, positive mass to negative mass, in which case, positive case, you have sort of cuboid type of object, and the negative mass, you have a vortex type of things. And this physics is equivalent to fermionic mass added to it, where fermion mass, if it's positive or negative, in 3D, this one changes the spin of the fermions. And because it is parity order terms, such a way that bosonic mass square, I mean this parameter m square, can be positive and negative, and that's equivalent to the fermion mass being positive and negative. So this is amazing duality between fermions and bosons. So this is the place where Chern-Simons term added to scalar field becomes a fermion. It's free fermion. And this simple duality between fermions and bosons has been generalized to a lot more cases by including additional interactions. Now, symmetric phase, I said anyons are possible and with fractional spin. And if you look at the anti-anyons, which has opposite charge, then because speed, angular momentum was proportional to the square of the charge, both of anion and anti-anion has the same spin. But if you look at spin statistics, then two anions have fractional spin statistics because they have fractional spin. And if you look at fractional statistics into it account, then orbital angular momentum becomes 2m plus 2s. So especially if S and S is 1/2 fermions, then we know orbital angular momentum has to be odd integer, so that you cannot have angular momentum 0, which is which makes two particles on top of each other. So that's the right statistics, and you can calculate this using around form phase of quantum mechanics between two particles with flux and charge, and that generated this fractional orbital angular momentum. So total orbital angular momentum is 2m plus 4s. And remember, this fractional part of previous calculations show that is proportional charge square, and in this 4 is 2 squares. That's why it's 4. So spin and orbit together is 4s. On the other hand, if I have anti-anions, then I say the same spin, but anti-anion has opposite electric and magnetic flux, which means that around form phase is opposite to this guy. So orbital angular momentum becomes 2m minus 2s. So if I sum all the angular momentum, there is a 2 times integer. And of course, we know if I particle and anti-particle means I should be able to annihilate them into a vacuum, right? So total angular momentum should be 0. And this case, very nicely, orbital part cancels the spin part of it so that you can annihilate. And anions are supposed to appear in the fractional quantum Hall effect. We don't know much about this, so let me just show the pictures. There are experiments, there is observation, lots of Nobel Prize has been given, and I don't think people have observed the anions yet. And if you observe certain kind of anion, especially non-abelian anion, which we haven't talked about, then that will allow us to do quantum computer calculation, and that will allow us to much more stable quantum computers. But people haven't observed the non-abelian Fibonacci anions yet, but those will be also a really amazing breakthrough. So this is quite often an interesting field. Now let's go to magnetic monopoles. So magnetic monopoles are proposed in late 19th century by Pierre Curie, who is the husband of Madame Curie, and then also by Henri Poincaré. I guess both of them are two French scientists. And magnetic monopole is similar to electrons, where you have a magnetic field that comes out from monopole uniformly. And so divergence of magnetic field is just delta function at the point. So if you have a charged particle moving along the distant magnetic field, then the equation of motion, Newton's equation, will be this. And because the magnetic field is uniform, there's no rotational symmetry is still preserved, so there is a conserved angular momentum. And using equation of motion, you can see that conserved angular momentum is not ordinary r cross mr dot, which is mass times the velocity, which is not conserved, but this combination, including r hat, is conserved. And you can see this one is Eg electric charge times magnetic charge by 4 pi. And basically, if I have a magnetic charge and electric charge, then magnetic charge comes in, and magnetic field and electric fields are coming in from two particles. And then E cross P, the pointing vector, is going around this r hat, and that generates this angular momentum. And that's how you can calculate this using pointing vectors. So this part of angular momentum is carried by electromagnetic field, and the equation of motion knows about this. So because this one is conserved, so suppose I have angular momentum direction, then you have particle point somewhere. Then if you make an inner product of this object, then you can see R hat and the orbital part is vanishing because the orbital part is R cross MVR dot. So this inner product will be just constant, which is easy over because it is direction, so divide the total angular momentum and that fixes the angle. So once you have angle there, then particle comes in, then make a, it's always angle is conserved, so which means the particle is always moving on this conical shape, and particle electrical charged particle comes in, goes around, and comes in and goes around, and goes up along the cones. So this kind of motion of electron in approximately happening in North Pole. So in North Pole, I mean, South Pole is far away, right? So North Pole is almost like a magnetic monopole. And then there are solar wind you heard of comes in. Then solar wind comes from far away, then make a conical shape, then goes up. And then when they are accelerating this, they radiate light. That's aurora. So aurora comes from this motion of the charged particle around the magnetic monopole. When it goes out, that's light comes out, and that's the aurora. Now, to do quantum mechanics, you have to introduce vector potential. So one of gauges you put the, because once you put a vector potential and then you write down the magnetic field as a curve of the vector potential, then divergence of that magnetic field is equal to 0. So you have magnetic monopole, then there cannot be, you need some solenoid coming which supplies magnetic field. And so this configuration has a solenoid along the south pole of the origin, because that's the place where theta equal to -1, cosine theta is -1, so then that's the place where d phi is not well defined. So there's a solenoid along the south, and that's called the Dirac strings. And this solenoid is unobservable if the Aronoff form phase around the solenoid is trivial, which means that this product has to be quantized. There's no electric charge times magnetic charge, it should be 2 pi times integer, which means that if we have a magnetic charge somewhere in the universe, all the electric charge has to be quantized in terms of this magnetic charge. And this is one of the explanation why protons and electrons, they all have the exactly opposite charge. And this, of course, is consistent. And the people haven't seen the magnetic monopoles, but it should be there. So detail of there's Tufte-Polyakov monopole, which I'll talk about a little bit later. But in standard model, there is no Tufte-Polyakov soliton magnetic solution, monopole solutions. On the other hand, because of gravity, we can have a magnetically charged black holes, which is in principle possible, which allow us to quantization of electric charge. And if you look at the combined system, then you can see when EG product is 2 pi, this orbital, this field part is 1/2, because 2 pi over 4 pi is 1/2, which means that conserved angular momentum is really half integer, so which means fermions. So you can make a fermion out of two bosonic particles. With charged particle with magnetic monopole, you can make a fermion. So previously we had the Chern-Simons theory where we with Chern-Simons level 1, where we had a fermion coming out of the magnetic flux and charge. Here we have monopole and electric charge, but their product is quantized to be 2 pi. Then angular momentum is 1/2 plus integers. The orbital part becomes integer, which means that total angular momentum is half integer, so it's fermionic. So magnetic monopole soliton appears when we go to the higher gauge groups, like SG2 gauge series, where we have scalar field which belongs to adjoint representation. So is coupled to the SU2 gauge field in this non-abelian manners. And then there's field strength and the scalar field kinetic term and the potential terms. So especially if we have the potential where SU2 is broken to U1 because the scalar field has expectation value, magnitude is V, three-dimensional vector with magnitude is like a 0, V kind of a field. We can take expectation value, then we break SU2 to U1. So naturally, in low energy, there's U1 symmetries, and then massive W bosons, the Higgs particles are there. So in this case, group vacuum manifold is a two-sphere because scalar field magnitude is fixed. And then if you look at some profile of scalar field, and you go to R equal to infinite, and then in space it's R3. So if you go to infinite radius, then it's a two-sphere again. As a map from two-sphere to two-sphere, vacuum manifold, you can have a non-trivial winding numbers, which is second homotopy group. And with these configurations, you can have a non-trivial magnetically charged monopoles. So for example, if we have a spherical symmetric case where this winding number is 1, so phi goes to some radial directions with some magnitude depending on R, then we have a gauge field again with the internal rotation, SU2 rotation, and also spatial rotation. One can have this invariant ansatz. And then we are looking at the configuration which minimizes the energy, and especially if energy potential is equal to 0, then we can combine magnetic field part of it, because we are not looking at time-dependent one, so electric field is equal to 0. And space derivative, we combine them together, and then we have this cross term. And using this expression, we can give a bound on the energies. And the energy is bounded by magnetic flux. And this bound is saturated when you have this equation is satisfied. So magnetic field is proportional to covariant derivative of scalar field. And with this ansatz, we can solve the equation. And here's the solution. So mass of W boson is G times V, and scalar field profile and the magnetic field gauge field profile is given that. So you can see cotangent type. So if you go to R goes to infinite, then this goes to constant 1, and this goes to 1 over R. So scalar field falls off very slowly because there is no potential. And then magnetic field, this part falls off exponentially. So if you look at, and if you go back to this expression, then there's one left which generates the magnetic field or monopoles. So in this case, the energy is bounded by total magnetic flux, and that mass is given by 4 pi V over E, or coupling constant, which is MW over E squared, 4 pi E squared, and which is MW over alpha. And alpha is E squared over 4 pi, which is a fine structure constant of this SU2 gauge series. Now, later on, I'll talk about additional term in the Lagrangian, this theta FF dual coming from instantaneous effect. And then this theory, especially when you have supersymmetries, can written in terms of complex coupling constant, not a single coupling constant, but theta and 1 over G squared combine into this very nice modular parameters. Theta over 2 pi plus 4 pi over G squared. And this complex coupling constant generate with these theta terms something called the Witten effect, which means that magnetic monopoles have a fractional electric charge proportional to these theta terms. Well, that's not that typical to derive this. And also, especially if you want to detail, you can look at my lecture note in the on solitons, which I gave in BIMSA. And the best term for this PPS object is coupling G or E, V times NE minus tau NM. And it turns out with the electric and magnetic charge given in terms of two integers, NE and NM, and then especially if I have a non-magnetic, non-trivial magnetic field, then this generates through the theta terms Witten effect. Now, if you go to maximally supersymmetric case, which is N equal 4 super Yang-Mills theory, which means that not only you have a KG field and this scalar field which belongs to identity representation, you have a fermionic field, and also there are 6 scalar fields to have supersymmetries. In this case, one expects SL2G symmetry, which is transformed coupling in using SL2G elements, which is where A, B, C, they are integers, and AD minus BC equal to 1. So this huge transformation, and coupling transform imaginary part of tau transform specific way, then you can see a coupling constant transform in these manners. And especially you transform electric and magnetic charge same way, then PPS mass term, which is G, with this combination is invariant under these transformations. This looks highly complicated. Simple part is this SL2G made of the generated by this S transformation and T transformation. T transformation is just changing the electric charge of monopole by T is like 1, 1, 1, 0. So you are just transforming electric charge or magnetic monopole shifting by the magnetic charges. So that's very simple transformation on dionic magnetic monopoles. Now, S transformation is one exchange the electric and magnetic charge. And this is related to Maxwell theory, where if you learn the Maxwell theory, when you don't have electric sources, free Maxwell theory is invariant on the exchange of electric and magnetic field. E and B goes to Bm minus E, then Maxwell equation is invariant. That simple dual transformation between electric and magnetic field is now allowed to include the sources, because in n equal 4 super Yang-Mills series, not only we have electrically charged particles which comes from perturbative W bosons, we have solitons like magnetic monopoles. And so we have a magnetic source and electric source, and they are transforming each other through this transformation. So SUN KG series is invariant under this transformation, but if you look at the generalized symmetries, like then there's an additional interesting transformation between SUN and SUN over ZN. But if my KG group is SO2n plus 1, then this theory, when you go to say weak coupling, then W boson is very light and monopole is very heavy because they are non-perturbative. But if I go to very strong coupling, W boson is very heavy and monopoles are very light. So you want to say, oh, monopoles are W boson and the W bosons are monopole, kind of solitons. So you want to reverse their roles. And to do that, you make a S transformation. But in that case, S transformation is a little more complicated. But when you change it, KG group changes from SO2n plus 1 to SPN. So this is called Lang-Lens dual groups. So Lang-Lens dual, Lang-Lens program, maybe you heard in mathematics, where that's one of the very interesting physics and math problems, and there are a lot of progresses. But the key origin comes from this simple duality between electric and magnetic charges. So abelian cases, you can just exchange with S transformations. Now different groups, you go from different groups. These two groups are called the Lang-Lens duals. So monopoles doesn't appear in real world, not yet, but mathematically and physically it gave us a huge new understanding of the theories, and also opened up many new interesting ideas. Right, so any question about monopoles?
For the U1 theory, the
Yeah.
monopoles is not a field configuration, right? It's the elementary particle values.
U1 theory, as I say, in quantum mechanics, in field theory, we are describing, this one is elementary particle, this soliton. But when you look from the, say, quantum mechanics point of view, we are doing semi-classical description. But if you go to quantum world, it doesn't know whether it's elementary particle, whether it's soliton, right? So you quantize it, and that's the quantum object. So U1 theory, and here SU2 gauge theory broken to U1, then there's no difference between monopole and W boson in that sense. So. Any question about monopoles? All right, sorry, so I have to go over very quickly. Now let me go over to instantons. Oops. Yes. Instantons, axions, and sphelerons. And axion is not solitons, but speleron and instantons are sort of solitons. So let's think about SUN gauge theory again. Forget the monopole, so forget the matter field. And then we want to quantize the Z theory. So if you look at F mu, then F mu has a time derivative of AI, space component, then A0 has no time derivative. So A0 generates a Gauss law constraint. And so, and also conjugate momentum of AI is conjugate momentum is just AI dot over G square. They're all n by n matrices, and there's a trace. And normalization, I just ignore it except the coupling constant. Then we can write down this Lagrangian in terms of first order formalism, Lagrangian in terms of px dot minus the Hamiltonian. So something similarly, we can write down this Lagrangian this way, and the Hamiltonian density will be electric field square or pi I square plus magnetic field square. And then we have A0 with the Gauss law constraint. Now, so we want to quantize the theory with A0 equal to 0. We impose Gauss law constraint on the system or on wave function. And then we want to quantize this Lagrangian or Hamiltonian. And especially we want to look at what kind of vacuum we have. Vacuum means magnetic field strength has to be 0, which means gauge field has to be pure gauge. So that's the vacuum, which means pure gauge. Now, let's think about something a little different for a while. So instead of thinking about F mu, let's think about F mu tilde. F mu tilde is dual field, which is epsilon mu nu rho sigma 1/2 times F rho sigma. So that's like electric field is magnetic field, and magnetic field is minus of electric field, dual transformation. So F tilde mu is dual field. And this combination turns out to be total derivative, is topological terms. And total derivative of this expression, this is like if we put mu equal to 0, then spatial component will be Chern-Simons term, non-abelian burden of Chern-Simons term we talked about. And yeah, we are in 4 dimensions. Yeah, we are in 4 dimensions. So when mu equal to 0, spatial component is like.
You want everything that you say is specific to 4 dimensions.
Yeah, I'm specific 4 dimensions. So if you go to higher dimension, the instantons play different roles, especially in 5 dimensions. They are solitons, not tunneling solutions. Now this guy is total derivative. And this is total derivative of this current density. Now, when gauge field is pure gauge, if you calculate the charge density 0, this charge, then we add this specific configuration with pure gauge, then this integration, because it doesn't need to be 0, but this integration is given in terms of expression pure gauge to the cube, and the normalization changes to 1/24 pi square, and that's n to the u. That's the winding number of the R3 to SU2 or gauge group, UN, SUN. So this is the winding number of the pi 3 over G, which means the map from R3 to Lie group. And remember, yesterday when I talked about scomions, I said that this pion field U is SU2 element, and there is a non-trivial winding number from R3 to SU2 element, which is group manifold is S3. So S3 to S3, there's non-trivial winding number, and this is exactly that number capturing the non-trivial map. But this winding number not only captures a map from R3 to S3-2, but R3 to any Lie groups. And it turns out all those cases, this number comes out to be integer. So you can see there is a skyrmion-like object for any Lie groups. Right. So we are looking at the ground state. So let's think about the vacuum with winding number n to be some state n, and let's superpose this state with some eigenvalue of the translation between different winding numbers, and let's say that with theta, which is a combination of this vacuum with phase n. Then we are looking at the expectation value of the time evolution between two theta prime and theta. And through the manipulation of the gauge invariance and shift, one can show that this is proportional to delta theta prime minus theta. So there's no, whatever time evolution you are doing, you cannot change the value of theta. And then you have a sum of the k with different winding number between 0 and k. K is all the integer, then you put a phase e to I k theta, and the e to minus iht is the relation between them. And now this configuration can be written in terms of path integral, where we are integrating over the gauge field where initially gauge field is pure gauge, a equal to 0. Then when you go to final configuration as winding number k, then we have this path integral. So this k is change of the winding number in the sense that if we integrate over T4x over trace of f mu and f mu tilde, I said that that's the at the boundary we have a winding number. So this is the integration of time integration of the 4-dimensional J0 and the time derivative of J0. So it's a difference in charge, which is winding number charges. So which means that if we do look at this sum over k, then k times I theta is like k is this topological terms. So this term is similar to adding in this path integral, adding this topological term, theta over 16 pi square trace f dual. So one can see that this time evolution of the state between theta and theta prime can be written in terms of this delta function plus path integral with original Yang-Mills coupling plus additional theta term, space integration of that. And then we integrate over all the gauge field where we don't impose any constraint on the winding number, initial and final winding numbers. So you can see naturally, if we think about this theta vector, then our Lagrangian is not Yang-Mills theory, but we have an additional term, complex Lagrangian with two coupling constants, Yang-Mills coupling and the theta term together. And then, of course, we are interested in the Euclidean time case because it's tunneling between different winding states through some non-trivial configuration. So we want to know how vacuum energy is shifted in Euclidean time. And so we look at the Euclidean path integral. So here, without I, then large T, it will capture the vacuum energy shift. So that will be given in terms of Euclidean path integral with this imaginary path. Right. So we are interested in vacuum to vacuum. Yeah.
So in the next slide, so that delta theta prime minus theta.
Right.
I mean that.
Yeah.
So means two different theta vacuum can't transit.
Right. Right. So it is the like super selection sectors. So because of this infinite degeneracy of vector, you can have this translation invariant state theta. Then you cannot, if you have one given theta vacuum, then you cannot go to another theta vacuum. So that's why it is coupling constant. So it's additional parameter naturally appears when you think of the quantum mechanics of Yang-Mills theories. Right. So we want to do this path integral. Means we want to look at stationary points of this Euclidean action. And the Euclidean action can be written in terms of f mu nu square is f tilde mu nu square. So we can combine together, divide by 2. So it's 4g square. Then f mu nu and f mu nu tilde squares, we can put into a single bit. And then we have cross terms. So with two different signs, then here's plus and minus. Now this is remember 1 over 16 pi square times that quantity is this zeta terms, or that gives a change of the winding numbers. So this will be 1 over 16 pi square g square, and then there's the 8 pi square. So together it generates a bound on the action. So when this is equal to 0, action will be saturated, and that bound is 8 pi square over g square times integer k. And k is the one when you integrate over this at the boundary, because it's a total derivative, that captures the winding number of the gauge field at the special infinite. So k is integer, which tells us that it's called the instanton number. So that counts the number of instantons or number of winding number changes. And then this instanton satisfies self-deallocation when k is positive. And if k is negative, then there's minus sign, and they are called anti-instantons. So solution of self-deallocation, which is highly non-trivial, and people have studied quite extensively, and is called self-deallocation. And for k instantons, and if you solve it, then there are 4kn zero mode for SVN gauge theory with k instanton. So if you have single instanton in SVN theory, number of zero mode is 4n. Among them, they are all PPS bound. They are saturated bound, so they are stable solitons. And out of this 4kn, 4 will be the center of the mass position of these instantons. And 1 will be the overall scale of the object, because turns out 4D Yang-Mills series has scale invariance, which means I can make an instanton of any size. And to be more specific, let's look at SU2 single instance solution. Then form is explicitly given. I will not explain this 2 tensors symbols, but the gauge field can be written in very nice form. And lambda is a scale. And here we put the instanton at origin, but we can shift the x to x minus a, xa, x0, or x minus x0. Then you are shifting instanton to any positions. And so SU2 case, number of zero mode is single instanton is 8 zero mode, and so position is 4 zero mode, and scale is 1 zero mode, and then 3 comes from rotation of this instanton in SU2 space. And field strength is more localized, and you can see that it falls off much quickly, and the field strength also scales like lambda square. Now you can calculate the instanton contribution to partition function, and those are called the instanton partition function. And this has been studied very, very extensively, n equal 2 series, and that's called the Nekrasov partition function. And it's made of the perturbative part plus the instanton corrections, and there are many different ways of writing down, and especially in 5D gauge theories, which I don't have time to talk about. If you think about this one, and with -1 to the f, you count the PPS object or Witten index, in which case there is no space-time volume appears, but that counts the really PPS object, and those are called Kopakma-Vapa invariance. And there is a lot of extensive research going on this instanton partition function for last 20 years. But here we are merely doing QCD. So we are looking at the shift of the vacuum energy. Remember, we are looking at large T limit. Then naively, there is a perturbative part around the trivial vacuum. Then there is single instanton contributions, and it has a lot of zero modes, so you have to integrate over scalings and so on. There are additional subtleties. But ignoring that, there's the exponential suppression factor coming from instanton mass or action. And then instanton and anti-instanton generate potential e to the I theta and e to the minus I theta. Together it generates cosine theta. And there is a free factor which is related to one loop. So you can see theta vacuums, it is super selection sectors, some parameter of coupling, and they have a different vacuum energy depending on value of thetas. And also this violates CP violation terms. And QCD, I mean, naturally you would say theta can be any value from 0 to 2 pi. But QCD, from the analysis of a neutron electric dipole moment, theta turns out to be less than 10 to the minus 10, extremely small. And that's called the strong CP problem in QCD. And now you can couple the fermion to this series. So suppose we have some flavor of fermions, matrix Dirac fermions coupled to gauge field. Then this one has a lot of symmetries, flavor symmetries. If we have NF flavors, then SU, NF left and right flavor symmetries. And also additionally, there's a baryonic number, U1 baryon number charges. And also there's axial symmetry, which is related to gamma 5. So because they are matrices, so we can have left and right fermion transform differently. So you can insert gamma 5. And this current is classically conserved with this Lagrangian. But through the triangle diagrams, one has anomalies proportional to trace F mu and sorry, this F mu tilde. So it's related to this instanton number.
You need to have asymptotic freedom
for this
to do things in a meaningful way. Suppose you have too many fermions, then you lose asymptotic freedom.
Right.
And does it hurt that you're going to set at instantons?
Yes, in a way, because right. So of course, so I didn't talk about asymptotic freedom, but if your theory is not asymptotically free with a lot of flavors, then UV physics is not well defined. So you have to add additional information. Maybe in UV your gauge group is bigger, and then again it will be asymptotically free, so it's well defined. So you can leave it as it is. Then low energy, you have to think about again instantons. Then of course, if you have a lot of fermions, then this anomaly calculation is nothing to this number of flavors. So only when you do one loop, no, this one doesn't care. But if you look at the beta function, of course it cares. So when you do instanton corrections, one loop corrections, beta function appears very naturally. So when you integrate over scale of the instantons, maybe it will affect it. Because scale means you are looking at short distance or long distance physics of the series, and then whether it's not, if asymptotically not free, the UV physics is not well defined, so you have to provide some ad hoc corrections.
You know, in these extensions and so on, do you expect to have something like the vivid gas approximation?
Yes.
Which of course is only valid.
Right, only valid when instance is small, right? So again, I don't have time, but when you integrate over instantons in IR, again, there is some divergence when instantons are overlapping each other. So instanton physics looks very nice, but it becomes very murky because of dielectric approximation breaks down. And also there where coupling is very big, means the instanton, which was action is like 1 over g square, which is very, very big if g is small. So weak coupling, instanton effect is suppressed. But when go to strong coupling, instanton effect is not suppressed because g becomes big. Then you don't know what to do. So I heard from cynical theorists from QCD expert, there's no evidence for instantons in QCD physics. But I'm not expert, so I know the instanton is there, but people have been always trying to narrow down this is the instanton effect, this is the Meron effect, and so on. But instanton physics always have been murky unless you have supersymmetry where it's so well defined. but still, we don't need to give up. I mean, we can give up today, but tomorrow we don't need to give up. So we are always imagining whether we can do something interesting about instantons. And recently, I don't know, you guys noticed, there's a faculty at Tsinghua University IAS. He wrote a paper on instantons on lattice. That seems to be also quite impressive. So, you know, ambition is endless. And one wants to, again, capture the instant of physics unambiguously and present to this experimental fact is due to instanton, and that would be really nice. Right, so, what? So, right, so number of fermion changes related to, because this oh, it's okay. Right, so because of this conservation laws, we can see this total derivative is a change of winding number or instanton number, and then there's NF, and then there's factor 2, and then this side is the change of the left-handed fermion minus the right-handed fermions. So it generates this chirality violating interactions with the instantons. So there's some effective action generated by instantons, and that is also important part of the physics. But I'll skip that. All right, thank you. Right. So I said that QCD, so theta term, theta parameter, which is complex coupling constant, should be very, very small in QCD because neutron dipole moment is very, very small. You measure it, and from there, you compare the theta term contribution to neutron dipole moment, and that leads to theoretical prediction that theta should be less than 10 to minus 10, even though theta can be between 0 and 2 pi. So nature acts always strangely. You thought you nailed down and you're happy to discover the neutron dipole moment. You measure it, it's not there. As if I'm almost there. What is it? There's a famous movie, if you catch me if you can, kind of thing. So nature is telling me I'm instanton, theta term is there. So you want to catch it, then it disappears right in front of you. So this is the theta term, so nature disappeared right in front of us, and we thought we can capture it, but it's gone. So we have to find the answer why this guy is so small, even though it's allowed. And this was, I guess, one of the initial people who come up with the Pachai and Quinn, two physicists in late 80s. They come up with some new idea where you have some neutral scalar field, I use the same phase, theta, because that's related to theta term. It's a space-time dependent field, which is coupled to gauge field in this way. Not fermionic field, but fermionic yuan part of it. So, and then you can imagine the integration of, now fermions are massive, so you don't have chirality, but you have still chiral yuan transformation, because if I rotate the fermion by chiral transformation, I can just shift the theta by constant amount. So yuan axial symmetry is still there through this transformation. Then if you integrate over fermionic field with instantons, then you generate, because of triangle diagrams, you generate now interacting term where theta x trace f as f. Remember this total derivative, but now phase constant is become dynamical. Or theta x, theta 0 is shifted to theta x plus theta 0, but the constant term can be always observed by shifting the theta dynamical variable. So this axial field, this now theta becomes dynamical field. So if you choose, if you can make this dynamical field to be vanishing, then you solve the strong CP problems, because before it was some super selection factor, some coupling constant, but now it's a dynamical field, and it can change itself. And if it runs to 0, then well, there's nothing to. Oh, here is kinetic term. Here is kinetic term. Right.
So it's kind of
right. Yeah, it's like Green-Schwarz mechanism. So, so this field is called the axionic field. Now, the instant calculation is in UV, where there's no pions and no strong couplings. But you can calculate the axion mass from pionic dynamics and also Kwong masses. And roughly, in high energy, I just wrote down the instantaneous effect, and the instantaneous effect is like cosine theta 0, but theta 0 becomes shifted to cosine theta plus theta 0. And so you can see minimum of this potential means that this term equal to 0 or pi or something, which means that's the place where CP is not violating. So you solve the strong CP problems by introducing this dynamical field. Or you can go to low energy effective potential in terms of pionic dynamics. Then you get a complicated expression from which you can calculate the axion mass roughly, and the axion mass, and roughly because of observation effect, there's this FA, which is related to symmetry breaking, which generates axion field. And if it is 10 to the 12 electric volt, it's very high energy, then that's electron mass is 6 micro electric volt. And I guess this is a very small number. I think GeV. Right. I think I missed that factor. Yeah.
Can you wrap up in a few minutes?
Yeah, no problem. Right.
Already a little bit over time.
Oh, you should have told me 5 minutes ago that I could have done it. So anyway, turns out that's not end of story. Electroweak theory, SU2 cross SU1 theory has instantons, but because of Higgs mechanism, it's a little subtler, and the instantons changing winding number. Instead, you have this semi center point, which is called the sphelerons, and the speleron has the instanton number 1/2, and that plays a role in baryogenesis. And the people have been studying these sphelerons quite extensively for last 30 years. And still it's an important part of the baryogenesis in cosmology, where why there are more matters than antimatters. Right, so this is ultralight scalar and stars. There's nice YouTubes. And we know there is a dark matter in our universe. Our universe is, our galaxy is this small. And then if you look at the some of stars near our galaxy and how they're moving around, then this observes the rotational velocity. And that's the expected velocity, which means that there are a lot more matters around us, around our galaxy, especially dark matters from different Planck satellite experiment tells us that 26% of matters are dark matters, and the ordinary matters are only 5%. So if we have our galaxy, then there is a dark matter halos. So we want to look at this nature of the object. It's not observable. It's not baryonic. What is this? And I start from Sapronova's talk, landscape of dark matters, and people have been studying WIMP, weakly coupled massive object, and it doesn't work well. And then you go down, and the shooter place seems to be between micro electric volt to 10 to the minus 22 electric volt, ultralight particles. And only natural particle candidate is action or action-like object, which arises from string theory. So this ultralight particles are kind of one of natural candidate for this Tang methods. So here is axionic field, which is very light. So that's very natural Tang method candidate. And it's very simple to understand how this Tang method arises. You just have neutral scalar field, Bose condensation, but this potential between them just comes from the gravitational attractions. And gravitational attraction is coming from self-generated mass. And so from this Bose condensation, one can have a star. And this star supposed to be side of the much bigger than our solar system, maybe like a light year size. And such big stars are floating around in our galaxies. And those are so light, so faint. If it's going through you now, you wouldn't know it. But those becomes a highly attractive Tang method candidate, and people have been studying this. It's some sort of QBAR with no charge because it's neutral, scalar field, massive, self-grading Bose condensation. It's like axionic field, and those are like oscillating classical field inside. And people have been studying this object for last 10 years quite extensively. So let me conclude. So solitons play a very, very important role in 4D theories and also higher dimensional quantum field theory and string theory. And also there are some solitonic objects, a little different, which you call the TFX, and which I don't have time to cover. But the solitons captures non-perturbative physics. Remember, most of physics you do Feynman diagrams and perturbative calculation, but solitons are highly non-perturbative, and they give us a new insight on the physics, especially duality between various series, where solitons are playing important role, like fermion-boson dualities and magnetic field and electric field dualities and so on. So solitons are still quite interesting objects to think about. Thank you.
We thank Professor Lee for the very pedagogical and very thorough overview of the soliton and the related subjects. Any more questions?
How the theta related to neutron moment problem?
Right. So suppose you have set of terms, and remember it's related to triangle diagrams. So suppose neutrons have neutrons are made of 3 quarks, and it has a charge neutral, and it has spin. And so, in some sense, you say up quarks are going this way, and down quarks are they have a magnetic moment. So neutrons could have a magnetic moment, or it could have an electric moment. I think a neutron doesn't have a magnetic moment either. Maybe it does. But if you look at the CP violating term, then magnetic electric moment is CP violating. So CP violating part, which is the electric dipole moment, you calculate it, and then using this instanton corrections, you have a non-trivial but effective action coming from instanton. It has non-trivial correction to the electric dipole moment, which generates non-trivial value depending on value of zetas.
Okay, thanks.
Any other questions?
Thanks for the lecture. So I have a question. In the standard textbook of the supersymmetry theory, so for example, when we introduce the n equal to supersymmetric theory, we can specify, for example, n equals to hypermultiplet and vector multiplet.
Right.
So we have already write down the Lagrangian for those two multiplets and their interactions.
Right.
And then we have a non-perturbative term, instanton.
Right.
So how does the instanton play a role in such a theory that we have already have a Lagrangian.
So we have a Lagrangian. So remember, I wrote down Yang-Mills Lagrangian. I haven't done anything else. And then when I do path integral, not only we are integrating more small fluctuation around the ground state, we are looking at the configuration which is big, and then which has to be included because in path integral we have to sum of all possible configurations. So you have a Lagrangian in which there are instances already. But if you just look at perturbative part of physics, you don't capture that part of physics. You have to look at the non-perturbative big configuration into the path integral. Then you look at the effect of this configuration to the physics.
Okay, thanks.
May I ask, how do you include the temperature or finite density effects when you are calculating the incident effects?
Oh, so finite temperature, well, remember I integrated over from, I took the limit where capital T is very big. For finite temperature, the T is finite and it's inverse temperature. Then when you integrate over path integral, you have to impose a periodic condition on the field configuration because you are doing finite temperature physics. Then you have additional configuration you sum over. And that's how you take over a finite temperature effect.
Because of the limited time, for more questions, please ask Professor Lee in private. Let's thank him again.
All right, thank you.
Thank you much. So let's take a few minute break. We prepare for the next lecture.
这个看学生也挺累的了，到最后。
对，但是我们也没办法。我们本来没排那么多，但是好多老师强烈就讲2堂。
不过这个范围挺广的，就。
一半的学生是外面学校的。
外面学校的，主要是哪些学校？
都有吧。
都有，都是主要北京学校还是全国的？
北京多一些，也有清北的，然后也有其他学校。
OK。
最有比较难的到南科大、港科大都有。
哦，南科大、港科大都有。
对。
南科大这个理论方向比较少。
行，那我们就开始今天下午第3节课，然后就是冯老师的第2堂课。冯老师继续给我们讲现代这个散热振幅理论。好，那有请冯老师。
好，这个我知道这个每天7节课让大家学生确实是比较疲惫。好在我这课是中文，所以听力上大家会感觉好一点，没那么累。好，我们接着讲，因为这个我说了，这个我们最近20年发展的这个散热振幅的新技术，实际上对无质量粒子最有效，而无质量粒子中最重要的就是规范场，因为现在这个具体计算中复杂度实际上就来自于规范场它的自相互作用，还有规范场导致的那个很多这个特别规范不变性等等，是这个传统的费曼图这个不太有效的原因所在。所以说我的讨论就会以规范场为主。那现在呢，我们就说规范场计算呢，我们知道那个费尔规范场，你就费曼图的时候，它是有2个部分出现，一个是动力学因子 K-mu 这些东西，另一个就是摄因子。所以说费曼图中它会带有摄因子和动力学因子在一起，所以你真正去用费曼图计算的时候，你会发现这2个点搅和在一起会造成很多复杂的地方出现。所以说这个历史上这个大家就发展了一个非常重要的经验，就是把这个不同的物理起源分离起来，就是说把摄指标和动力学指标进行分离，而这种呢分离之后，你就能发现，在不同隐藏就是原来纠缠在一起，但是你分离外不同部分，它就有它一些相对的一些这个隐藏的信息，这个信息就非常有用，而这个就是我要介绍的色分解的这个技术。那色分解技术很简单，对 SUN 的话，你这个胶质它的伴随表示它是这样的东西，然后这个伴随表示我们可以选择矩阵是规划系数， 然后是摄因子的这 coupling constant 是可以写成这样的东西。然后这个东西的话，你会发现这个东西的话，你是可以计算它有这样的一个结构，就是你两个，这个是因为你在中间要求和，对传播子中间求和，你对摄因子求和，所以两个摄影在一起，你又并成一起。这个是 NC 实际上是来自于那个 SUN 的 U1 部分贡献，你原来是在一起的，你又会分成两个。所以说实际上是色的分解就是利用这个技术把 FABC 写成这样的 trace 结构，你就可以知道了。那所以说这个一般结论就是任何这个规范场的这个叫的闪数图闪什么，它就可以写成这样的东西，就是你 sigma A1 它的这个次序在那儿，就它是一个 trace 的结构，然后这个 trace 结构是一对应，所以说这样的话你实际上是变成对所有不同的摄因子求和，每个摄因子它是有一个摄次序的。摄次序的好处就是它这时候它的规范场的它那个传播子它一定是这个动量一定是 K1 加就是 K1 加 K2 K3 这样连续的一些东西，在这个摄次序下，它不是任意的那个不会 K2 K4 合起来的这个出现，所以这就是所谓摄次序的分解。然后这个你可以很容易去做个计算，比如4点的时候，你可以写成这样的东西，然后你可以变成这样4项，然后每一项生成你用刚才写的东西，就是那两个这个矩阵的这个东西，就是用这两个关系，你就去做分解，分解出来你会发现，这时候它实际上是4点它就有这样4个不同摄次序结构，你可以很容易看得出来这个是什么样的这个结构。好，注意这个王文森的 U1 消失，它实际上是有一些原因的。那摄次序下你又可以写出摄次序下的费曼整符规则，但是这是你要保证它的次序是这个 cyclic order 的。然后你可以用来这个进行规范那个摄次序下的规范场的整符的计算。它的这个分解的优势呢，就是说我经常有时候要算 SU2，有算 SU3，那我那个摄次序下的这个东西呢，你实际上不依赖于你是哪个规范群。你把这个算完之后，你把这个只要把摄指标你代成 SU2 代成 SU3，你就得到 SU3 的这个结果了。所以这就省得你不同规范群的时候，你要同时去做的话，你会发现原来的这个费曼图你要很多你已经知道的东西，你要再进行计算。所以这个摄分解的优势就是这样的。这个是这个它好了，摄分解优势实际上是你这样的话就知道，我们原来规范整符变成一堆 trace 的求和，每个 trace 它对应一个单独的一个摄结构的那个摄次序的一个这个东西。而摄次序整符呢，它实际上是有一些很好的关系。第一个就是这个摄的，你当这个原来是顺时针，你本逆时针它有个 n 点的话有个负1n。然后呢，第二个就是你保持1不动，你这个2到 n 你 cyclic 求和，这个结果这个加起来等于0。然后第三个呢，就是说你实际上是叫做 KK 关系，这是89年发现，就是说你实际上是比如1、2之间有阿尔法、贝塔。它摄次序下，但是它可以写成1和 n 在两边，这个 sigma 在中间，这个一种保持次序下的求和的这个一个关系，叫沙夫结构的一个东西。具体的你可以去这个不用去特别，现在因为短时间你也不会掌握。但最关键是说，实际上这个在代数意义下的话，这个摄次序的积，实际上你可以选2个例子。在两边固定，然后只变中间的东西，它是一个积，这个叫 KK 积。然后呢，这个是2008年这个BCG 关系发现，他就说实际上是发现实际上这个摄次序下的积它不是只可以固定2个，它是固定3个。这个固定3个的话，实际上它关系就是说你原来是比如1、2固定的，他发现1、2固定后还有这样的关系，但这时候系数呢不再是一个常数，而是依赖于动力学因子的一个关系。这个东西实际上就是这样的，你比如2、1固定之后，你这个4从这边挪，原来4在2之间，然后是跳一个过来变成4变这边，然后4在这边的时候的话，它实际上是43、41，所以说43、41，4在这边只有41，所以是41。同样这边4的挪，这个4的因子摄因子就是这个动力因子43、45、41，然后4挪一个变成45、41，然后再挪一个变成只有41，所以这个关系很规律的。然后这个关系实际上是08年发现的，就是告诉大家，实际上真正的在摄次序下的话，你可以固定3个位置，其他的你可以做变换。 那这个为什么三个呢？实际上在那个弦论中，这个弦论中那个规范场的设置与整物，实际上是在那个一个这个 Dix 的边界上，你撒点就是这个点是次序在沿着的边界，然后是那个 SL2Z 的这个对称性就可以固定3个点，这是然后其他点就可以自由去撒，这实际上是这就是BCG 实际上这个关系就实际上是就从场论角度给出了弦论这个直观图像。好了，那当然说这几个东西，你说这几个关系，你可以从去看看能不能从这个当时我这个前头给的这个色次序下的这个费曼图这个规则，你去推一下，你会发现第一个关系就是 color order 的 reverse 关系可能好推 ，UE 的你就很难去从这个费曼图规则去发现了。那下面我就要讲在线对立关系怎么很容易的把这几个关系的证明出来。这个就是在线对立关系的话，它实际上是不仅是在计算中极大简化了，它同时呢对理解理论中很多深刻的这些结果，它会是极为简化了。现在我就开始介绍在线对立关系怎么去很显然的满足这个证明这几个东西。那就是它呢，实际上是就是说，实际上是这个就是说提供了，因为这几个关系只有在校情况下成立的，而这些证明它实际上不通过拉格朗日量出发，它实际上是就可以看到很多简单的东西。那我们看第一个色次与关系怎么实际上是这个东西就非常简单。我们知道我可以选择2个粒子固定去做 BCF deformation， 然后我就可以计算这个东西通过递推关系。那我们就可以这个地方，我就可以因为 En 是这个是这个东西，那我看我 En 对这个我做规范这个形变之后，我总可以写成这样的东西，而这种就是这种计算，我可以叫做原来是通过右边计算左边，但现在我把逻辑反过来，我说任何一个左边东西可以通过右边展开，我这个叫 BCFW 展开。好了。那有了这个思想之后，那我就可以看这个逻辑呢，就是我首先把一边进行 BCF 的展开，然后对剩下的这个展开之后的2个子振幅，我用递归关系去操作，然后操作完之后，我再把它重新拼接起来，就得到我要证明的关系了。这逻辑是不是就很清楚？那我们看一下这个最简单的递归关系，就是那个色次序的东西。首先，递归证明就是色次序 n 等于3的这个-1，这个是费曼规则，因为3点图你马上就可以看出来，所以说这个你从费曼规则3点图很容易证明这一点。好了，这个有了这个之后，我们就可以看怎么做。对一般的，我进行展开叫 BCF 展开，我就选一个 En 作为的形变的，我就可以中间的话，因为色次序底下你一定就是这个 i 对 i 从1到 n 减3的求和这样的东西，对不对？那这个时候我对这个子部分用那个递归的这个应用，那这个就变成倒过来，它就变成这个负 pi 贝塔 i n 的这个一个东西乘上一个因子，它的个数是 i 加2，对不对？这个再逆过来变成这样的东西，然后这一逆你发现，哎，这个你把这个因子提出来就负1n，那剩下部分求和呢就是1到 n 的 BCF 展开。这一下就证明了这个东西，这个，所以说对一般你就是就一下就证明了那这个实际上是同样的思路用到其他的4个关系上，当然每个关系就会变得稍微复杂一些。我们看 U 退耦合，U 退耦合就是1保持不动，在这个2,3n 的话做个 cyclic 求和，它变成0。它为什么这个关系成立？它实际上来自于我们当时设结构的时候，每个1是对应了 TA、T1，然后是2,3对应 T 那个东西。但是呢，我假如 T1 这个1的例子，它不是这个 SUN 的这个 generator， 而是 identity， 就 U1 generator。这时候这个色次序的话，这个1实际上可以出现任何位置的，它可以在不停的挪，因为挪完之后剩下 n 减1个的这个 SUN 的求和还是不变的。所以说这个求和的出现，就是因为我1取 identity 之后，因为其他色结构就要求我把这个求和起来，而我们知道光子场不和任何其他相互作用，所以说这有光子参与的话，费曼图的规则一定告诉你最后结果为0，这就是 UE identity 的这个物理意义。那我们看它怎么去 去去进那个这个就是我刚才解释的这个就在解释这个是这个 U1 的物理含义。那我们看怎么证明？证明呢，我就举个 n.5 的例子，就是同样的。那 n.5 的例子 ，n.5 例子呢，实际上设置一下就4项，就是左边4项，我要证明左边4项求和为0。那这个n等于3的时候，实际上你可以很快去容易证明。然后是 n 等于4的话，你也可以进行计算，就是从 n 等于3出发，你可以证明。所以说，我就假设这个3点4点的这个U1 identity 已经是证明了。那我们就看到125的时候，我选15，选12做这 BCL 展开的话，你就1在两边，你可以发现它就展成这2项。这1在123这个实际上是表明实际上是这个实际上是写成12345，然后231，这样是这样的一个缩写，它就可以这个展成2项，这个展成4项，这个也是4项，这个人是我这样特别写的结果就是对齐。这个在这个时候，你看这 P23是公用的，所以说 P23这边的因子是一样的。那这样的话，剩下的部分呢，就是这边的部分。这部分你看，这部分实际上就在做这个2、3、4、5的 cyclic 3项，所以4点的求和你就知道为0了。所以每个 column 实际上都是一样，这个实际上是这个1保持固定，这2个 cyclic， 这个也是3个 cyclic， 这个是2个，所以说你加起来就为0了。所以说实际上是你看到，实际上这个的对一般，你实际上就可以知道，每一个人展开之后，你这个把这个有一边因子那个弄起来，因为它从2个开始，至少是2个开始，所以剩下的部分它一定是低点的这个重新组合，你一下就看清楚这个事情了。就这个这相当于纯粹的，但就像变游戏一样，你就是有点无脑的操作。但这就确实反映了这个从在校角度去看这些关系的这个优势。这个当然是后面细节我就不讲，你怎么展开之后，你怎么去这个细节，就是说你多少项，这个怎么写成这个东西都，因为我们的时间有限，我就不讲这些细节。然后这第三个就是我可以把2个就固定在，那这个关系怎么证明？这个就会就是这样的一个东西。那比较好的，比如 n.5 的时候，这个15在两边，中间我就有2、3、4，那我就把15弄在两边。那这时候的2和3、4之间有个那个 permutation 任意 permutation， 但是我要保持3、4次序不变。所以说这个3、4呢次序要逆过来，所以这边一定是4、3次序。所以2可以在这边，再插中间再插这边，所以说你看有3项出现，这是 KK 关系的这个结果。好了，那我们同样的可以看到。我这样怎么做？我首先去看看这个原来的左边我进行 BCFW 展开，然后呢，这取了15作为 deformation， 那这个我就得到4项，这1在这边，5在这边，我当然写的次序就是为了这个后面。好了，然后你可以发现这个时候这个5呢，我可以 cyclic 变成这个边上，这个1呢，我可以 cyclic 变成边上，我就把每个1和5不在边上的，我都通过 cyclic 变到边上去。然后呢，这个时候的话，这个时候这个这个地方，你看这个来说，1和这个不在边上，那我就用低点的 KK 关系把这个1和这个边上的写成1在这两边，1和边上这个1和边上写成这2项，用低点的 KK 关系。我写完之后的话，你会发现这个呢。这个是写成2项，这个呢是的 cyclic 就是1项了，这个是这个也是cyclic 1项，这个写成这个是5和 P 字不在一边，选2项，所以这个2项实际上就是变成2项，所以说一共变成6项。6项之后，我就这个就刚才那一项变成2项，这个是变2项，这6项之后的话，你就会发现这两组合。每个的这个T1这一项和第4项第4项是这个，你看这个的时候，这个是都有这个1、2、3、4，你看这个 P12，这个是1、2、4，这个是1、2、4在这边 35，看到没有？这是1、2、4，这个是1、2，然后4在这边，所以这个呢 T 这一项加上这一项就是1、2、4、3、5的那个 BCF 的展开。因为1和5在两边嘛，这个1、2一起，1、2、3、1、2、4只有2项，所以说这 T 和 T4就给出了这个的 BCF 展开，所以合起来这个变成这个，所以说你看6项就给出来了。这个就是这样的一个规律，就是你展开之后，低点的用 KK 关系，然后你重新组合就变成高点了。当然这些就是对一般情况下，这就是写的比较详细，这个我就跳过了，因为这个没有必要。但是只是通过这个例子呢，就给大家演示这个它的这个 power。好了，那最能全有关系就属于2008年发现 BCJ 关系的这个证明。那这个证明就挺有意思的。这个当然我这边也给了大家这个旋论中它图像什么样的，它是因为这个旋论中这个你把这个色次序的在那个这个 disk 的这个圆盘的边界上，你按序点的话，有3个可以通过这个所谓的这个modular symmetry 去固定。那这个为了证明思路呢，我就是以这个6个点的为例，6个点的话，我这1、2固定的话是不停的跑，就是所以说这个动力因子在这边。好了，那这样的话，我同样的这个思路，我就选1、2作为这个固定的这个 deformation 来进行这4个东西的展开。好了，我先把这个就进行展开。展开之后的话，每个展开是有3项，因为1、2这两边的话，它是有展成3个，先2、4、2、4、3、2、4、5，所以有一共3项。我先讨论只展成这一项展成3的这个左边只有3的就有2、4、2、3、2、3，那你看到剩下这几项是一样的，这一项是不太一样。好了，那我们怎么去做呢？第一项通过动量守恒，我可以重写为这样的东西，它是负 S24 这个部分，可以写成这个 S2 hat， 就是因为这动量是 deformant 的动量，然后这个 S2 hat 呢和这个组合起来，就低点的 BCD 关系它等于0，所以剩下就是这样东西。这个就是第一个这个是稍微麻烦一些。那后面3项，因为这个左边是相同的，然后右边的话可以重新组合，但组合之后的话，你要用这个低点 BCD 关系的时候，你这个离变成 hat 的这个动量，而不是41，所以我就是1加1减，就这个变成41，这个变成41，那你每个多一个41减去41减的东西，它都是一样的东西，所以说减的东西呢就合在一起。那剩下这部分呢，就是用5点的 BCD 关系，它就是为0，求和为0，那实际上就剩下这个东西。然后呢，合在一起的时候，你又看到这个东西，然后剩下3项是这样的东西，而1、2形变告诉我们这个有这样的一个关系，就是所以说这个减等于这个减，这个是动力学的这个稍微操作一下就很容易知道了。好了，那我们这个左边是3的，我就很快合在一起就写成这样的东西了。这个呢合在一起写成这样的东西，写成这个东西。那你看我左边3的这样操作，这个2、4、3，这个是左边3个的，也同样可以操作，就是 I3 你也可以有这样的一个合成，这样是2个，这个2个，然后是 I4，就是左边是4项的这个东西，你也可以这样合成。那合成之后呢，你会发现，把这所有合成之后，它呢实际上相当类似这样的一个维导积分。而这个维导积分是什么呢？这里头这个东西它没有动力因子，而这个里头的这个求和，就像 KK 关系，就是 KK 关系。KK 关系求和之后呢，你会发现它变成什么呢？这时候的话，当然这个符号这个细节的计算，这个就是把这个 K， 所以说我们求和呢就得到什么？这个是0点的计算是变成这个东西，然后呢剩下的部分呢变成1和2不在一起的这个东西了，而不在一起呢，它的这有个 z 因子，然后这个就是 z 不等于0的所有求和，而这个求和呢，你可以去转化为无穷远点 无穷原点的这个东西，而无穷原点的东西呢，因为这个行为，这个就是1 over z 平方的这个压低因子，所以这个无穷原点的积分为0。所以这时候就可以看到，这个 finite z 不等于求和就等于负 z 等于0求和，就等于负这个东西。所以合在一起，你把这个的积分带到前头去，你就可以知道，这个是正的减上这个负的，就等于0。所以这个就是，当然这个 BCD 关系呢，这个证明稍微复杂点，但是你一步下来的话，也就没有什么特别的这个东西。但是你要从这费曼图结构去证明这个，几乎是不可想象的。我至今这个没人去这么尝试过。这个要是有这个不服输的，可以去尝试一下，看怎么去做这个事情。好了，我这个就把这个树图的部分的一个介绍完了。下面我要进行圈图的这个讨论了。因为我说了，我们当时剩下时间也不多，就20多分钟，尽快讲，能讲多少讲多少。然后实际上是我们这个过去20多年的最大进展，实际上是树图当然是进展的一部分，另外一部分就是在圈图上，因为实际上是只有圈图上我们的能这个给出这个费曼图不能 handle 的这个情况之后的话，大家才其他人才认可这个方向的进展是重要的。这个就是圈图的这个问题。那圈图呢，首先我们知道树图实际上是经典效应，量子修正一定圈图开始。这个圈图呢，实际上最重要的一个计算方案就是约化。它是什么意思呢？就是实际上我们看到你从费曼图来的这个所谓的贝积函数，它不是任意的，原因就是它的分母一定是一堆传播子的乘积。它不同的是在分子上，分子是不同的理论是分子不一样，但分母是一样的。因为这个有分母的共性，所以你会发现任何不同分子的结构，它可以写成一堆积的组合。这个积呢，就是所谓的叫这个，那其他呢就是一个系数的计算。所以说这个积呢，你可以算一次，可以用到所有过程上去。然后那个系数呢，不同的物理过程对应不同的系数，所以物理的不同物理的这个真正的不同物理的信息是在系数部分，而积呢给出了它的一些 universal 的解析结构。这实际上这个思想是极为关键的这个东西，它实际上是分析起来实际上是这样的。那这个东西呢，实际上是到现在为止仍然是我们高圈计算的一个黄金的这个，就大家都 follow 这个规则。当然这时候你又会发现，因为这种分解的话，你积的这个所有圈图计算，你分了2个相对独立的部分，一个是我积，我算一次之后，有人算了解析结构或者程序包就供给大家用，你算一次就可以了。那剩下的部分就是约化系数怎么计算，不同过程约化系数怎么计算。对当时来说，实际上一圈图的很多积我们已经算完了，对 HC 开展之前，所以当时碰到的困难就是你约化系数是计算是很复杂的。这个约化呢，实际上分2种约化，一种贝积函数层面的约化，就是你给了一个这个费曼图给出的这个贝积函数，它是一个有理式，在这个层面上进行约化，它是纯代数的。另一个叫是在积分层面约化，就是你在纯代数约化之后，你会产生有些项，它代数上它不为0，它积分为0。那这样项的话，我就不需要去保留。这是从代数约化到积分层面约化的一个必要点，就是你有的信息你就可以扔掉了。那下面呢，我就开始介绍这2类约化，就看时间。这代数层面约化什么意思呢？代数层面约化实际上本质上就是这个例子，这个就是所谓代数层面约化，它就进行代数分解。你原来是分母有很多个传播子，那我呢尽量是传播子越少，显然积分越简单，对不对？那我就能不能把这个分解成传播子少的项的组合，这就是这个意思。这个地方写成 x， 这个地方 x 平方是 x 的减1乘上 x 加1，然后分解2个，每个只有1个因子。那显然左边你要进行积分的话，比右边肯定是简单多了。这个思想看起来简单，但是它就是核心，就是代数层面约化的核心就是这个。像有的东西的话，不是概念上不复杂，但这个地方的话问题是所在什么地方呢？就是这种分解，大家很容易知道，实际上通过那个做那个除数，就是所谓单变量的这个 polynomial division 就可以，大家学那个 代数分解的时候，或者你一个质数分解的时候，一个数的分解的时候，就是所谓高斯那个消元法，不是高斯消元法是什么？欧几里得这个辗转相除法。Anyway， 对单变量的这个东西很容易做，但是你当有多变量的情况，就变得极为复杂了。而这个实际上，这个对一般多变量情况怎么处理呢？实际上是现所谓的这个就是我刚才已经说了，这基的就是研究是好。我现在这个在多变量情况下，它实际上本质上它就变成一个所谓现在有个数学分支叫这个叫那这个computational algebra， 就是交换代数的一个东西。实际上交换代数就是在做这个事情。它怎么看到是这个变成一个多变量的一个分子除以分母的分解问题呢？实际上很容易。比如我们在四维中，我取两个动量，我可以构造一个4个的动量积，这个是旋量指标，这是为了简单。Anyway， 你不管怎么说，你任何一个动量可以在这个4个积下进行展开。那展开系数呢，就是所谓的我任何一个这被积分变量，我就可以展开系数。这个系数呢就是 x， 就4个变量。所以对一圈来说，它实际上就是一个分子是一个4个变量的一个 polynomial， 除上分母呢也是4个变量的 polynomial， 但是那4个变量的 polynomial 是一堆传播子乘积。所以这个情况你怎么去做约化？你比如在这个地方的话，我选择这个积的一个好处就是它变成 L 平方变成这个 LK 变成这个东西。那我举个例子，所以它变成这样的一个除数问题，你怎么把这个 F 中剥掉 dt 的因子？那约化问题实际上你把每个 fi 展成某个 dti 乘上一个这个就 remainder， 大家是要直数那个数相除的话就 remainder， 这剩余函数就实际上是你有多少个 remainder， 它就是所谓的积分层面的积。这个东西的话这个处理的话，一般情况的话就是所谓的用代数语言就说你实际上是传播子就生成了多项式环的这个理想，然后代数积就是3环上的代表源。这个就比较抽象，但是实际上就是我在很多不同场合中，我实际上就说，我们大学物理系的，我们第1年也要学线性代数，对不对？线性代数实际上是线性方程组的求解问题，这是物理中基本的。为什么？实际上我们物理碰到了很多问题，你实际上是你都在做微扰部分，你在那个微扰的第1阶就是线性的东西，对不对？所以说，这为什么线性代数是在物理中极为有用？但是你会发现，你当碰到稍微复杂的问题的时候，你就不再线性了。这时候你又第一个比线性稍微复杂，但是比所有其他更简单，什么？就多项式。所以说，实际上物理中现在很多情况不同分子，你都会发现你就会碰到多项式问题的求解。而这时候的话，代数几何就是这个数学家发展的这过去100多年发展的对多项式这个零点的求解的这个数学工具。所以说我就曾经跟很多人说，我说现在物理系学生的话，可能大3、大4需要开一门这样类似的课，就跟那个数学物理方法一样，因为你会发现这个在很多研究中极为有用了。当然我也是这个做研究的时候认识到这一点，这个是认识到现在这个代数几何对我们实际上是很重要。好，那这个是举个例子，这个我就举几个这个例子，我举方块机有4个传播子 ，L1 这4个传播子，我用这个写成机构到它写成这个就是这样的，这个是projected， 这个是线性的。然后这时候的话，这个是那就是实际上是我任何给一个分子的话，我怎么去求解这个东西？那你就可以看到，通过这个关系。我把这个第1减掉第0之后，我就得到一个这个的线性方程组，对不对？那我就可以把这个 x1 写成这样一个东西。这个实际上就表明这个3环，因为3环实际上就是这个任何东西你设为0，那剩下就是说 x1 它不再是一个变量，它可以用 x2 变量求解。那这时候的话，你同样的把这个东西，我可以把剩下的3个传播子减掉这个的话，我就可以把 x1、x2、x3 就4个传播子4个变量中，我就其他都求解出来。那剩下的话，我就只有一个 x4作为这个不求解的问题。 那我把这个求解 xn 带到第4个第0方程，我就发现它实际上是变成这个东西。我实际上是商的话，就是相当于令这个等于0，就是把只要是 x4平方，你就可以写成 x4加这个常数项。那这实际上告诉我们什么呢？就告诉我们，你分母上你只要出现 x1，你就变成 x4。然后 x4你要是一堆 x1的乘积或 x 的高阶项的话 ，x4的平方、3次方、4次方你都可以约化成1和10。那剩下的就是这2个积了，就是这样的一个东西。就是当然这个例子是极为简单，但实际上是告诉你这个代数几何怎么去求解这个问题。好了，这个时间这个三角的话就比较复杂。3个三角的话，你这个只有2个，这减掉 l， 你只能求解2个 x1 x2变成 x3 x4的线性函数。但代数带出来之后，你会发现剩下就是 x3 x4有这个关系。那这个什么意思呢？就是你 x3 x4的话都变成一个的东西。那实际上你会发现三环的话，它的生成元就是 x1 x3 的任何幂次 xn 任何幂次。因为 x3 x4的话，它就是变成一个数了。虽然这时候 g 的个数是无穷多，就代数上是可以，但是呢，因为我们这个物理的实际上是你分母是3个传播子的话，分子的话，你可重置理论它的幂次也只有3个，所以说你不超过3的话，你就可以知道只有这7个 g。这是物理的约束，要是不是物理，它就无穷多个。好了，这个那有了这个之后，我就可以下面的我就可以跳过去，因为这告诉你怎么去，这是我可能时间只有那个还剩多少时间？
如果您想讲的话，可能还25分钟。
好，那就先讲这个东西。这个的话就是实际上就是我们这个一圈图革命，这个是在大概OP 方案，就这个方案就说实际上是这个代数约化的这个实用的一个典型。就是它这个出来之后，大概是这个工作是2006年出来的，然后这个工作基于这个工作开发的程序就一下就是一个突破性的成果，就是当时一圈图中很多费曼图没法算的一些结果，后来就用这个方法就可以算了。所以说当时大概到10年左右，就是我们大家认为这个一圈图，这个我们所有计算就已经是没有任何困难了，就是我们只要 HC 设计的这个过程都可以一圈图的修正都可以计算了。这就是 OPP 的这个这个和另外一种方案就是腰正切割方案，我今天肯定没时间讲。这2个方案就是电子一圈图革命的这个基础。好了。这个从10年之后的话，实际上是现在的这个我们这个圈图计算前就是2圈及其以上。现在2圈的东西还没有完全解决，实际上还有很多困难问题在这个需要解决。那1圈呢，我介绍他们的工作，他的工作就是实际上就是这个东西，就是这个是我刚才说的，实际上是分子除以分母就是这个东西。他会发现通过刚才分析之后，他会发现这个积是哪些呢？积就是在 box 里头，这个是实际上这去掉4个传播子，这个除掉之后，实际上是这一项除掉这个所有传播乘积，就实际上是只剩4个传播子，所以这一项是给出的 box 展开。box 展开积里面，第一项是这个是物理的积，就是1的对应；另一项这个项呢是 Q 的这个线性项，刚才我已经讲了是这个线性项。而这项呢积分是为0的，但是在这个地方我是需要计算的。那这3个呢，这部分对应是triangle 积的这个东西。那这边有7个，所以 C0 是一个物理的，剩下6个是非。那 D 呢，这个是2个传播子，所以说对应 bubble， 这个 bubble 的积，这个是 tadpole 的积 ，tadpole 就只有一个传播在底下的。好，他知道物理的告诉我们这个展开就一定可以这样展开，这就是我们需要计算的约化系数。那呢，巧妙是在什么地方呢 ？OK， 他说，哎，我这个东西，你可以这个东西，你写了这个展开之后，一个方法的话，你可以很容易知道。第一个，这边我可以求解这些系数，这个是形式我已经知道了，我可以撒点，撒足够多的点，我就可以求解所有系数了。这是一种思想。他们这个展开，他们这个东西很早就知道，大概03、04他们就已经知道这个展开。但是他们的当时就说撒点的话，这个系数可能有100-200个。他就求解100-200的这个矩阵方程，这个也可以求解，但是呢速率很慢。后来呢，他就是在我们的一个工作启发下，就是 我可以不用一次求解的东西，我可以分布求解。那这个就实际上是一下子简单。怎么分布求解？因为这个时候你撒点是有自由度的，对不对？那我说这个四维情况，我可以撒这样的点，我可以选这个一个 box， 我使得这个4个特定的传播子为0，撒这个点，就 Q 的球。因为4个传播4个方程，然后是4维中，你可以定出这个 Q 只有两个分离值。那撒这个点为0之后，你会发现，因为你在所有其他项里头，在所有其他项里头，这个至少包含1个传播子为0，因为你这个只去掉3个传播子，所以说还剩下一个传播子，所以有个传播子肯定是为0的，所以所有项都不贡献，都为0。只有这个特定的传播子，就是这个 box 对应的传播子，它才因为这4个为0项你去掉了，其他都就只保留这个单独这个box 的这个东西出现，所以这正好是2个未知数，2个方程，你就可以一下求解了。所以这时候你就单独的一个传播子，单独的一个 box 变成22方程求解。那你撒不同的传播子的组合，你就把所有的 box 都求解完。每次你只解2到2的这个2×2的矩阵问题，然后举完之后怎么办呢？哎，我就很好，我这个费曼图给出来这个我已经知道了。那我把这边减掉我 box 的这个计算之后，那剩下最高的项只是这个剩下 triangle， 对不对？那我又选 Q， 使得3个传播子为0，那它这样3个传播子，它就挑出了特定的 triangle 来，对不对？但是你3个传播子为0，这时候 Q 呢是4维的，所以它实际上是有一个自由度，它有个1维的一个连续变量。但是呢，我这边有7个这个未知函数，我只要选择这个7个就可以了。所以说你这样的话，我就triangle我只要选择这个7个方程就可以求解。那求解完 triangle 之后呢，我又把 triangle 减掉，我就可以求解 bubble。你就看它就原来是这个所有系数，因为不同你每个 box 是两个系数，不同 box 乘起来，再加不同 triangle 7个系数，一个 triangle 7个系数，不同 triangle 系数，原来就是整个物理过程你几百个的这个方程，几百个那个大方程，我就分解成一个小方程，每个小方程算得很快。所以这个一个改变之后，就让这个计算的速率大大增加。你看这个思想，这个思想是极为简单，但是呢，这实际上是非常重要的一个事情。实际上是后来我们会发现，你实际上是在我们圈头计算中，或者你做了很多研究中，你会发现，有时候你要算一个很大东西的时候，你想想有没有可能，我把一个大问题分解成一个若干小问题，每个小问题。虽然你分解小问题多了，但每个小问题计算的速率和这个memory 消耗都会比较小，你合起来反而比你一下大一统的解决一个大问题反而来的简单。这实际上就是这个工作这个给我们这个所谓的研究方法中的一个很好的一个启迪。好了。这就实际上是这个，当然你看这每一步都是一个代数的东西，所以它这个东西是很好编程。所以编程的话就是很好在程序中实现，就真正是实现了我们这个所有的一圈图的现在市面上的这个程序基本上都基于这个思想，当然还有另一个思想就不说了。好，这是我刚才解释的东西。那下面呢，我就开始讲这个积分层面的约化。就在这个地方呢，它有优势是在地方，就是说你会看到，比如我 box 有2个系数，它在这个 OP 方上需要计算，但是一个系数它积分为0，就是那个圈那个积分为0，所以它的系数实际上你算或者不算都对物理没有影响。但在 OP 方中你必计算，在 triangle 中是一个是物理，另外6个是 sphere 的，但是呢这个代价不算大，所以我们还可以承受。但是你用同样的方法到2圈的时候，你会发现，哎。这个2圈给了一个这个积的话，它系数很可能是会有100多项，但100多项中只有几项是物理的，其他项都是积分为0。这时候你仍然可以用 OP 方法，因为 OP 方法的话就基于实际上是 computation algebra geometry， 这数学家给我们了一个一般的 algorithm 去算这个问题，但是你会发现这时候代价就太大了。你物理上只需要几个，但是你为了这个实现用这个方法去算，你需要算这个2个量级的这个系数，那就非常不经济。所以这时候就问有没有方法，我只算物理上有贡献的这个约化系数，就是这个积分层面的约化，就是这个思想。而这个思想呢，最开始的这个东西呢，来源于这个所谓 PV 约化方案。这个 V 呢，就 Whiteman 呢，就是那个所谓和 t h o f 的2个一起拿诺贝尔奖这个 Whiteman。好了，那他的思想呢，实际上就是说，这个在医学图这个比较成功的是有 PV 方案，还有腰正切割方案。我这个时间的话，我现在就介绍一下 PV 它怎么好，这是2个传播子这个一个张量，它2个传播子你 L1、LP1。好了，我们知道对这个张量情况下，因为我知道这个积分结果它一定是rank 1的，所以说而 rank 1呢，在这个积分中能提供这个指标的只有 P1，所以我就知道在这个积分的话，我不管我怎么算，我知道它一定是这样一个数，这个 B1呢是一个洛伦兹不变量的一个函数。剩下 PM， 对不对？它一定是这样的一个组合。那现在的话，我知道这样，我在这两边同时上 P1， 那 P1 实际上这个时候就是 P1 点成这个，而这边是 P1 平方。那我现在就是问这边这个实际上 P1 之后它是不是能可以约化？那这样你会看到这边实际上 P1 之后的话，它变 PL， 那你会发现这个 PL 的话，它可以 LP1， 它可以写成这样的组合。这个呢组合，这个呢就是实际上就是传播子2。第一传播子1，你可以减掉，那你会发现这个呢，你实际上是这一项组合就把这个一个传播子去掉，所以变成那个 teleport 的积分，这个也变，那剩下部分呢就是变成这个还是 bubble 积分，但是呢上面的分子是1，就是 G 了。所以这样的话，你这个线性代数组合，你把这个带进去之后，你就左边等于右边，你可以求解出来，它就等于这个，而这个就是。这个去掉一个第一的传播子变成 teleport， 第2传播子这个是这个 bubble， 这个但分子为1的叫 scalar bubble 的 G， 就是它的思想就是这样的。这个思想呢当然是极为简单的。然后你是要2个 tensor 的话，你比如 L1、L2 呢，那这时候你会发现 P 没有 P 没有 P6 加上 G mu， 这是 G mu 要进来了。这时候你会有2个东西，你可以同样去做，但这代数呢？这个思想很简单，但代数会比较复杂。就是这样的情况，你可以同样去做，但是这时候你要求解2个方程，你可以 P1 乘上 L1 后，你带上去，你可以求解，就要建立2个方程，2个方程求解，这个实际上是就计算出来会比较复杂，它实际上是不是一个很好的一个东西。但是这是 PV 的这个逻辑，就是我通过外动量和度规构造张量结构，然后是乘以每个独立张量结构形成一个方程组，然后求解，这是它基本。还有多少分钟
？10分钟左右。
啊，我要不了，我就尽快完，我就简单介绍一下下面那个。那这时候就它这个实际上是70多年7、8年80年左右的这个工作。但这个工作为什么后来就实际上是仍然是费曼图计算造成困难呢？就是因为这个工作，这些它这个求解也是碰到一个大量的方程组的求解问题。那这个的话，这个 PV 方案改进，我看这个跳过去。好，这个我看看，我还是讲这个吧。这个 PV 是积分层面约化， 但是最后实际上是现在比较一圈图比较好的，实际上是所谓的腰正切割约化。腰正切割呢，实际上是它实际上充分利用了这个积分的一个解析性质，就这样说的。就是我们实际上知道这个你 y 动量呢，实际上是一个常见，就是所谓的你把这个 s 它是10的，你把在一个它是一个割线，你在上半部加 a0 减掉它那个割线的下半部，它实际上不等于0，这个就所谓的整幅的虚部。虚部呢，就实际上是它有一个重要性质，就是说这个虚部呢，你这个计算虚部的时候，它实际上是把2个传播子变成德尔塔函数了。那就是所谓的切割，就是你原来是积分4维，但是你分子上变了2个德尔塔函数之后，你变成2维积分，所以这时候你算虚部的话，实际上是比这个比直接算这个积分要简单的。而这个实际上是这个虚部呢，实际上是重要的一个东西，就是这样的。这个时候第一个简单之后的话，还有一个非常好的优势，就是你把这2条线切了之后，它变成再翘了，那这样子变成什么？这个输入变成左边的树图和右边树图。这个输入的话你就不需要用费曼图去算一个图，你可以通过再跳递推关系算出树图，输入上去。那这个表达式就一个树图，它就这个一个树图结构就涵盖了很多个这个费曼图，所以这是腰正切割的这个一圈图的一个很简化的东西，你输入上极大的简化了。然后第二个呢，你这个积分呢变成这2维积分，这是腰正切割的一个图像，它的优势。但是这个我们知道，虽然是2维积分，你不要说2维积分，就1维积分，经常我们说不出来，对不对？所以说，凡是碰到积分，你的问题是积分能不能简化成微分？微分我们很好算，积分很难做。所以说，实际上是现在这个我们实际上成功的经验就是说，我把任何积分都转化成微分，然后求微分方程组，这是我们现在高圈计算的一个思想。这个思想呢，也传递给大家。你们碰到这个积分问题的时候，你可以想想这个思路。好了，那用这个腰正切割来怎么去做约化呢？我们知道这个 A 呢可以写成这样的积分的约化。那约化呢，这个 C 它是一个有理函数，所以有理函数它没有虚部。所以我两边取虚部的时候的话，这个 G 的虚部是可以计算。然后我假如能计算这个右边的这个虚部的话，那我就可以对比这两边，我就可以读出约化系数来了。这是腰正切割用来进行约化的这个关键思想。那因为这 G 呢，它实际上不同的 G 它的这个计算出来虚部之后，它是不同的解析函数，所以说这个东西的话，就相当于我们两个多项式相等的话，多项式的系数一定相等。那现在问题是说，哎，这个看起来很好，那实际上是问题就是说，这个我每个 G 我当然很容易计算。那现在问题给出一般数，你怎么算这个东西？就刚才说这个实际上这个也是2维积分。那但这个计算呢，实际上这个后来实际上是这个思想是在94年被他们提出来，但是呢，这个最大的问题是这个积分实际上很难算，就是我刚才说的这个这个很难算。但是呢，在那个03年的时候 ，Witten 这个 twist program 里，它实际上就给出一个方法，就可以怎么去算这个积分。这个积分的话，计算就是这个2维积分的话，它实际上是可以转化成一个辅平面上积分。然后辅平面积分呢，又可以把这个被积函数，因为这个是这个费曼图给出的这个表达式，它是不是任意的？它实际上是有理的。而这个有理的，它有很好的特征，它也可以写成一个全微分，再加上一个反常项。啊，全微分是共线为0的，而反常项呢，它是又给我提供了2个德尔函数。所以说这样的话，这个2维积分就转化成求一个有理函数的极点的流数计算。思想就是这样的，就这个就工作就这两个工作就把这个实验就发展出来，就是说像最后的实际上是剩下2维积分计算，它不再是一个积分，它是一个纯粹的这个代数计算。当然呢，我们时间没有，我为了给大家简单例子，就举这样这个是一个辅平2维积分，我这个呢是一个求导，这个求导的话，大家知道这个求出来肯定是一个这个是 z bar 其实，但是呢，我把这个 z bar 呢可以写成全微分。因为 z bar 对这个微分是大值为0， 大值为0，那可以显示这个全为分。但是呢，我们知道实际上这个 z bar partial 1/z 它实际上是不完全等于，它实际上有个德尔函数。这个实际上德尔函数就是所谓的这个反弹项，而这个实际上就我们在电动力学中那个电荷的点粒子的这个势能，你实际上是那个点电荷产生的那个势能项是 1/r， 对不对？你那个泊松方程是那个拉普萨平方作用在 1/r 上不等于应该德塔 r。实际上这个就是同样的，这个德塔函数来源就这个。那知道这个地方德尔塔平方这个你实际上这个积分的话，我就是把 z 取成 z bar， 就这是流数就这样，这个计算，这个实际上例子就告诉你这个东西。好了，那是有了这个计算之后，我就可以这一般情况我就不讨论，然后我们就可以把那个很容易求解出来。然后这时候我们输入又很简单，输出就是这个输入是这个在校计算数图成绩，这个我后面都是就都跳过了。这些都是流数计算这个一些技术性细节，当然这都是最后结果是什么呢？结果实际上很简单，就是实际上是这个求流数的这个我真的是时间到，我就这放最后一个结果。我去看是不是最后一页。这是我以前去年讲课时当然是比较细节了。最终结果好，这个就是当然这个实际上是这个积分的话，因为这个可以解析写出来，所以这个实际上我们实际上给出了这个，我们实际上是这个文章中已经完全推导出来，我就直接给出表达式了。表达式就是比如我这个输入就这样的一个东西，这是一堆这个东西，这个因为分子一定是论之不变的这个量，这个 k， 然后你通过这个 k， 你可以定义这个量，定义这样出来之后的话，你就可以发现对这个输入它的这个包含传播子 k、r、k、s 的这个 box 系数就是由这个计算出来。这是我已经给了你一个简易表达式，你只要把这个量算出来带进去就知道结果了。然后这个 triangle 就是也是可以写出来，然后 bubble 系数就是我就已经给出这个表达式了，你就不用再去做刚才流数的各种计算。这个都是这个好，我这个一圈的这个情况就介绍这样，就是基本上是回顾了我们这个过去2年这刚开始最基本的一些发展。好，谢谢大家。
感谢黄老师给我们介绍，对咱们政府有个全面的介绍。大家还有没有什么问题吗？
就是你之前讲的结果是你们已经得到很多这个数图上的这个就是各种各样的这个约束关系，对吧？然后我看到就是我一开始以为你讲这个是想说可以把你们那个数图的递推关系各种各样的递推关系推广到这个圈图，然后我看到好像就是可以通过光学定理是有一个联系，是吗？
不是，这个你问了个很好问题，实际上就现在是这个数图推广到圈图的这个东西，还这个实际上这个最近这个发展的实际上是在尼玛和和顺他们一系列公司在做这个事情。就是我一直在说这个我们这个新的这个研究领域有一个宏大目标，就是不是一个目标之一，就是我寻找到一个就是费曼图的一个替代方案。在数图上，我们递推关系已经可以解决问题了，但是圈图上怎么去构造圈积分的这个倍积函数，而不需要用费曼图，这个实际上现在实际上是这个在这方面进行进展研究实际上是不多，但是这是我们实际上是目标。而目前的话，这个 尼玛和那个何颂他们那个还有一些合作者，他们那个几个组，实际上在这方面做了一些推进。比如在 n等于4的这个超弦理论中，有这个 amplitude 这个它有一个很几何的构造方法，可以这个Grassmann 的那个这个变量，它可以写出任何圈的贝积函数，可以写出来。但是呢，只在几个特殊的例子上，我们可以有任意圈的贝积函数构造。对于一般理论构造的话，现在还只是没有太多进展，但这是一个非常重要的课题。
但方老师就是通过你前面写的那个，就是如果我们只关注一圈图的这个虚部的话，那至少已经可以通过你们那个树图的递推关系已经可以确定了，是吧？
对，就是一圈图腰等切割底下这个我这些表达式是完全是你就是你都不需要，就是你就算的在校树图输入，然后拼起来就可以算这个圈图计算结果一圈，至少是已经可以达到这样的。
行，谢谢。
还有其他问题吗？或者有问题可以接下来再问冯老师本人。好，那我们就先到这儿。感谢冯老师给我们两堂精彩的
好，多谢大家。
好，那我们就稍微再休息几分钟，准备我们今天最后一个课程。
总算完了。
好，感谢冯老师。
不用。
Hi, Professor. Can you hear me? Sorry, we just finished the last lecture. Sorry, really sorry.
I've been online for a while, yes.
Yeah, we just give students a short break. How about let's start in a few minutes? At 25?
Okay.
Okay. Thank you.
Tell me when.
Sure. today's afternoon session. So we are very happy to have Professor Sakar again. He's going to give us the second lecture on the observational effects in cosmology. Let's welcome him. So, Professor, you can start.
Thank you.
Thank you.
Well, we ended yesterday with this anomaly, which I emphasized is something very significant. It's over 5 standard deviations. Now, I'm trying to get a feeling for how many of the students are familiar with this area, because that would make it easier for me to set the level of the discussion. So please, can I ask whoever has heard of this to raise their hand? Has anybody ever heard of this dipole anomaly? Did you understand?
The dipole anomaly?
No one has heard about it? It doesn't matter. I just want to sort of get a sense. So, okay, I mean, I understand you are all doing theoretical physics, so would not have necessarily learned about these things. Sorry? No.
I don't see anyone raise a hand.
Yeah, I don't think anybody knows about this. Okay, but the point is that if you are going to be working on cosmology or are interested in cosmology, the biggest issue today at the interface of theoretical physics and cosmology is the question of dark energy. The universe is meant to be dominated by a cosmological constant, which is vacuum energy. That's what we are told. And this is something that is at a physical scale of a milli-electron volt, 10 to the minus 12 GeV, which, as you all know, has got nothing to do with high energy physics, with the standard model, with anything that we know about particle physics. So this is a big problem, and therefore some of us are interested in digging into the foundations of cosmology to determine how did we come to this conclusion? Is it true? Because it has, of course, a big significance for all attempts at fundamental model building. For example, in string theory, it's the interesting question whether de Sitter vacua are even allowed in any theory of quantum gravity, since you can't construct an S matrix on a de Sitter space. So what I'm trying to say to you students is that you're not normally trained to analyze or understand astronomical analysis and astronomical data. But today we have a situation where it is, I think, important that theoretical physicists do try to understand cosmological data, because only then you can get an appreciation of how seriously to take what you are told about the nature of our universe as a whole. So yesterday I discussed with you that we are in an expanding universe. You know about the Hubble expansion. All galaxies are supposed to be going away from us. But the actual situation is that locally, the universe is not homogeneous. It has a lot of structure, and not all galaxies are going away from us. For example, our nearest neighbor galaxy, which is Andromeda, is in fact falling towards us. So we have so-called peculiar motions, which are due to inhomogeneities in the local universe. And this is in fact reflected in the fact that the cosmic microwave background has got this dipole asymmetry, which is because we are moving in this direction towards that hotspot at a velocity of about 370 kilometers per second. And, this is not unnatural. There are inhomogeneities. We have peculiar motions of a few hundred kilometers per second compared to the Hubble expansion rate, which is 70 kilometers per second per megaparsec. So up to a few megaparsecs, you would expect peculiar motions to be as important as the Hubble rate. The anomaly is that we expect the same dipole then in the distribution of distant objects like quasars. And here is a map of quasars. You can see the same hotspots and cold spot, but the amplitude of this is much higher, as marked here, than what you expect on the basis of this 370 kilometers per second. However, the directions are consistent. So this is called the cosmic dipole anomaly. And it is not just in the quasars, it is also there in the distribution of radio sources. So here is a compilation of those measurements made by these authors. This was 2 years ago. And you can see here that this this vertical black line is the expectation on the basis of the cosmic microwave background. And this is the data for various catalogs of radio sources. They have different names, never mind the names. The fact is that you can see that these measurements are discrepant. Now, the early measurements had large error bars, so even if they're discrepant, it is not a worry because they could just be a fluctuation. But it is hard to make that argument for something like this. Notice that these error bars are all 3 standard deviation error bars. So, none of them should be anywhere close to the black line, means that there is a problem. So I think it is now pretty clear that there is a problem in the sky. In other words, if I boost to the rest frame in which the microwave background looks isotropic, in that rest frame, the distribution of quasars or radio sources or distant matter, supernovae, whatever, will not be isotropic. And so what that means is that we have to ask, are we entitled to use the standard Friedmann-Lemaitre-Robertson-Walker model, which is the basis of the lambda CDM cosmology? Now, the issue is that the microwave background dipole itself is believed to be kinematical in origin, as I said, due to our motion. And there has been a cross-check made of that by the Planck satellite, which is in fact given an answer consistent with the standard model. So what happens is that if you have if you are moving in some direction, then you are breaking the symmetry of the sphere, right? You're picking out a particular direction. So what that means is that if you decompose the sky in spherical harmonics, which are orthogonal functions, then because you are breaking the symmetry, you will induce correlations between those otherwise orthogonal functions. They will become not independent of each other. And these correlations will be seen between the multipoles of the microwave background, the higher multipoles. This is just due to our motion, aberration, old effect. And the Planck satellite actually sees this effect. You can see that this is the expectation for the correlations, and the measurements at different frequencies are consistent with that. So they can say that independently, they can detect that we are moving at this velocity, 384 plus minus 78 plus minus 115, which is consistent with 370, although with large error bars. So this is only a less than 3 sigma detection. But other people say that they can get it to be more significant by doing the analysis a different way. So essentially, people are pretty convinced that the microwave background itself is the result of our kinematic motion. But in that case, the dipole in the matter cannot be. Okay, it's one or the other. So I told you yesterday that this has led to lots of discussion about whether we live in a fundamentally anisotropic universe and how such anisotropies might arise, for example, from the development of large-scale structure, which happens at about a redshift around 1. However, this would mean giving up the Friedmann-Lemaitre-Robertson-Walker models, which is the basis of the standard cosmology. Now, many people are reluctant to do that, and they wonder if you can somehow modify the model to make it consistent with this dipole anomaly. And one possibility is the following. This is a subject in itself, so I'll just give you the bottom line. You can ask me questions about it later. You know that all the structure in the universe was generated from primordial fluctuations, probably generated by inflation. And these fluctuations are taken to follow a power law spectrum. This red line is the assumed power law spectrum of the initial fluctuations, which give rise to all this structure. But in fact, today we have enough data from the microwave background and from large-scale structure that we can do something, instead of assuming the spectrum, we can try to actually construct it from the data. And that is a process of deconvolving the data in order to determine the primordial spectrum. And what we get is this blue line. And these are the associated error bands. So you can see that the blue line has got lots of structure, but that structure is not statistically very significant apart from this thing here, which is corresponds to the multipole at L of 21, which is a bit anomalous. But otherwise, it is consistent with that power law. And then at very large scales, which correspond to very low multipoles, the power drops. This is what you actually see on the sky. But still, it is not, this is 1 sigma. So you can see that at 2 sigma or so, it is consistent with the expectation of the power law. However, what this raises is the possibility that the inflation was not as simple as people think it is. It did not just generate a smooth power law fluctuation. It maybe generated so-called isocurvature perturbations, right? First of all, this suggests that inflation did not last forever. It lasted just long enough to create the patch that we live in of the universe. So out here, we are seeing the beginning of inflation. But what this raises is the possibility that there is a particular kind of perturbation called an isocurvature perturbation. Isocurvature, as it means in the name, is that the curvature of space-like sections is unaltered. The matter fluctuation and the radiation fluctuation go in opposite directions so as to cancel out. So the net curvature is retained to be 0, but there are fluctuations in the density in opposite directions. And that isocurvature perturbation has the property that, as we have shown in this paper here, that it does not affect the number count dipole, but it can affect the CMB dipole, right? So if there was a perturbation like that oriented suitably in the universe along the direction of the CMB dipole, then it could cancel out part of the CMB dipole. So maybe we are actually moving at not 370 kilometers per second, but more like 800 kilometers per second. But the reason why the CMB does not show that is that part of the CMB amplitude is being cancelled out by this, right? Now, this is possible. So in principle, that could be happening, and that would then explain the dipole anomaly without having to give up the whole framework of the standard cosmological model. So people would be happy. But of course, we are not so easily satisfied, because if, in fact, this perturbation has no effect on the matter dipole and only affects the CMB dipole, then how is it that the two are pointing in the same direction, right? Then there is no connection between the reasons why they have a dipole. So there is no reason why they should be aligned. So I'm not very happy with this explanation, but in principle, such things could be happening. So this is worth looking at. So what I want to do today is to tell you a bit more. First, let me say that there is some new data coming, for example, from this telescope, which is currently being built in Chile. People can join this collaboration and test whether these anomalies are really there by looking at a much bigger data set that is going to come from this telescope, the Rubin telescope. And we have proposed such projects for testing the isotropy of the universe, testing the homogeneity of the matter field, and so on. So this is going to be happening over the next few years, and I'm very excited about that, because this is an opportunity to directly use data to determine this. But today I want to talk about something else, which you would have heard of, although maybe don't know in detail, which is the discovery back in 2000, well, it was back in 1998, and it was awarded the Nobel Prize for Physics in 2011, the discovery of the acceleration of the universe, the cosmic acceleration. And this, made headlines everywhere. It got lots of awards, in particular the Nobel Prize. And I don't think it is an exaggeration to say that it is because of this that the standard cosmological model, which is based on the idea that the acceleration of the universe is caused by a cosmological constant, became widely accepted. You know, this is kind of a confirmation that, you know, the community accepts this validity of this. However, in detail, most people don't actually know very much about how these measurements are done and interpreted, and I assume that includes all of you, because that's why I asked how many of you are familiar with this kind of data, and nobody raised their hand. So let me tell you very briefly and in kind of like executive summary of what is involved. So what is done in this cosmic acceleration business is that they look at distant objects called supernovae. And supernovae come in two types. There are supernovae where the whole star collapses because nothing to hold it up. All the fuel has been burned up. And that then explodes. And you get, from the core collapse, you get neutrinos. The last one that was seen was supernova 1987A. But there are other kinds of supernovae which are just like giant thermonuclear bombs, where there is for example, a star which is accreting matter from a companion, and when its mass exceeds the Chandrasekhar mass, then it can't any longer be supported by electron degeneracy pressure, and it explodes, right? And the way that the astronomers know which kind is which is just by looking at the spectrum. The type 1a supernovae have no hydrogen lines in the spectrum, but they have silicon lines, whereas the type 2 supernovae have usually hydrogen lines. Actually, there is a class of core collapse supernovae which have no hydrogen lines, but they have no silicon lines either. So you see there's a bit of morphology going on, but they think they know how to recognize this. And what you do is you measure the light curve of the supernovae, you measure the fact that there was nothing in the sky at some point, and then suddenly the brightness started increasing, and then after a while it starts fading, and you can see that this goes on for of order a month. That's how long it takes for this thing to fade away. This late time thing, you can see this is a log-log plot, the magnitude versus the log linear plot. And this thing here is due to the radioactive decay of nickel-56, which is synthesized in this explosion. So what the astronomers do is that they measure these things in different bands, which have got different names like blue and infrared and so on. And what they do is that they measure the peak magnitude and they measure the width of this light curve. Why is that important? Because if you actually plot all these light curves together, there is a big scatter. Okay, you can see that the scatter is order of magnitude in the here. The magnitude is itself a logarithmic measure of the luminosity, how many, how many ergs per second are being put out. So this is a big scatter. However, it was found that the width of the light curve and the peak magnitude are correlated, or rather anti-correlated. And by using this anti-correlation, you can actually scale, stretch all these light curves to more or less lie on top of each other. So if the light curve width was very large, right, then correspondingly you can read off what the peak magnitude was and correct for it. And so this is a stretch correction, and the correction is different in different bands. So that's also a color correction. So you do two kinds of corrections, and then you can create this so-called template fit, which is that they all fit onto the same light curve. And now you see the scatter is a lot less than here. So now you can start doing some cosmology with it. Unfortunately, you don't understand why these correlations are there. There is no model of these objects. These are far too complicated to do a computer model of. So you don't really know the physical reason. So everything is empirical. So what people do is that they do surveys of the sky. And here is a survey called the Joint Light Curve Analysis Catalog that was a compendium of 4 different surveys. And this was made public in 2014. And what it shows is the distribution of these objects on the sky. So this is in right ascension and declination, which are astronomical coordinates, natural for a telescope on the ground. And this blue strip here is from the Sloan Digital Sky Survey, as you see here. And in redshift, they are around a redshift of 0.1 to 0.4. Okay. Then there is these little red dots, which are very nearby supernovae within redshift of 0.1, and they're all over the sky. Okay. And then at very high redshift beyond 1, there is the Hubble Space Telescope, which are these little purple points you can see here and there. They are also randomly there over the sky, and they are at high redshift. So they have been redshifted to the infrared, and so you need to go above the atmosphere to see them, which is why you need the Hubble Space Telescope. And then most of this data is coming from this supernova legacy survey, the green, which you can see is only in 4 directions in the sky. 3, and I don't know where is the 4th one. Okay. So in other words, the distribution of these objects on the sky is rather scattered. It is not very uniform, and the data is very limited. But these people at least analyze them all in a consistent way using the same template that I discussed. And they publish these things. They tell you what the peak magnitude is, what the color correction and the stretch correction were. Notice that the redshift of the supernovae, which is measured, is in fact already in the CMB frame. In other words, they have been boosted to this frame in which the universe is supposed to look isotropic. We have seen in the previous lecture that there is a problem there because the assumption is that once we go to that frame, then the distribution of matter is also isotropic. But actually, we find that in that frame, the matter distribution has a dipole which is not isotropic. So the very assumption that underlies this analysis is now in question. Nevertheless, this is what has been done. Once you measure the magnitude, you can construct this object called the luminosity distance, which you can relate to the cosmological parameters that I discussed in my first lecture, omega matter, omega curvature, omega lambda, and you can determine them by fitting to the data, right? And that is how the supernova data showed that 0.8 omega lambda minus 0.6 omega m equal to minus 0.2 plus minus 0.1. But actually, you don't really need to use a cosmological model because what you can do is you can expand that luminosity distance in terms of the derivatives of the scale factor. So the first derivative of the scale factor is the Hubble parameter, h naught, a dot by a. The next derivative is the acceleration, a double dot. So people in astronomy, traditionally, they have written it in terms of this variable q naught, which is a double dot times a divided by a dot square. Okay, this is not normalized so that it is a dimensionless number. And it had a minus sign put on it in order to make it a positive number because they thought that the universe must be decelerating because gravity usually pulls things. So therefore, it was defined with a minus sign in order to make the quoted Q naught from data a positive number. Great surprise, it has turned out to be a negative number. That is the cosmic acceleration. And then the next term in the expansion, which is a triple dot, that is also suitably normalized to make it just a number. And this is in fact degenerate with the curvature. Right? Now, one more thing that I need to tell you, although this is a little technical, but and you are all theorists, so maybe this doesn't mean much to you, but you should know that the way that the analysis of the supernovae has been done is from a statistical point of view, somewhat unprincipled. What they do is that they take the measured object magnitude and they subtract from it the expected magnitude for a theoretical model, namely lambda CDM, and you square it and you divide it by the uncertainty in your measurement. This is fine. This is called a chi-square, and you know that you need to minimize the chi-square to get a fit to the data. But what they actually do is they add another uncertainty which is arbitrary and which is adjusted till you get a chi-square of 1 per degree of freedom for the fit. In other words, you get a perfect fit. Now, this is not a good strategy if unless you know that the model that you are fitting to is the correct model. But in this case, we are trying to understand whether lambda CDM is even the correct model. So you can't just assume it and do this exercise. This is not very principled in a statistical sense. So what we did was to introduce something called a maximum likelihood estimator, which is the standard thing that is used in data analysis. So we just say, what is the probability of the data given the model? And the probability of the data can be factorized into the probability of seeing the parameters we are seeing for the supernovae and the parameters we are seeing for cosmology. But we make the assumption that the supernovae are independent of the cosmology and the cosmology is independent of the supernovae. So you can factorize that. And the actual these distributions of these correction parameters are fairly close to Gaussian. So we can approximate these things by Gaussian distributions. And we all know how to integrate a Gaussian. So from this, we can determine what the likelihood is analytically in just 2 lines. We don't need to do expensive Monte Carlo calculations and so on. Now, the net effect of this is that in that plot of omega lambda versus omega matter, where this banana was up here, okay, in the usual standard analysis, we find that it actually comes down here. And you can now see that the evidence for acceleration is actually pretty weak because this line separates acceleration from no acceleration. And you see the 3 sigma contour is already crossing it. So in the fit, we have omega matter, omega lambda, and the parameters that describe the light curves. And in fact, the fit is pretty good. However, the significance for acceleration is very weak. Okay, this is not for a fundamental discovery, you want at least 5 standard deviations, right? Nobody believed the Higgs discovery until the Higgs signal until it got to 5 sigma. And then you needed 2 independent experiments. So this is not sufficiently convincing. Now, of course, on this plane, you can put other constraints. For example, there is a constraint which goes diagonally across, I showed you, which is from the fact that the curvature of space sections is close to 0 from the CMB. But that is only true for the lambda CDM model, where you have that sum rule. In general, you don't know that is the case. So you can't use that. And by the way, people then said our statistical method is something strange about it, but other people who use a standard Bayesian hierarchical model get the same answer. So this was our answer, the green line, and the yellow line is their answer. You can see it matches. The reason why this group here does not get a smooth line like we do is because they're doing a computationally much more intensive exercise. They're doing something called a Markov chain Monte Carlo scan. And so it will take a long time for the chains to converge, and that's why these lines are irregular. But you can see that they are in broad agreement with what we got, and they're certainly not in agreement with the plot that you see everybody showing, okay? So bottom line is that we did not see that there is much evidence for acceleration from supernovae. But the supernovae people came back and started saying that, okay, we had taken these corrections that we have mentioned, the stretch and color corrections, to be constant with redshift. That's actually what their own paper had said. But they say, look, we can imagine that this data is showing a trend with redshift. You can imagine that there are these trends, okay? With the Hubble Space Telescope, there's the uncertainties are too large to claim any trend, but you can perhaps claim that with this data and this data. So when they do this, effectively they're adding 12 more parameters. There are 3 more distributions each, and 2 of the 3 times 2 times 2, because they're fitting parabolas which have 2 parameters. So we had only 10 parameters, and now they're adding 12 parameters. And by doing that, they are managing to take this banana, this contour, which, as you can see, is touching the no acceleration line, and they lift it. Okay, so this is what we did. They reproduce our work, but then they actually managed to raise it by imposing these corrections. But even so, the evidence for acceleration is only 3.7 sigma. It is still not got to 5 sigma. And even though the number of supernovae has gone up from 100 to 1,000, it is still not much better than when it was first claimed. So all this makes one wonder as to whether there are systematic uncertainties which are mimicking acceleration. Now, another point, this is going back to what we discussed in the last lecture. I told you that our velocity is determined by looking at the cosmic microwave background dipole. And according to that, we are moving at 370 kilometers per second. So there is that corresponds to some redshift, which is called Z sun. And what we then do is to boost all the redshifts that are measured from our position in the so-called heliocentric rest frame to go to the CMB rest frame. And then we have to correct for the fact that the supernova host galaxies themselves have peculiar velocities with respect to the supernova frame. So you do two Lorentz transformations in order to get to the cosmological redshift from the one that is measured from the solar system, right? This is the standard exercise. Now, I work with Mohammad Ramiz, who I mentioned earlier, and he actually is very good with data. So he looked at what these people had done, and he discovered that the corrections that they had made, this quantity C, which is plotted here, right, that thing up there, if you plot it against redshift, it looks like there are large corrections, and then they suddenly stop at this point. Why do they stop? Because they have assumed that we have actually already reached the CMB frame, and therefore there are no further corrections to be made beyond that point. Okay? I mean, I apologize that I'm giving you a lot of detail and you probably, cannot follow all of this, but I think you get the point. You can see that these corrections that are being made to the data are suddenly stopping at some point. Okay? And this point corresponds to where they think the universe becomes homogeneous, we converge to the CMB frame, and business is as usual. But actually, what we have discovered in the last lecture is that none of this is true. We have not converged to the CMB frame. There is a bulk flow which stretches out beyond that, and more to the point, the distribution of matter is not isotropic in the CMB frame. So this cannot be justified, right? So what we did was to undid all the corrections to get the original data, because we want to check if the acceleration of the expansion is actually isotropic. Why? Because if it is due to lambda, Lorentz invariance requires that all observers see the same vacuum. So if it is vacuum energy, then the acceleration due to it must be isotropic. Okay? I hope you all agree with that. However, when we do the analysis, we take that same luminosity distance from the magnitudes and we do a Taylor expansion, just sticking to the first two terms. But we now let this acceleration have a dependence on angle. We have a monopole term and a dipole term. And then we ask our maximum likelihood estimator to see if this fits the data. And it says, yes, it fits the data very well. In fact, the acceleration is mainly a dipole. This is the dipole plotted versus the monopole. The monopole is almost zero. This is the line of zero monopole, right? It's very close to zero. But the dipole is very strong. It's 50 times bigger. And in fact, on the sky, when we plot the dipole, it is maximum in the direction of the CMB dipole, right? So what this shows is that the cosmic acceleration that is deduced from supernovae is actually mainly along the direction that we are moving towards this hotspot in the CMB. It is not uniform over the sky. And so it cannot be due to lambda, right? Because anything that is due to vacuum energy is locally covariant, and therefore it must be isotropic. So what this suggests is that this acceleration that we deduce from the data is not something which is a global property of space-time. It is just because we are located in this deep bulk flow, which I told you is anomalous and which is also going in this direction. And this is something that is, let me skip all this and, come to this and I'll go back to that. This is because in general relativity, all energy momentum gravitates. So the local bulk flow with the peculiar velocities which are coherent, that is also energy momentum, right? And what that makes us is a so-called tilted observer. You see, we start out assuming that we are Copernican observers. We are typical, we are random. We are at some random place in space-time and we should see the universe as isotropic and homogeneous. But in fact, the CMB dipole tells us that we are not a random observer. We are a particular observer moving with a particular velocity in some direction. Then the standard cosmological idea is that that velocity is a peculiar random velocity. If you average over a large volume, then it will average out to zero, and we will get back to the standard model. But the observations show otherwise. They show that we are not actually getting to the standard model. We are not getting to the CMB frame, and that this bulk flow is continuing much more deeply than it is expected to in the standard model. So what Christos Sagas, he's a relativist in Greece, and collaborators have shown is that what that does is it makes us a so-called tilted observer. We are in this yellow patch. There's the bulk flow, and A is the global spacetime. And because of this, since we have a mean peculiar velocity, and that patch, it depends on whether the velocity is converging or diverging, then you can calculate a quantity, this theta. And this observer who is inside such a patch, when he or she interprets cosmological data, the acceleration parameter they infer from that data now has a correction term because of this energy momentum of that flow. And that correction term has an opposite sign if the flow is converging, which our local flow seems to be. So what that means is that the global Q value might actually be, positive. That, in other words, the universe is decelerating. But locally, because we are embedded in this bulk flow, if we don't take care of that, if we don't account for that, then we will infer negative deceleration parameter. So in other words, going back to this plot here, we are meant to be at lambda CDM is here. Lambda CDM is a deceleration QM of minus 0.5. Okay. But in fact, the data is consistent with it being close to 0, right? Because in the lambda CDM model, of course, there is only a monopole term. There is no dipole term. Dipole should be 0. It should be here. So you can see that these two are discrepant at almost 4 sigma. Okay. They are not in the same place. And this is difficult to extract from the data. This is what comes out from the data, and the two are discrepant. In other words, the cosmic acceleration that we see is consistent with what you expect for a tilted observer. And at this point, by the way, we went and looked at the original data that was awarded the Nobel Prize, the two teams which looked at about 100 supernovae. And you see, most of the supernovae they looked at were actually in the direction of this dipole hotspot. They did not have many supernovae in different directions because you observe from some telescope on the ground, so you can't actually see the whole sky. And that might explain why they inferred acceleration. And we have recently gone to a much more bigger catalog of supernovae, which is more than twice as big, Pantheon Plus. And you see the JLA had this distribution in redshift. Pantheon Plus has many more supernovae, especially locally. So we can now do tomography in redshift. We can take slices of redshift and determine how this dipole varies as we go in redshift. And you see, regardless of if we do the analysis in the heliocentric frame or the frame of the CMB or the local group frame or the CMB frame with velocity corrections, whatever, they're all showing dipoles. The reason why this is showing a negative dipole and that is showing a positive dipole is because I showed you a picture that the solar system is orbiting around our galaxy in actually the opposite direction to the direction of the CMB hotspot. So the velocities are in the opposite directions. That's why the signs of the dipole are opposite. So as you go to high redshift, by the time you get to redshift of 0.1, this dipole has disappeared. This is just what you expect because that is meaning that the bulk flow that is responsible for this is dying out. And incidentally, these directions of these dipoles are all consistent with that of the CMB direction or with the local bulk flow direction. So it makes a consistent story. And incidentally, the Hubble parameter also has a variation of the order of 2 to 3% in this redshift range, where in fact there is supposed to be something called the Hubble tension anomaly, where they claim to measure it to 1% accuracy and then claim that there is a discrepancy with the value deduced from the CMB. But actually, we see that there is a systematic uncertainty in the Hubble parameter, which means that you can't really make such a strong conclusion. So this is suggesting that cosmic acceleration is actually an artifact because of this relativistic effect that I have just explained. Now, there are other anomalies in the sky. So, for example, the cosmic microwave background that you're always shown as evidence for the standard model actually has more power in one part of the sky than the other part, and this is called the hemispherical power asymmetry. It's there at about 3 standard deviations. There is a cold spot, which is anomalously cold. The temperature is low, the fluctuations are very small, and this is at about 5 standard deviations. And interestingly, the higher multipoles, the quadrupole and the octupole, you see this has 4 and this has got 8, 4 hotspots and 4 cold spots. They should be randomly oriented, but they're actually nicely aligned. So these are all mysteries about the cosmic microwave background, which people have pointed out for quite some years. And they also point to the need for a re-examination of the standard cosmological model. So let me come to my summary. I know you have had a long day and I don't want to give you more data today, but I think I've given you some idea. The standard model of cosmology was established 100 years ago. Friedman's paper was 1922, right? Today it's 2024. And at that time, there was no data. In fact, we didn't even know that we lived in a galaxy, right? That came about 15 years later. But now we have data, so we should test the assumptions on which that was based, namely the assumption of isotropy and homogeneity, right? Instead, what we are doing is we have constructed a model called lambda CDM, and we are supposed to be doing precision cosmology, which is measuring those model parameters. But the model itself might not be the correct description of the universe. So now you understand why I quoted Dennis Sharma at the top. You should first try to find out what our universe is really like. So what I have shown you is that we are in a bulk flow, which is stretching out beyond the scale at which the universe is supposed to become homogeneous. And also that the inference from type 1a supernovae, that the expansion rate is accelerating, may be due to this bulk flow and not due to lambda. Now, that is of major significance for fundamental physics because the entire fundamental physics community has more or less accepted the claim by the astronomers that we are in an accelerating universe, we have to deal with de Sitter space, and there is still no explanation for such a small cosmological constant from fundamental physics. So people do all kinds of gymnastics, they invoke the anthropic principle, there is talk about the landscape, and now there is a talk about the swampland in string theory and so on. In other words, it's a very uncomfortable situation. The thing that is most crucial in all the observational findings is that the rest frame of distant quasars is not the same as the rest frame of the microwave background. If you boost to the rest frame of the microwave background, then the universe should look isotropic in terms of radiation. But in that frame, the distribution of matter will not be isotropic. And this is a puzzle because the two were, after all, in thermal contact at the time of last scattering, at the time 10,000, redshift of 1,000 when the universe was still ionized. How did they become disconnected? It's something to do with structure formation, but that needs to be solved, okay? But what that means is that you cannot assume this FLRW metric for analyzing data today. It is okay for analyzing the CMB, for doing early universe cosmology, but not for analyzing the data today. So what should we do? Well, the manifesto has already been given by George Ellis and Stoger years ago. They called it the cosmological fitting problem, how to actually use data to construct the metric. And today, with advances in machine learning and so on, this is actually an interesting possibility that we can directly use data to construct the metric of the universe instead of making the maximally symmetric assumption, the simplest possible assumption, which was indeed done 100 years ago when there was no data. Today we have data. Let us take a different data-driven approach to doing cosmology. So I'll stop there. Thank you. And I just want to say that in case you are wondering, this is not a fringe subject. It has actually become a topic of mainstream discussion. So in April this year, we organized a meeting at the Royal Society this is with James Binney and Roya Mohai and John Peacock and myself. And we had experts speaking on all aspects of this, starting with Jim Peebles, who won the Nobel Prize for developing the standard model. And we had very good discussions moderated by excellent chairs. And if you are interested, please look at this website here. And all the talks are there on the website, so you can get a feeling yourself of how seriously to take the things that I have talked about. Okay. I'm happy to take some questions now.
We thank Professor Sakar for the very interesting talk. Any questions?
Including on yesterday's lecture also, if you like.
Hello, Professor Sakar. Thank you for your interesting talk. And you have mentioned that maybe nowadays we have some data on the cosmology, and we can feel that something like the CMB is not quite like the maybe 100 years ago we are thinking about this universe. So do you think it's possible to maybe just like some assumption of the Einstein's special relativity that think there is no proper static frame is not true now, maybe? It seems that from the CMB, yeah.
I understand what you're saying. So as far as the CMB is concerned, as I said, there are 3 points. One is that the CMB dipole was actually predicted because it was already known in the 1960s, before the discovery of the CMB, that we have a peculiar velocity. Our local velocity field is not isotropic. There are irregularities in it. There are peculiar motions. And so what Shama inferred from that is that when we discover the microwave background, it will not be isotropic. We should be moving with respect to it, and therefore it should have a dipole anisotropy. And then Peebles and Wilkinson calculated using special relativity how the temperature should vary over the sky. If you are an inertial observer moving with velocity v in some direction, how should the temperature look and the direction theta? And that variation fits pretty well with what is observed. Also, recently the Planck satellite has looked for, they look at the fluctuations on the sky, and they do a multipole expansion. So they do a spherical harmonic expansion of these fluctuations on the sky. And when they do that, they find that it actually, there is evidence in the correlations between the higher multipoles that we are moving in one direction. I showed that a little while ago. Let me go back to that. And that evidence is okay. It is not very precise at the moment, but it is independent evidence. Here. You see, this is independent evidence that we are actually moving through the cosmic microwave background. What this is showing is that when you move towards the CMB dipole, then we see the expected correlations. If the velocity is oriented at right angles, then you see there is no effect right on top of where you should be. So this little shift here, that is a direct measurement of the velocity by looking at the breaking of anisotropy due to our motion. And all this is suggesting that the CMB dipole is actually kinematic. But if that were true, then what are we to make of this? That, if this is kinematic, then if I boost in this direction at 370 kilometers per second, then the sky should look isotropic. But the dipole in here is much bigger than the dipole here. It is twice as big. You can see that here, the amplitude. Here it should be around 7 point something, and it is, 15 point something. So that means that in that same reference frame where the CMB is isotropic, the distribution of quasars is not isotropic. The distribution of radio sources is not isotropic. And so we cannot use the Friedmann-Lemaitre-Robertson-Walker metric and the Friedmann-Lemaitre equations to analyze light curves of supernovae, to analyze baryon acoustic oscillations, to analyze weak lensing. This is what it is being used for today in cosmology, because it is assumed that the same frame in which the CMB is isotropic is also the frame in which the matter is isotropic. Okay, so to answer your question, we have to understand why the distribution of matter is anisotropic in that frame. Otherwise, we don't know what mathematics to use. You see, that's the point.
Yes, thank you.
Thank you.
More questions? Okay.
So you mean that so you mean that this anisotropy dipole could solve the Hubble tension problem?
Well, it is. I don't think there is such a thing as a Hubble tension problem, because the Hubble tension problem is the statement that somebody has managed to measure the Hubble parameter to 1% precision locally, and that disagrees with the Hubble parameter deduced from the microwave background at something like 5 sigma. So the whole question is, are there uncertainties in the local measurement which are bigger than this 1% that is being claimed? And what I'm saying is that we find that the Hubble tension is for the Hubble parameter h sub 0. H sub 0 is meant to be isotropic. It's meant to be the same in all directions. But we find that it is actually not the same in all directions. It has an anisotropy of 2 to 3% in a band here. Okay. Sorry, I don't have the plot here, but you can look at our paper where this is described. And so the point is that you cannot actually measure the Hubble parameter to that kind of accuracy locally. It's not possible, because it is in fact something which is well, let me just put it this way. Let me show you the original plot of the anisotropic universe. So then you get some idea about why I am skeptical that you can actually even define the Hubble parameter. So let me give you an analogy. What we are doing is we are looking at a very anisotropic universe. So let me sort of get to the correct plot and I'll show you. Yes. So let me share my screen again, and this time I'll pick this plot here. Yes. Okay, can you see my screen?
Yeah.
Yeah. So this is the real picture of the local universe. Okay. We are in the center of this picture, close to we are part of the Virgo cluster. We are moving towards Shapley, etc. So the statement that is being made is that the Hubble parameter can be measured by calibrating supernovae with Cepheid variables within this little local volume, right? But the question is, this is a bit like saying that I want to measure the radius of the Earth. Supposing you say you want to measure the radius of the Earth, what are you saying? You are implicitly saying that the Earth is a sphere. Okay, and so that it has a well-defined parameter called the radius, and then you can measure the radius to some arbitrary precision. But actually, the truth is, as you know well, the Earth is not a sphere to arbitrary precision. It is actually what is called a geoid. It is deformed by 100 to 200 kilometers at the equator and flattened at the poles, etc. And then its surface is not totally smooth. It has got mountains. It has got deep underwater trenches. They go up to a few miles, few tens of kilometers. So in other words, you can measure the radius of the Earth to a precision of 10%, no problem. It's a well-defined quantity to 10%. You can probably even define it to about, what is it, 4,000 kilometers. So you can probably even define it quite precisely to about 5%, right? But you can't really measure the radius of the Earth to 1% precision, because that means that it should have no irregularities or departures from a sphere more than 50 kilometers, right? But that is not the truth. That is not the Earth's radius. That's not the Earth shape. So similarly, you cannot define the Hubble parameter H0 is the property of an assumed underlying theoretical model. The question is, in the real inhomogeneous universe we live in, can we make corrections for all these irregularities and peculiar flows and everything to 1% precision? And my answer is no, you can't, because the data itself is showing that there is a variation by more than 1% over the range in which the CFIT calibration is going on. And therefore, you cannot actually define the Hubble parameter to better than 2 to 3%. Okay? And what that then means is that you have you cannot actually define the you can't actually claim that there is an anomaly. The systematic uncertainty in the determination of this is too large. Is that clear?
Okay, thank you. Yeah. Your explanation is very clear. Okay,
Yeah.
thank you.
Okay, because
I
of
should
time,
add,
I think.
No,
Yeah,
sorry. Please
go
go
ahead.
On. No, it's okay. You go ahead.
I'm just to conclude. Do you have
Okay.
some more comments?
No, but all I wanted to say is that if any of the students are interested in learning more, they are welcome to email me and I'll direct them to the literature.
Okay, thank you much. So let's thank Professor Sakar again.
Thank you.
Okay, thank you much, Professor.
Okay, all right. Bye-bye.
Hope to see you later.
Yeah.
Hope to see you next year.
Yeah.
Bye.
Thank you. Bye.
Thank you. Okay, that's the end of today's lectures. We're going to continue tomorrow.